I would like to welcome you at the third POP3 Profiling and Optimization Tools workshop, which is co-organized by Center of Excellence POP and also by NCC Austria, Czechia, Hungary, Poland, Slovakia, and Slovenia. It's under the auspices of a training sprint initiative that the EuroCC project together with Castiel project is organizing. And we will have many different tutors from different centers, Jülich Supercomputing Center, Brian Wiley, and from Barcelona Supercomputing Center, Judith Jimenez will be presenting today, and also Radim Vavčík from IT for Innovations. And regarding the recording, we are recording only the tutorials, not the hands-on sessions. And with that, I would like to pass the speech to our first speaker.
I think that will be me. Thank you. Okay, good morning, everyone. My name is Eric Valency from the University of Versailles in France. I am in charge of coordinating the training events from the VI-HPS consortium, and I will now present the VI-HPS consortium. So the Virtual Institute High Productivity Supercomputing has been funded in 2006 with the goal to improve the development process of codes running on parallel computer systems and high-performance computing. So the idea first is to develop tools that can help with analyzing and optimizing performance on HPC systems, and then spread the use of these tools and the associated techniques through various workshops, such as this one, for instance, or additional tutorials in conferences, and offer services, various also services. So all information relative to the VI-HPS consortium is available on our website. When you can see the URL here. You can get information on this website on any past and future event, and of course also this one, and also information on the various tools available from the consortium. So the historical partner founders were these, sorry, just one issue. Well, these four universities, Jülich Supercomputing Center, RWTH Aachen, Technische Universität Dresden, and University of Tennessee, Knoxville. And then these historical partners were joined across the years by various other entities, Barcelona Supercomputing Center, the Erlangen Computing Center, Lawrence Livermore National Lab, the Leibniz Supercomputing Center in Munich. The latest one is Linaro, which took care of the formerly Alinea tools and then ARM tools. University of Darmstadt, of Munich, of Oregon, Stuttgart, and of Versailles Saint-Quentin. So we offer various tools. The consortium offers various tools. The tools we'll be focusing on during these workshops are the Paraver DMMAS Extrae tools from Barcelona Supercomputing Center, Scorpy, Scalasca, and Cube from Jülich Supercomputing Center. We'll also have some presentation of the Macao and Mustarker tools. So the BSc tools mostly focus on tracing parallel events and analyzing the generated traces. Scorpy is measurement infrastructure, and Scalasca allows to analyze large-scale parallel traces and provide some performance insights. Macao is an assembly analysis and optimization framework, and Must and Archer allow to perform correctness checking of MPI codes. There are a lot of other tools available from the consortium. So all these tools are, sorry, this issue, yeah. All the tools are listed in the tools guide, which is available from the VI-HPS website. It is updated twice per year, and it contains basic information of each tools and how to obtain it and what they can offer in terms of functionalities. So we have also a lot of other tools. There is some performance modeling tools, workflow execution automatization, cache analysis, parallel debugging, various low-level performance analysis, integrating performance visualization and analysis. All these tools can be found on the website. And if you're interested in them, there will some of them will be featured in future tuning workshops. So the idea behind the consortium was to be able to provide tools for each step of the performance analysis and optimization process. So the idea is that if we start by executing or making sure, we want to make sure that our code is running correctly, so doesn't contain any errors, so that we can debug it, make sure that for instance, also that the code is correct, which is not so always obvious. Then perform some hardware monitoring to make sure that we are correctly using the machine capabilities. Being able to profile the application to obtain some traces that will then be able to analyze and to extract some performance insight out of that will then implement back into our code to be able to start with a new cycle. We'll get some additional insight on that with the POP methodology. So one important point to make is that a tool is not a magic wand that will automatically make an application or computer system more productive, but it's, as the name implies, a tool that will help you understand where the issues lie and how to fix them and how to address them. So the training and tuning workshop program aims at giving an overview of the various tools available from the consortium, explain what they can offer, how to use them, how they can be used on your codes, and provide some direct assistance on how to use them, interpret their results, and hopefully use that to improve the performance of your codes. And another interesting point for us tools developer is to retrieve some feedback from the participants to be able to improve our tools or the formats of the workshops for future events. So we have been doing this since 2006. Basically, usually we have 2 or 3 tuning workshops per year. This time it's our fourth tuning workshop this year. At some point, they were all organized online, of course, during the COVID pandemic, and now we are resuming the normal hybrid or on-site format for the workshops. So as you can see, we tend to organize this workshop wherever people are interested to host them. Most of them are organized in Europe, in Germany, France, Spain, but also in the UK. And we had a couple of workshops that were organized in the US or in Japan and Chile. So for now, this is the last such tuning workshop this year. We don't have any date for the next workshop. There will be some tutorials presented at Supercomputing in November. And of course, you can check the website where all future workshops will be announced and any relevant information will be available. And of course, we are always on the lookout for new locations where to organize these workshops. So if your university or company is interested in hosting such a workshop, don't hesitate to contact us. We'll be happy to organize this. Thank you.
Hey, I hope you can hear me. My voice is a bit rough this morning, but I hope that won't be too much of an issue. So yes, I will give a short introduction to the Performance Optimization and Productivity Centre of Excellence that is one of the organisers of this specific workshop today. The POP Centre of Excellence is promoting best practice in parallel programming. It's providing a range of free services to help application developers and other users of parallel applications to understand how their parallel applications execute on HPC systems, and providing support to guide how to get improved performance, improved efficiency in the most productive way of those systems. In contrast to most of the other centres of excellence that were funded by VI-HPC, it's transversal, meaning that it's across application areas rather than focused in one particular area. And we deal with all platforms and all scales, from the smallest scales to the largest ones, although the current emphasis is on the large VI-HPC systems and scaling to use those as extensively and productively as possible. The services are available within the VI-HPC area for academic and industrial codes and users. So it's not restricted. We welcome all usage. The Centre of Excellence has the partners who are shown here, the 8 partners listed. The Centre of Excellence is coordinated by Barcelona Supercomputing Centre. There are a number of partners in other parts of Europe, including IT for Innovations, hosting the workshop here today. And ourselves, I'm from Jülich Supercomputing Center in Germany. There's also Stuttgart in Germany and Aachen, who are 2 other partners there. We have a couple of partners in France, Teratech and Versailles. And a new partner that joined the consortium at the beginning of the year is Ines in Portugal. And Ines has also just applied and been accepted as a member of the Virtual Institute for High Productivity Supercomputing. IT4I is expected to apply and join sometime in the course of the year. So that's a consortium that's been up and running for a number of years, with additional partners joining. We have a range of partners involved, a number who are providing different tools that investigate parallel application performance and help with tuning. Other partners who are more focused on programming models and programming practices, and covering everything from an R&D background all the way through to working with academic and industrial applications. So it's a broad consortium of partners here. The reason for the consortium is that parallel applications are complex. Parallel computers are complex. Matching the codes to the systems is often a real challenge, and it's helpful to provide to get some feedback as to how the application is actually running and what are the most productive areas where you could actually improve performance and efficiency. It's important not just to improve time to solution, but it may also be important to look at energy to solution, and to also look at how you can scale up the application to deal with larger problems and potentially use more compute resources efficiently, and overall improve the productivity of those application development efforts. We're heavily focused on HPC applications, parallel applications. These, of course, are mostly using MPI for message passing between compute nodes. They may be using various forms of threading within compute nodes as well, typically OpenMP. But increasingly, we're dealing with and seeing applications that are using a variety of methods to access attached accelerators, whether that's through OpenMP, OpenACC, OpenCL, or some proprietary languages such as CUDA. So the Centre of Excellence has been running for a number of years. We started at the end of 2015. We're now in the 3rd phase of funding, which started at the beginning of this year. If you're interested in using our services, or you know someone who might be interested in our services, then the process is that they fill in a short questionnaire telling us about their application and what their interests are, and then we would work with them to go through the process of doing an assessment and audit of the application's performance. The request would be assigned to one of our analysts, one of our partners, and then they would work with you or work with the requester to make sure that the tools are installed on the machine that's to be used, and then work through the process of gathering and analysing the data and ultimately producing a report summarising the performance. In a more graphical form, it's shown here. If I put on the pointer, so here is the input where the person who's interested in using our services fills in the form. It gets assigned to one of our analysts. Those analysts work with you, providing a basic analysis report, and then they would report that to you, share that information with you, and that might lead to an additional service, one of our second level services that might repeat this process. There are other parts of the Centre of Excellence that are focused on dissemination of results. We are involved in the advocacy, working with customers to verify that our services are appropriate and are delivering what they're supposed to. And there's also part of the COE, which is distilling the insights from the assessments we do into a database, into a repository, which is then accessible and can be exploited by others. The services which are provided by the COE are, as I mentioned, free services. That means that that our time and our resources are paid for by VI-HPC. The two main services are an initial performance assessment, where we look at a range of performance metrics to assess the quality of the application execution and understand its performance. And if necessary, we would go further to look at identifying the root causes of why there are performance limitations, why there are performance issues that can be not only qualified but also quantified to determine how much could be potentially gained by addressing these. And so those recommendations would be shared as part of the analysis report delivered to the customer. There's a range of second level services which cover a variety of different aspects. They may be looking at correctness issues that may be a concern. They may be looking at energy efficiency, or there may be a more general follow-up of the different work that has been done, for example, to look at changes that the customer has made to the code to address certain performance issues, or maybe they have interest in comparing another platform that has a different environment, different processors, different compilers, etc. So there's a range of second level services that build on the basic performance assessment that starts the process off. This is a shared effort. We can do a limited amount on our own. We need to work with the customer to identify the test case and verify that we're running the test case appropriately on the system of interest. So there is naturally some involvement required by the customer, even if they can be involved as much as they want in terms of doing measurements and doing things on their own, or they need to tell us how to build and run the application on the appropriate system. So that is a two-way process where we work together. And of course, when it comes to making code changes to improve the application's execution performance, often that's something that the customer is themselves best suited to do, and they typically also want to be engaged in making changes to their own code. So again, that's a customer effort. We also provide training, and this is a training event of one of the many that we've been doing. We've done a number of workshops, as Cedric mentioned earlier, primarily through the Virtual Institute for High Productivity Supercomputing. Some of those have been special events which were organized specifically by and for women. Those are exclusively female instructors and assistants, and we're targeting underrepresented groups in HPC. So we've done a couple of those. They were promoted and sponsored by the Women in HPC organization, and we're planning and looking forward to do more of those in future as well. But basically, it's the same format where, like this workshop, you bring the applicants are encouraged to bring their application code, build and run it on the HPC system, and then we would work jointly with you to make sure that you can analyze and understand its performance and get some coaching and guidance as to what might be suitable changes, whether those are simple changes to make, changing runtime parameters, for example, or perhaps they may require some more substantial algorithmic changes that that would take longer effort and require more effort. But it's a collaborative opportunity to work together, work very closely with specific application codes, and get feedback as to how to use the tools effectively and understand what they're able to tell you. That isn't possible in a tutorial environment at a conference, but we have also done tutorials at a number of HPC conferences where in that restricted environment, we can't really work with participants' own applications. So we provide them either small applications, or we provide them with just the measurements to look at that we have made and provided for them. And we did a tutorial earlier this year at ISC conference, and UDIT was involved in the first instance of that several years ago, and we expect to do those tutorials again at future conferences as well. So that's a way of expanding the outreach and awareness of our tools and methodology to an audience beyond those who have the time and are able to join workshops such as this. Our customers are primarily the code developers, because we're getting very into the details of how the applications build and run. If someone is just a user of the code, then they may be interested to know how well it's running or not. Likewise, the infrastructure operators, the system admins, often they're interested to know whether applications are running effectively or not. But neither of them are typically in a position where they can make real changes to the application to improve its performance, without getting back to the code developer, the people who can who understand the code and can make the appropriate changes. So there they can benefit and use our tools and insight as well. Maybe they're also have a support team, an analyst team at the HPC Centre who are supporting their local users, and again, they can learn how to use our tools and methodology and benefit from them in that way as well. The tools that are part of the Centre of Excellence are available for the workshop today. They're installed. We're mostly working with open source tool sets, so we'll feature those in the workshop in the remaining days this week. They deliver very detailed information about how CPUs and GPUs are being used, and they are scalable up to the very largest scales. So certainly up to the scale of Carolina and well beyond that to larger systems as well. We'll be focusing on the tool sets from Barcelona and our tools from Jülich Supercomputing Center, but in the afternoon session, we'll also briefly introduce some of the other tools from the Centre of Excellence as well. There may be other tools that you're familiar with or that are available on the HPC systems. Sometimes we use those, or in many cases, we end up using those as well, especially if they're vendor tools that provide much more detailed insight into what's happening on the GPUs, for example, or what's happening with specific processors. So the methodology will be something that Judith will pick up on in her presentation that follows this, but just to briefly summarize things, what we're doing is we're combining a problem data set, a design of some form. We are combining the code that has been prepared to handle that, and we're running it on a specific HPC system, a computer cluster, for example. So that combination is what we're analyzing. We're generating various performance data from that execution. That performance data is something that we, as the POP Centre of Excellence, would summarize and produce an overview of its performance, how it's scaling, and what its efficiency characteristics are. That is then a starting point for going into much more fine detail and looking at specifics of what is the reason for specific problems. Why is there a load balance or some other issue that is showing up in that application execution test case? And from a wealth of analyses, we can then go into a very deep diagnosis of what are likely to be or could well be the the causes of those performance issues. So these are just very brief examples that we'll go through in more detail in the next few days, but we would typically have a summary of execution efficiency at different scales. So in this example, we're dealing with a relatively small execution with 1,000 processes up to a relatively large execution with 300,000 processes on one of the European systems. At the lowest scale, everything is relatively efficient, but as you increase the scale, things get increasingly less efficient, and there are issues that need to be investigated. But you need to understand what is the issue that you should address. And by following the green colors here, you can tell that communication efficiency is very good up to the very largest scales, so we don't have to worry about that. Whereas load balance is something that is not so great and deteriorates a little bit. And in this case, the red parts are the parts that stand out. Those are where the computation itself has become just too small. As we're doing a strong scaling here, the problem size per process has just got too small to be efficient. And that's why at the very largest scale, the efficiency has deteriorated substantially there. So that's much more information that allows you to interpret the typical scaling curves. So this is just a general speed up curve showing that the scaling efficiency is very good up until relatively large scales here of 100,000 processes or so before it tails off. And by looking at our efficiency table here, we can get an idea as to what factors we need to look into. In doing our analysis, we need to be careful that we're analyzing an appropriate part of the execution. So this is a timeline diagram. You'll see more of those later. At the beginning, there's some initialization that's going on. That's a one-off cost, reading in and distributing data. That's an unavoidable cost. It can be optimized, but typically most of the time is in some sort of computation that is repeated and maybe repeated many, many times in the course of a simulation. And then there might be some finalization where some results are collated and output at the end, which again is a one-off cost that might not be so valuable to analyze. So by distinguishing the computational phase, or by being even more specific and just taking one of the solver iterations, that determines as a focus of analysis, it would be the basis for the efficiency and scaling assessment. Another way of looking at things is not looking at execution traces, but more looking at execution profiles, where again, we need to identify which part of the execution, which part of the profile is the part that's most interesting to analyze, and then what are the aspects of that, whether it's use of MPI, or in the example here, it's the computational kernels running on the GPU that are spending most of the time. So we need to identify which of those are key issues, and then which processes and threads. They're not all necessarily doing the same thing. This example here shows, according to this color scale at the bottom, the ones which are red in the corners are the ones which have the highest time, whereas the ones in the interior, the bulk of them, are actually spending much less time on the GPU. So there's an imbalance here between the corners and the edges versus the interior. So those different aspects are things that our analysis will look into and give you detailed insight and recommendations as to how to proceed. So I think we are very good with the time. We have time now for Judith's presentation, who will go into the methodology, the metrics, and the process in a bit more detail. So if I exit this, stop sharing this, Judith, you should be able to start your presentation.
Yes, I think you see the slides.
I see your slides. You're good to go.
Great. So good morning. So my name is Judith Jimenez. I'm working at Barcelona Supercomputing Center, and today I'm going to present you a little bit the POP methodology, just starting from the point that Brian left, the last slide from the presentation of Brian. So the idea is that I'm going to show you how to identify the performance bottleneck through the efficiency metrics, and I'm going to present you a performance model. So the idea is that this model will be covered during the full training. And what is important today is that you understand the concepts of this model. And if you have any question, please feel free to stop me and ask a question. So the idea is that you get familiar with the concepts of the performance metrics efficiencies. Let me try to move to the next slide whenever this won't. Okay. So let me start with a question. As we have seen in Brian's presentation, I can compute the speed up and I can have a perfect scaling in a range with multiply by 15 the number of resources, and the speed up is a little bit more than 15. So even it's a little bit more higher than ideal. So should we be happy with that, with a perfect scaling? Well, you may be happy with a perfect scaling, but it's important you understand why you are getting this perfect scaling. Okay, so this is from a real execution. It's not a drawing plot. And I may tell you that this application is doing a strong scaling. As Brian mentioned, well, maybe this is not so high variability, but when you have a strong scaling, what happens is that you increase the number of processes, the number of resources that are solving the problem, so the amount of work per process is reduced, while typically the communications either stay constant or are being increased because you have more neighborhoods. So being so perfect scaling with a strong scaling is harder, okay? But what about if I tell you this is an unbalanced simulation? Well, if I have problems of unbalance, maybe it's not so easy to have this perfect scaling. So knowing my problem, I may have more questions saying, well, I'm happy to be perfect scaling, but maybe there is some reason for that, okay? And what thing that is important, always you look at a speed up plot is, what about the reference case? So maybe it's a perfect scaling because the original was already quite bad, okay? So my message here is, please try to consider when you are measuring the speed up, only the speed up, try to consider what is the problem you are solving, if it makes sense to have that speed up or not, okay, whenever it's good. So for that reason, many years ago at BC, we developed a efficiency model that has been extended and being deeply used in the scope of POP Center of Excellence. This model, as Brian said, is not modeling just the application, it's modeling the application run. So we have the application and the input, the software stack, and the hardware underneath, okay? So it's a combination of all these components. So it means if I move my application to a different platform or to a different software stack, I may have different values, okay? And the idea of this model is to measure the efficiency based on the allocation of that run of the application. And I can consider the allocation of a run is basically during a time interval, okay, that here I plot on this axis. I have a given amount of resources, okay? Let's name them CPUs for simplicity. So that's my allocation, this kind of rectangle, okay? And in that rectangle, if I want to say what is my parallel run, because this is more than one line, so this is a parallel run efficiency, is the percentage of time I'm doing useful work, okay? And what is for me useful is the time I spend doing the computations of my applications. I consider whenever I am in a parallel runtime, that's the overhead I have to pay to run in parallel, okay? It may be very efficient MPI, but it's not what I want to do to be inside MPI, okay? So keeping in this simple case for MPI, what are the reasons to be inside the parallel runtime of MPI? That will be the potential bottlenecks when I am in this overhead time, okay? The first and maybe the most, the one that is really expected is to be transferring data, okay? You go to MPI because you want to communicate with someone else. So that transfer of data is one of the reasons to be inside the parallel runtime, but it's not the only one. We also, as Brian has shown, we may have load imbalance. And what does it mean? It means if you have a couple of processes and one of them finalized earlier the computation, then in entering MPI, and it has to wait for the partner, okay? So this generates a time in MPI that is not really transferring data, is basically waiting someone else, okay? So that is also a bottleneck that you spend in MPI. And the last reason, maybe that is not so easy to understand initially, but I have tried to include some examples also to make it easy to understand, that you can be in the parallel runtime, are temporal imbalances or serializations. That basically one simple example is that consider we are a team that we are working to solve a problem, and on each of the iteration, one of us has to do some extra computation, okay? Some kind of summarization of data. What happens is that if this is done on each of the iterations, basically a long time, this is balanced. And when we finalize, we have all of us have been working the same amount of time. But a long time on each iteration, all others have been waiting to the last one that was doing this extra computation, okay? So that's, again, is time in MPI that will be a temporal imbalance. A serialization is kind of a chain of dependencies, okay? So assume we have to do a computation, but I cannot do that until my previous process sends me some data. And the same happens with the next one. This chain of dependencies, this serialization, is causing that all of us work the same amount of time, but all of us are waiting to the previous and are making to the next one to wait, okay? So those are the main reasons that you have seen these concepts on the tables presented by Brian that are the components of the parallel efficiency that measure the efficiency of a given run on a given resource, okay? But we have also the other dimension that is the scaling, okay? What happens when I scale, when I increase the number of resources, but also when I change my input file, okay? Well, in this scenario, we have the first thing is that the scaling of the parallel efficiency itself and its components, okay? It's increasing or is reducing the percentage of time in the useful when I change the number of cores, okay? It seems one has problems with the slide, but seems some other is working. So please let me know if there is some issue with the slides. So basically, the first scaling efficiency will be the scaling of the parallel efficiency and the components. But also, as Brian has shown, is the computation, the scaling of the computations. For instance, if there is code replications, that will mean there is an increase of instructions, okay, when I go to larger scale. And that will for sure penalize the execution. But also the IPC, the speed that execution, that instructions are being executed, okay? And in that scenario, you can consider, for instance, if it's a strong scaling or weak scaling, initially in a strong scaling, it's easier that the IPC is improved because basically on a given on some scales, if you reduce the amount of work, the amount of data you work as a process, that may take more benefit of the memory and the caches, and that may improve the IPC. We have seen that in many cases, and you will see that in some tables we present today. What happens in weak scaling is each process keeps the same amount of work. So maybe it's easier to keep with the same IPC, but maybe it's penalized. You also have to consider how many guys are sharing the node with you, because depending on the load of the node and depending on the load of the socket, you may have sharing resources that affect to your IPC. So if your application is pure OpenMP and you do a scaling test, what happens? Well, as of today that we have this multi-core architecture, what happens is that when you increase the number of processes, they also reduce some resources. They reduce basically level 3 cache and they reduce the bandwidth to memory. And in that sense, it may happen that the IPC is reduced. So even you do a good work, redistributing the work, you get a penalty because you are having a higher load, okay? So all these factors we have been seeing can be expressed as a percentage or can be expressed as a positive number from 0 to higher, typically from 0 to 1. but sometimes it may be bigger than 1, expressing that is more than 100%, okay? And always for all these metrics, the higher the better, okay? So let's go back to the example of my first slide. And now I tell you, this plot is for ggpop. ggpop is a proxy app for the ocean, for modeling the ocean, and it's doing a strong scaling. So that's the reason I said, well, the ocean, if you split the Earth in chunks, the ocean will not be balanced, will not be so easily balanced, okay? And it's doing a strong scaling. So let's look at those metrics we have seen to explain why we have this perfect scaling. Let's start with the para efficiency, that is this dark blue line. And we can see that in fact, even for the small core count, it was already not so high. It was around 75%. This means I spent 1/4 of my time inside MPI. Well, this starts to be high. And this is becoming worse and worse with the scale, okay? And if we look at the components, we can understand why I am increasing my time inside MPI. The main reason is the one that is closer to the parallel efficiency, that is load balance, the pink line, okay? And we can see that it was the main reason for the smaller core count, but when increasing, even it's able to improve a little bit load balance. And if you try to understand that, you consider, if you do a strong scaling, you are doing chunks on the Earth to do the simulation of the ocean, okay? And what happens if you have more guys solving this problem? The chunks you have to work with become smaller, okay? And maybe it's easier to have a better balance because of the size of the chunks, okay? Then we see that transfer of data as expected in a strong scaling case. Initially is good, the balance between computations and communication is well set up. But when we start increasing the scale, it becomes more and more important, okay? Because basically the ratio between computations and communications becomes harder, okay? And you have to transfer more data and you are computing less time, okay? So proportionally, your transfer time increases. But in this code, we are lucky and we don't have a serialization that on those days, this is the original model developed at BSc that was named micro load balance, okay? That was the blue line. So that's the last thing we have to consider. So basically analyzing the para efficiency, I understand that my efficiency is low even for the lower core count. The main problem is load balance as expected, but I also have problems of the transfer on larger scales. But as I have seen, I keep with a even little bit higher than perfect scaling. And as the previous slide mentioned, the reason is on the computation scaling. So let's look at the computation component, okay? So the green line is the efficiency, the global efficiency. We have the para efficiency as the blue line as before, but now we have also the instructions efficiency and the IPC efficiency. Instructions efficiency, that is the yellow line, is almost flat, saying there is no relevant code replication. There is not, I can ignore that dimension. I have no problem on that dimension. But what happens with the IPC? You can see if you imagine a mirror in the around 1, the line of 1, you can see that whenever I lost something in the para efficiency, the IPC is able to compensate that, okay? So the reason why I'm getting the perfect scaling is not because I'm running perfectly in parallel. It's because my IPC is being improved because, as I mentioned, with a strong scaling, my volume of data is being reduced, so I get faster on the computations because I get more memory. I fit better in the caches, okay? And then I improve my IPC. So for that reason, I'm getting this perfect scaling. So knowing that, now I can understand, depending on the values of the IPC, I was quite lucky in this range and I cannot go further. But if the IPC is still low, I may increase a little bit the scale and I still be performant, okay? And in fact, this the first example, I have been using that example for many, many years. But in fact, in POP studies, I have seen in many cases, this is the real situation. In many cases, applications have not so perfect, but have not so bad scaling because the IPC is saving this execution, okay? So I think one thing is important, if you work with some code, if you do this kind of analysis, and during this training, we will show you how to do this kind of analysis. You can do this kind of analysis by yourself, or you can get the support from POP to do this kind of analysis. You can check if IPC is helping you to have a better scaling or not, or you are really having a good parallel efficiency of your run. So based on this model developed at BSc many years ago, that was the starting point for the POP's efficiency metrics. And in those days when POP started, there was one additional component that was not on the old days, that is the frequency scaling. So as you can see, this is a hierarchy of multiplicative numbers. So every leaf multiplies to get the communication efficiency is the one I didn't mention, okay? And basically that was also on the slides of Brian, is if I multiply the serialization and transfer, I get what is named the communication efficiency. If I go from top to bottom, my parallel efficiency is the time I spend computing. That can be distributed in two factors: global load balance at the full execution level, and communication efficiency, that is the time inside MPI, if we keep on the MPI word till now, the time I spend in MPI that is not caused by global load balance, okay? And that includes both these serializations, these temporal imbalances, and the transfer of data, okay? And then we extended the computation efficiency, that is the product of these three numbers. We have the scaling of the IPC, the scaling of the instructions, but also the frequency scaling. And that's important, again, if you do one node analysis, or if you do OpenMP scaling, because basically, as of today, I think all the machines, when you, depending on the load of the machine, the scale, the frequency has some variability, okay? So you fully load the node, it has some scaling, some frequency, sorry. If you reduce the load, the frequency increases, okay? It's able to increase the frequency. And in that sense, this is a factor that will also affect the duration of your computations. It's not only that you are sharing resources, it's that we are more in the node, so I get a lower speed, okay? So let's see some examples. And how do I look at the efficiency model tables? Basically, three recommendations. The first one, I consider kind of a flag 0.8. So if it's above 0.8, I may consider it's good, okay? I have to analyze in this table 2 dimensions. The first one is the execution, and typically I focus on the lower core count and the scaling. Okay, so what is the lower values in the first column? That is the lower core count. And what are the values that has suffering a higher drop when increasing the scale, okay? And basically, we will use in POP, we will use those identified values to drive the analysis in the POP methodology. So let's start with this table, okay? Those are real cases from POP studies, okay? And the first thing I look at is the parallel efficiency of the lower core count is already low, okay? Is close to 60%, okay? It's low, it's really low. If I look, what is the reason for that is load balance. It's clearly in the coloring, you already see it, okay? Is the value that is lower in the small core count, but it's also the one that has the bigger drop when scaling. Well, it's not the bigger drop, but it was a big drop when scaling, okay? We also have a big drop on instructions for the higher core count, okay? And in that case, we can try to get some insight from the code, but we can also check with the owner of the code, with the user of the POP service to find some hints to explain why up to 96, the scaling of instructions was good, but then it dropped when we go to 192, okay? Another case, this table, again, I look at the first column and load balance is the lower value, but this is still high. It's close to 90s. 90s are good, okay? If I feel safe if I am in the 90s. If I go to the 80s, I start to have concerns. If I go lower than that, then I consider I have an issue, okay? I have to solve. So then the lower drop, the biggest drop, sorry, is the serialization efficiency, okay? Change of dependencies. So I have to change my code to eliminate this kind of imbalances or change of dependencies. Okay, and the other factors that also limiting the scalability are data transfer, as you can see, and instructions scalability. So reading these tables is easy. You look at the first column, you see the lower values in the first column, and then you look at the range of values moving around, and you have to check which ones get worse. Okay, last example. Here, everything is close to green, so things are perfect. Okay, for the small core count, the efficiency is almost perfect. Okay, and there is only a smooth degradation of the power efficiency, and all the components have a similar contribution. Okay, so in that case, there is not a guilty guy. There is no one I can blame. There is many guys that have small issues. So maybe I have to go to a higher scale to push higher on this situation to see which one is the one that suffers first. Okay, but we see that the improvement on the IPC is the one that is compensating the loss that is caused by the real problem of this application, that is code replication. Okay, so the IPC is compensating, and you can check the computation scalability is very close to 100 for all the core counts. But if the IPC was not able to improve so much, then the increase of instructions have been suffering the performance. Okay, so before taking care of the power efficiency, I should check where this code replication is happening to try to fix it. So to benefit from the IPC, not to compensate the instruction scalability, so I can go higher on the scale. Okay. Again, as I said before, you have to check the value of the IPC to see if you can go bigger, but for sure it will not grow forever. So there will be some value where you will kill by the higher number of instructions. So one of the things, as Brian mentioned, that we do in the POP studies is select the focus of analysis. And this is very important. In this slide, I'm trying to explain you why it's such important with a very, very simple example. And the other thing that is important for those numbers I have been presented on the previous slide is to understand why those things happen. Okay, it's not saying just, okay, I have a problem of transfer. Okay, but where or why? Okay, giving reply to those numbers. Okay, so this is an example, a very, very simple example from an execution I get on another VI-HPS training. So when we do this hands-on and people use the tools with their own codes, there was one of the attendees that has these metrics for the execution. It has the power efficiency was almost perfect. Communication was the parameter that was closer. So you can see load balance will be close, very, very close to 100%. And in those studies, those were done with the trace file. And as you will learn during this training, with the original trace file, I only get in Paraver power efficiency, communication efficiency, and load balance. I do not split between serialization and transfer, okay? So for that reason, in this slide, I do not split between serialization and transfer, okay? So I have this number. If I use, as I did with the scaling plot, if I just say this is good, I have no problems, I can move to another tool, okay? Then you are lost. Because if you see the timeline, you see, in fact, this is the first time you see a Paraver timeline, but basically it's kind of the same square we have seen before. In this dimension, we have time. In this dimension, we have our resources, okay? We have 32 MPI ranks on this small square rectangle, okay? And in this window, what I have is activating the flags. So there is activity where I see some green, okay? And it's basically saying I have some large initialization, okay? And then here starts the MPI init. Here there is the MPI finalize, okay? And there is only activity in this small region, okay? And the reason for this large gap, okay, is initialization. It's reading data, initialization structures, these kind of things, okay? And what happens, and that's somehow not so infrequent on these trainings, is that people start with a very small input case, okay? Well, depending on the small input case, if you blindly do the analysis, then you may get wrong conclusions. So this small input case, the initialization was really dominating the execution. As the initialization do not use MPI, we consider this is useful in our model, okay? So for that reason, the efficiencies are so high. So if I just focus on the region where there is MPI activity from the MPI init to the MPI finalize, and I compute the metrics, well, now they go down to close to 80, okay? So there is a significant drop because this gap, this computing phase was dominating the execution, okay? So you have to consider what the efficiencies are telling you. Parallel efficiency is the time you spend computing. And it's not saying just the time you spend computing during nice things, okay? So you have to take care you select a focus of analysis that is relevant, okay? And you may still wonder if this is a relevant focus of analysis because you see a small gap here, okay? Now that I have zoomed, this percentage of time becomes quite important, okay? So basically, I need to understand what is the right focus of analysis, but I can still zoom bigger to try to understand the pattern. This is very repetitive. I zoom and zoom and zoom until I see the structure of my application, okay? And for today, you have to trust me. Those are the MPI calls in Paraver. And this is a all reduce. This is a send reg. This brown is a send reg. And this is a barrier. So basically, my code is doing a computation. Then it's doing a send reg phase. And this is doing a barrier to wait for the send regs to finalize. And that way, they do another computation. And they do the all reduce. Okay. So one thing you have to learn when you have visual tools like Vampire or Paraver, when you see these kind of shapes, this kind of step triangle, okay, take care. This is saying there is some serialization. This is not going to scale because basically you have to consider this is my triangle having 32 processes. Assume now I have 1K processes. I have 4,000 processes. This triangle is going to be bigger and bigger, okay? Because basically this triangle is telling me the higher my rank ID is, the higher time I spend in the same reg, okay? And when you see that, this is a problem that you have to solve. This is a very inefficient pattern, okay? And in fact, in this code, this is the main computation phase, okay? And partially, the computation is small because it was a small input case, but the benefit of this small case is that allowed to highlight this problem of the communication pattern. If I look at the point-to-point lines, well, sorry, here the efficiencies are really, really bad, are in the 30s, okay? Saying that I spend most of the time inside MPI, as I have seen here, okay? And if I draw the communication lines that in Paraver are seen in yellow lines, you can see basically all of them at the same time try to send to the first rank, okay? And this is something quite frequent pattern in application is that I have to communicate to a given set of processes, okay? And I start with a lower rank and increase the rank. And then what happens? All of the people that have to talk with rank 0 becomes a bottleneck depending on the primitives that are being used, and you have to wait for rank 0, okay? So in that case, this example allowed the user to identify a problem on the pattern, okay? Because everyone was talking to everyone else, okay? And he was able to fix that issue, okay? But in fact, at other level, at other scale, these problems also happen on the applications, okay? So what will be the right focus of analysis? This will not be the right focus of analysis because maybe depending on what it's doing here and is doing here, but some number of iterations may be the right focus of analysis, okay? And the analysis will tell you, you have a problem on your communication pattern. You have to change the way you are communicating. You are communicating with too many people. You have to consider if this is really relevant or not. And you have to increase your computation. You have to increase your input case because this is too small, okay? So next slides, I'm going to show you some examples. If my table shape, for instance, I have a problem of load balance, okay? Some examples of diagnosis by this load balance efficiency problem, okay? Digging down on why I have problems of load balance. And in this slide, I present two examples. The first one is with OpenMP, and the second one is with MPI. In the first one with OpenMP, I'm showing you a profile of the time spent computing for each of the threads, okay? And I see that when I have two threads, there is unbalance already, 79%, seems to be kind of the boundary. But in fact, there is one guy that is computing close to 100, while the other is around 60% of the time, okay? So it's already a problem. I do not see so much because there are only two guys, okay? And what happens when I increase to 8 processes, okay? The first guy keeps working close to 100%, while others are on the 25%, okay? 26%. And this is clear, is because there are reasons that are not parallelized with OpenMP. And for that reason, the master thread has longer executions and the slave threads only have the parallel loops execution. And the other time they are idling or they are inside barriers or so on, okay? So then the solution is clear for this case. It's very simple. You have to parallelize for the regions of OpenMP because the current parallelization of OpenMP do not cover enough space of the computations, okay? The second example is a little bit more complex in MPI. And here I show you a couple of histograms of Paraver. Tomorrow I will show you, and we will show you more detail how to read those pictures. As of today, please focus on the dark blue lines, okay? And this is a Paraver gradient that goes from light green to dark blue. The darker, the higher, okay? It's a way for us to express a continuous metric. And what I see here is a histogram of the duration of my computed phases. And what I see, darker means in this case is more important. So that's the reason I suggest you to focus on the darker points. Is kind of a structure imbalance. I have two guys taking less time, one guy taking more time, and this shape is along the execution. If I load the histogram for the instructions, okay, I have a very similar pattern. Is a structural imbalance that is correlated with highly correlated with the number of instructions, okay? And this is how do I read that? What will be? So basically, this is telling me I have a structured instructions imbalance, okay? That this basically the amount of instructions is what is creating this imbalance, okay? That as you can see is much more important, less important than in this case, that was quite drastic, okay? But as being a structure, maybe it's easy to solve, okay? I have to check my mesh, I have to check my word distribution, I have to decide maybe if I have to group this data in the 3 first guides, just make it in a coarse level of computation, or I can redistribute the data in a different way to avoid this imbalance, okay? So I may use profiles to understand the distribution between processes, but what I typically do when I see there is load balance problems is I check if this imbalance is correlated with instructions, with IPC, or what is the thing that explains that imbalance, because this is the way I have the answer on how to fix it. Let's look at transfer efficiency, okay? And these are views of the MPI calls, and these are the metrics for this example. In this slide, I just have one example that say that there is a problem of load balance and there is a problem of transfer, and serialization is nothing to take care, okay? In the case of BSC tools, what we do is we use DMMS, that was already mentioned, to simulate an ideal network. Ideal network is instantaneous communication. So that way, if I do this simulation, I eliminate any time that is transferring data, okay? Then I compare the real run with the ideal network, and that way I can see where is the transfer of data, okay? And if I compare these two views, the first thing I see is that this reddish that correspond to the point-to-point calls almost reduces, it almost disappears, it's reduced a lot during the ideal simulation. While the ping that is at all reduced, in fact, increases a bit because here there was less variability and here there are more guys that finalize sooner, okay? So what this is telling me, the time I spent on the point-to-points is transferring data, while the time I spend on the all reduce is load balance, okay? So now, depends what I want to fix, I may go to one way or the other, okay? But maybe the easiest one can be, if I do overlapping of computation and communications, this time inside the point-to-point will be absorbed by the computation that I'm doing at the same time. And that way, I maybe easily, and this is quoted because it depends on the complexity of the code, this time in MPI will disappear, okay? So I will kind of mimic this time if I do this overlapping of computations and communications, okay? Again, the load balance will depend if this is corrected to instructions or not, and I have to reconsider if there is some way to better balance the amount of work between the different MPI ranks. Serialization, okay? And in that case, I'm showing you just one example, but I show you both the first version of this code and an improved version that I have already analyzed within POP, okay? And is to show you this kind of patterns I have mentioned before when you see this kind of step triangles, okay? And you have to consider when you see these kind of things, okay? Take care. That's something that is not going to scale. This is also happening inside these regions here. So this is happening many times in this code, the original version. I show you here the MPI calls and also a metric that we name useful duration. You will learn more about it tomorrow, but it's basically the duration of the computing phases. So basically, something that is colored here means I am computing, and the color expresses the length of this computation, okay? And there are some of these serializations very basic, easy to see, like this one here, this one here, and this one here. And you can see, for instance, this one is the case I explained you before. Is because I'm waiting to start. It's not that I am computing more time than others and then it compensates. It's basically that I am delaying my computation until the previous guys have finalized, okay? So that was detected by the first analysis of the code, and the user understood the problem and was able to fix it. In fact, they changed, this is a point-to-point communication we told, and they changed this communication by a global collective. And with that global collective, all of them finalized at the same time. And you can see now they are perfectly vertical lines, okay? And this improvement of the code that you cannot so easily see here reduced this region duration at 22% of the time, okay? So they did that in some months. It was not a big effort to do it, okay? But they were able to solve it. So once you understand what is your problem, okay, you can find a way to fix it. So the idea of the efficiency metrics is that the numbers highlight where you have to look at, then you look where they are telling you to look, and then you, in many cases, you are able to find a way to fix it. I think this is the last example, is about the IPC scaling. What happens if my diagnosis saying I have problems of IPC scaling? First thing that this is illustrated in the first example is where is the IPC scaling problem? In that case, you can see the coloring, as I said before, the coloring express the weight. In this case, express the IPC, the higher the better, okay? And you can see that when I go to higher number of OpenMP threads, most of the colors reduced are clear, are lighter, okay? This means that this IPC is affected to all the computations, okay? And in that case, it's not so easy to solve because, in fact, this is what I mentioned. This is OpenMP, this is inside a node, okay? And the problem is that when I increase the number of threads, they get less resources, they get even a lower frequency, despite here the frequency is not illustrated, okay? But basically this is penalizing you on your computations, okay? You have to take care how you compute your application in OpenMP because all these factors are against you. They are not going to help you to have a good scaling. Maybe it's easier this second case with this MPI. And this plot corresponds to the tracking tool we will see on Friday, okay? But as of today, the only thing you have to understand, I have my space of IPC and instructions, and I have here my computing regions, and the arrows tell the movement on this space when I increase the number of processes, okay? So let's start with the good guy, that is the light green, okay? What happens is that this is a strong scaling, so I increase the number of processes, and this is going down. It's reducing the number of instructions, good. And the IPC is almost the same value, okay? Almost no modification. It's close to a very vertical line, okay? What happens with these three other guys is a problem, because basically they move to the right. So they reduce the amount of instructions, that's good, but they move to the left, meaning they reduce the IPC. For instance, this guy had an IPC close to 2.3, 2.4, and when I increase the number of processes, reduces to 1.5, okay? So these three guys, I need to check what kind of computation are doing. I need to check again the load of the socket and the node to understand if what's the reason they are reducing, because there is one guy that is not reducing, okay? Let's see what's the difference between these guys and this one to understand why this is not being penalized, why these others are being penalized. But the bad guys that was not the initial IPC problem are here, these four guys, okay? You can see these four regions, I increase the number of resources, but they in a strong scaling, they keep on the same point, okay? What does it mean? This means they are doing code replication. Those regions, even it's a part of an MPI program, they are not parallelized. Every MPI rank is doing the full computation, okay? So those are four guys that I discovered on my IPC analysis are the ones that are doing code replication and are the ones that are going to kill my performance. Because when I increase the number of cores, they will keep on the same point. They will still represent the same amount of time, that as a proportion of my execution time, they will become more and more relevant. So if there is any questions, if there is no question, I keep going, okay? I think I only have 20 minutes, something like that, or 15 minutes to finalize. No, 9:30, yeah. 15 minutes, that should be enough, I hope, to finalize on time. So that previous slides basically was for one level of parallelization that can be applied to either MPI or OpenMP, okay? Now, during the POP live, we need to extend to cover hybrid executions, okay? And I'm going to present the extension we have done to cover hybrid executions. So the first thing, you can do for an hybrid code is you can apply directly the same approach we have been doing for pure MPI or pure OpenMP codes. That is, I consider any time on any of the parallel runtimes is the overhead, okay? And only useful time are the computations. And with that thing, I can, with these same formulas, I can compute the hybrid parallel efficiency, the hybrid communication efficiency, and the hybrid load balance efficiency, okay? And those are good because those allow me to say if my problem is on the communications or is on the load balance. But the problem is that it's limited what I can do if I do not understand easily if they are caused by MPI or by OpenMP, for instance, okay? I need to distinguish between the programming models in order to be able to do it. So what we want to obtain is something like that. I'm able to split between the concept, but I'm able to split also between the different programming models. In these examples, it's MPI and OpenMP. So if we consider that the concept of communication efficiency and global load balance can be mapped to any parallel programming paradigm, okay? And some people, maybe it's not so easy to follow that, but in fact, you have to consider is a team of resources working to solve the same problem. So you can say there may be load imbalances between them, and any other time I idling and it's not caused by load balance, I blame that is label communication efficiency, okay? So with that approach, I can map to any programming model, okay? So then I can do the same. Once I'm able to compute the pi efficiency inside MPI, I can split between load balance and communications, and I can do the same thing for OpenMP. And then what happens is I can consider that the metrics at hybrid level are collapsing the contributions for the two programming models. So this is not a tree. This is not longer a tree. I have two trees together in the same set. Okay, I can dig down to the low level through the concepts of the efficiencies, or I can go through the programming models. Okay. Let's see that it may look complex, it's not so much. Let's see that with a very simple example. This is MPI plus OpenMP, and basically I have two phases. The first one is not parallelized with OpenMP, and the second one is parallelized with OpenMP, okay? So in the first computation, threads are idling. In the second phase, all of us are working. If I compute the metrics at hybrid level, it tells me your problem is load balance. That's clear, okay? Because there is imbalance. This guy is computing most of the time. This guy is computing just less than half of it, okay? If I compute the metrics at the level of MPI, how do I compute the metrics at the level of API? I basically consider, from the point of view of MPI, any time inside OpenMP is as useful as the computation because it's not their fault, okay? So with that approach, I can compute the metrics at the level of MPI. And it tells me at the level of MPI, there is no imbalance. It's perfect, okay? Then the way I solve this, I complete this analysis, I consider whatever is not caused by MPI is caused by OpenMP. And in that sense, I can compute as a ratio, all these numbers multiply. So as a ratio between these numbers and these numbers, I can obtain the efficiencies of the OpenMP. And they point the problem is on OpenMP, okay? So there is some flavors that I may introduce, I think on Friday, on some restrictions, how to interpret this MPI point of view, depending on the kind of parallelization, okay? And currently, some alternatives are already programmed in the tools that we will distribute, but some of them still are on the way, but they can be computed by hand. But the same thing, if you see what I have seen there, there is nothing specific about OpenMP. You can substitute that OpenMP by CUDA. So from the MPI point of view, CUDA runtime is as useful as computation, and whatever cannot be blamed to MPI can be blamed to CUDA, and that way I can use that. And in fact, it was the example I used to develop that model was an example with MPI plus CUDA, okay? So in that example, this is something I will explain later on the next presentation. But in that example, if I look at the components of the programming models, I can analyze the scaling of this application that is MPI plus CUDA. And I can see that the MPI component is important, but the CUDA component is more important, okay? The MPI component is degrading with the scale. That's the more important thing, but initially it's small, while the CUDA component is large for all the setups, okay? So I can distinguish the contribution of the two programming models to this scenario, okay? And in fact, as of today, that was the initial model we developed for MPI plus CUDA. As of today, we are reconsidering what to do with MPI plus CUDA because there are some codes that efficiently use the GPUs, but intentionally do not use the CPUs because they are lower, and they are going to delay the full execution. So they prefer not to concentrate any work, not to dedicate any work. Or some others want to dedicate them to do I/O, okay? But basically they want the CPUs to be ready waiting for the GPUs to request some work, okay? To be ready to do some more extra work, okay? So in that scenarios, what we are currently doing, for instance, what I have been doing on the last cases, I have to study with MPI plus CUDA inside POP3. Sorry, I have set up at global level, the metrics for all the resources, okay? So this is global power efficiency and global load balance are considering all the resources, and I clearly see my efficiencies globally are bad, but they are highly correlated with the global load balance. And the reason this close to 50% is because I am 50% of my resources. In that scenario, I have 1 MPI rank per CUDA device, is that 50% of my resources are just being intentionally not used, okay? And that's the reason they are 50%. And then all the metrics underneath, they are not focusing on the CPUs because it's not relevant how much time they spend in MPI or they spend in CUDA, as far as they do not delay the GPUs. So all the metrics underneath, they are only focusing on the GPUs. And for that sense, they do not split between programming models. So we have the GPU's global efficiency that we see is quite good, okay? At the larger core count is still close to 80, okay? And we see that the power efficiency has some degradation, that the degradation is correlated with communications, okay? And the computation also suffering a little bit, but just a little bit of degradation, okay? So we focus the analysis on these metrics as a different way. We're trying to make that on the tools ready for compare the different scenarios, but that's possible to do with the traces and with the profiles, both with Scalasca and Paraver. Last slide, how to compute the metrics. If you work with Extrae Paraver data, basically there is one Python module that is BSc basic analysis that can compute those metrics. It has some restrictions that I will tell you on Friday, okay? But it works for sure for pure MPI. For some hybrids, it depends. We are doing some changes, okay? But for pure MPI or OpenMP or CUDA, perfectly works. And also with Scorpy traces, since Cube version 4.5, it's ready. Depending on the version, you have more or less metrics available, okay? But in fact, this train will show you how to use them, how to use those tools to compute the metrics on your own. And if there is no question, I'm done. If there is any question, I will be quite happy to answer.
So I think that's been a good 10 minutes. I hope that everyone had a chance to have a bit of a break, and we'll try and keep on time to finish at midday and have an hour's break for lunch. So let me put in my microphone and see if that helps. Okay, now the microphone's on. I hope that that's a little bit clearer. So yeah, so for this next session, taking it up to lunch, Judith and I will split the time and we'll show some of the assessments that we have looked at mostly over the last year, but over earlier times as well, where we've looked at a number of applications. I'll cover the ones from the JSC tools, and then we'll return to Judith and continue with the Barcelona tools. So I should have introduced at the beginning, I'm Brian Wiley from Jülich Supercomputing Centre. Scalasca and associated tools are developed by us here, or by my colleagues here in Jülich. Scalasca is a collection of trace-based performance analysis tools. It's been developed for very large-scale applications and analyzing their performance, going into some detail to figure out where the inefficiencies are, where there are wait states, where there are things on the critical path that are limiting performance, what are the delays that are causing the wait states. The analysis is primarily limited to MPI and OpenMP. Can handle hybrid cases as well, but Scalasca trace analysis doesn't handle GPUs or anything happening on the GPU itself. So that's one of the limitations that we'll see when we return to use the tool on Friday. But for CPU applications, MPI, OpenMP, you can use the Scalasca trace analysis as well. Scalasca uses Scorpy as its measurement and instrumentation and measurement infrastructure. That's what we will use to instrument the application, so that they have our measurement libraries that incorporated and are able to collect things as the application is running. We'll put the information into event traces in one form or in an aggregated form in call path profiles. And the two different formats are quite different. They give you different information, but you'll see those in the course of the tomorrow and the next day. Scorpy is much more general than Scalasca. It supports a number of additional parallel programming paradigms. So there is support for various forms of GPU accelerator programming, including COCOS, OpenACC, as well as CUDA and HIP. And we'll see that on Friday in particular, but you're welcome to focus on the MPI and OpenMP part, which we'll focus on tomorrow. Again, it's an open source project. The way in which the tools work together is that the source code of the application gets instrumented using the Scorpy instrumenter. It's also linking in some additional measurement libraries to produce an instrumented executable. And then when the application runs, and this is supposed to represent a number of processes or a number of threads, they each have the measurement libraries linked in, as well as the instrumentation that's been incorporated. And then over the course of execution, they are capturing the measurements from the events that have been instrumented, that have been identified in the execution. These are timestamped, they have hardware counters associated with them. And then in the basic form, the initial form, at the end of execution, that is aggregated together, and you'll end up with a profile summary report. Information will be contained about every process and thread of the execution, or GPUs if they're also incorporated. And then there's a tool called Cube, which we'll see, which is our visualizer, explorer, browser for presenting and manipulating the various information that's been collected. So in that, you'll see a number of different metrics which identify or can characterize the importance of different performance problems. You can see where they occur in the program, which call paths or functions are affected, and then which processes and threads or GPUs those lie on. That's very summarized aggregate information in a profile form. We can take that information and use that to optimize the measurement configuration. The optimized measurement configuration can be used to reduce parts of the measurement which are not so interesting, but maybe causing a significant overhead. Or we can add additional information in there at this point. So we can add additional hardware counters or other metrics so that we get more information about the parts that we're really interested in. Build up another summary report, a more detailed one, a more comprehensive one, and then view that in the same way as before. The other thing that this iterative cycle allows us to do is that we can have a good idea of what to expect when we would enable the tracing. So when we enable tracing, we don't have to re-instrument the application. The measurement library already is there, but through an environment variable, we would say collect event traces and then write those event traces to file at the end of execution. The Scalasca trace analyzer would be started, which reads in those traces. It goes through those traces in parallel, replays them, identifies where there are wait states, and then at the end produces a wait state report. And that wait state report is an augmented report, very similar in format to the initial profile summary report, and can be explored and examined in exactly the same way with the Cube tool as before. So I hope this picture kind of summarizes at a very high level how the different tools of the Scalasca toolset fit together for trace analysis, for instrumentation measurement, and for the exploration of the results as well. What isn't shown here, and we'll have a chance to see it later in the week, is the Vampire tool, which allows us to look at the traces in more detail. And that's very similar to the Paraver traces and the Paraver browser that Judith was showing a little bit earlier. Cube I already mentioned, that's the GUI that we would present, and where most of the pictures that you'll see come from, because that's the most visual part. This is one example of a measurement where an application has been run on a pretty large number of processes. Here we see the MPI ranks, in this case sorted. So there's something like 13,000 MPI ranks in this case. This is the distribution of the values of the times for them. So we can see that there's quite a big distribution between 500 seconds and 1500 seconds for the specific function that has been selected and for the specific metric. This is the computation time metric that has been selected for part of the computation. Lots of other metrics, which are, I can't see on the screenshot here, but you can select, and then the displays to the right update dynamically. You can select a different call path. You can rearrange things and sort things in different ways to have a lot of power to explore the large amount of data that has been collected here. One thing to note is that some of these metrics are only available from the trace analysis part, which comes from Scalasca. Some of the metrics are optional ones for hardware counters that are configurable when they're required. But things like MPI and bytes transferred for MPI or critical path metrics, those you get for all of the simulations. But one of the challenges is that there's a lot of information, a lot of metrics, a lot of places where problems could be occurring. And as Judith was mentioning, it's good to start off with a much higher perspective where by selecting the part of the execution that you're interested in this case, the run simulation part, we can look at these efficiency metrics, the load balance, the parallel execution, the communication efficiency, and get at a glance an insight into the fact that communication here is very good. There's nothing to worry about. Load balance is only 50%, so that's a big concern. And then the product of load balance and communication efficiency is parallel efficiency. So that is explained entirely by the poor load balance. So that advisor, that high-level characterization is a good starting point, which can then lead you to identifying or investigating why does this execution have such a poor load balance? And we'll see an example of that in one of the cases that I'll come to. Scalasca has been developed over more than 10, 15 years now, I think, from some predecessor tools. It's been applied to a lot of large-scale application executions on our Blue Gene system that we had in Jülich for a few years with a million or almost 2 million threads, or on K-Computer in Japan with 600,000 or so threads. So it's been widely applicable to very large-scale executions. And of course, now it's being more applied to GPU executions. So I'm going to take the time that's available here to focus on a couple of codes, or one code that's in a couple of variants. We've worked with these codes in different forms over the years, and I won't go through all of the steps. We just pick out a few examples and focus on those. So the first one is a code called EMLB, which is a lattice-Boltzmann simulation code of blood flow in the human arterial system. It's from the Competence Centre of Excellence, C++ code parallelized with MPI in its initial form. And the diagram here is showing the network of arteries within the human brain. It's a very complex geometry, and that is, I mean, it's not the full network, it's just part of the network, but it's the main arteries in the brain. But it's a complex geometry, so the simulation is quite challenging. And as you can imagine, load balance of the computation within it could also be significantly challenging. This was run on the SuperMOOC NG system, which is at LRZ in Germany. And we were able to get access and run this code. It scaled, it ran on the full system up to over 300,000 processes. So on the left, we have the strong scaling execution times, which we see are decreasing nicely from 16,000 seconds down to 83 sections on what is almost the full machine. Focusing on the green part, which is the simulation, because the initialization, reading in and distributing the data has very clear scaling problems, but you do that once and then you run lots of simulation time steps. But for this measurement, we just did a few time steps. So we had correspondingly dominant initialization cost. So the simulation scales reasonably well up until it gets to about 100,000 processes. And when we look at the speed up, we also see that tailing off, that it drops below our 80% level, again, about 100,000 processes. It's still scaling, it's still giving us a 190-fold speed up compared with the smallest scale, but we can learn why we're not getting the perfect scaling that we would hope for. This was the table that I showed you briefly in the introduction. At the relatively small scales, or if we look at the smallest configuration, which was able to run this large data set, which was 24 nodes, 1,152 processes, efficiency is pretty good. Communication is extremely good. But there is also, even at that relatively small scale, quite a noticeable load balance inefficiency. It's only 80% here. And as we increase the scale, the load balance doesn't really get significantly worse. The communication efficiency doesn't get significantly worse. But what has happened is that the computation scaling, that's this curve here, this line of the table here, that starts degrading quite significantly at the very largest scales. And computation scaling is a factor of different things, or can be broken down into different parts. Part which is the instruction scaling, which is the instructions which are executed, and we see that that is scaling very poorly. So there are more instructions being executed, and that's explained by the need to handle the surface to interior. So as you take the computation and split it over more and more processes, over 300,000 processes here, the individual computational domains are getting very small, and they have very large, or they have relatively large neighborhoods that they're having to interact with. So that is one of the explanations for why the instruction scaling has deteriorated. What's interesting is that the IPC scaling, which is a measure of the computational efficiency, has actually started improving. And again, that can be explained by, as the computational domain gets smaller, it fits into the caches better, and then you exploit the cache efficiency of the processor. And that's why you have an efficiency here greater than 1, up to 30% greater than 1, because you've gone from more of the computation being out of cache to having a larger proportion within the cache. You also see the IPC number here as well. It's going up from something like 1.4 up to 1.9 as that computational efficiency improves. So this table gives us quite a nice picture at a glance, where we can see that at reasonable, up to about 100,000 processes, everything is scaling very well. Efficiencies are pretty good. There is a load balance issue, which is effective at all scales. That's by nature of the problem, but by nature of the geometry, and the fact that there are imbalances also coming from the need to inject particles, inject blood into the simulation and extract it from the outputs. So it's a challenging problem, and the good thing is that the load balance is not getting worse. It's not perfect, but it doesn't degrade as the computation increases. And at some point, you just run out of work for the processes to do, and if it was a larger simulation, the efficiencies would be improved then. So looking at this sort of measurement in the with our tools here, this is a few screenshots that help us understand some of the load balance efficiencies aspects that were shown here. So in this metric summary, the computation efficiency is extremely good. This is with only 13,000 processes, so it's not the largest scale. But the load balance is, in this case, very poor. We can work our way back through and find out which parts of the computation are affected. And by looking at the various computation metrics, we can figure out that it was a computation issue. And we can look at the fact that in this case, all of the processes were actually executing the same number of instructions. So the imbalance is not coming from any instruction imbalance. It was actually the metrics which are available in the Intel processor, Skylake processor in this case, for looking at stalls accessing memory. That was where the variation in time was coming from. So here is a topological diagram. It's a bit more scalable than showing everything as a tree list presentation. Again, we're looking at the coloring here from yellow to orange-red. The yellow ones are the majority. They're all pretty much the same. There's a few more orange ones here, but there is one process here that was red. So this has been rescaled to go from the lowest to the darkest color. One of them is much redder, much higher than the others, and has taken many more stalls accessing memory than all of the other processes. And when we dug down into this and investigated further, we were able to identify that this was an issue not with the application code, but it's an issue with the processor itself, or the memory that's attached to the processor was responsible for the fact that in certain cases, certain processes have a very much poorer memory access performance than all of the others. And what's interesting is that you run this code again, it'll move to some other node, You run it again, it will run to some other node. The severity varies, but you can't predict it, you can't deal with it. So the fact that you have done the application code has done a pretty good job of partitioning itself and distributing the work statically. But in this case, that static load balance has been completely blown away by the fact that you have some factor here coming from the hardware, which is affecting your performance, and you have no dynamic capability to adapt to that and resolve it. So that was the limitation of the static partitioning model of that version of the code. There was also a GPU version of the code that was a prototype that was analyzed on our local cluster here in Jülich using the Volta processor, so a previous generation of GPUs, 4 GPUs per node. It's a slightly different data set, but it's the same code essentially, again, C++ parallelized with CUDA. Here in the measurements we see the same application behavior on the CPU side, but we also see the CUDA kernels that are shown, and we see the variation of time of the different CUDA kernels across the different GPUs. In this case, it's using multiple CUDA streams, and some of them are used for different purposes. Again, there's lots of them. It's hard to get an overview in this tree structured presentation. So that's why we would use a more topological presentation here, where we can see for each process, processes in this case are the horizontal axis, and for each process there's a number of streams. Some of them are gray, which means that they don't have any data, so they don't actually execute that kernel. Some kernels are executed by them all and are pretty balanced, but some of the load imbalance is actually coming from the fact that some kernels are only executed by some GPUs. When we look at data transfers, in this case, the data transfers to and from the GPUs, we also see that is very imbalanced as well. So some of the processes a lot of the processes in the interior of a simulation have much more data being transferred. Here we're seeing the transfer time, it's not the data. So they're spending much more time waiting for those data transfers to and from the GPUs. So again, that's another origin of some imbalance in the execution. And another imbalance which was identified was in the file I/O. So as it was checkpointing, as it was running, writing its output, that execution time, the writing, of course, is not done by the GPUs, but is done by the MPI process. That also varies considerably across the process as well. And that's another factor that also factors into the overall imbalance. So lots of different aspects that come into play. Generally, it was scaling pretty well from a single node with 4 GPUs up to, what was this, 32 nodes or something, 128 GPUs. When we look at the efficiency metrics, we see that the efficiency on the single node is not great. The communication efficiency or orchestration efficiency to and from the GPU is not a good number here. It's a concern. And as you go to larger numbers of processes, then other factors come in as well, such as the overall computational load imbalance. And that has a big factor in the overall parallel efficiency of the computation as well. These efficiencies are not including the file writing, the I/O part. That's a big variable that we typically would try and avoid, and so it's not factored in here. That would make things worse as well. One way of looking at things is comparing what's happening in each configuration for what's happening on the CPU versus the GPU. So the bars on the left in this case are the CPUs, the ones on the right are the GPUs. The light green here is the GPU kernel execution, and we see that doesn't really change very much, which is what we would hope to see for strong scaling. But the overall execution time, as seen by the CPU, is increasing, and is increasing quite substantially for the largest configuration. Part of that is MPI file I/O, part of that is MPI communication, whereas things like the CUDA synchronization cost, the CUDA memory transfers CUDA memory transfers were also a factor, but perhaps not so much. And what is also, of course, relevant is that because the CPU is taking longer, that means that there's more idle time on the GPU, which is the white part of the bar here. So as it goes to, I mean, there was always a proportion of time that was idle on the GPU. On a single node, it was not so severe, but as you go to 32 nodes, it's more than half of the time is idle time, GPU just waiting, doing nothing. So that was one example from HEMLB. I'll quickly go through a second code here, which is a finite element code, SpecVem3D running on the Leonardo booster system. That's from the CHEESE Solid Earth Center of Excellence. This is a Fortran 90 code, again parallelized with CUDA. As I said, running on the Leonardo booster, which has 4 of the more up-to-date Ampere GPUs per node. Again, we're focusing not on the initialization, which is a factor that is a variable that we're not so interested in, but focusing on the solver where the iterate time is done. That's where there's, in this case, 48,000 time steps. Those time steps include the non-blocking neighborhood communication with neighbors and data transfers to and from the GPUs. In this execution, there was also some summary output every 500 steps, but it turns out not to be such a big impact in the performance, so it's not a big factor here. So we've identified our iterate time solver as the focus of analysis. The kernels are all, the GPU kernels are all executed from there, which is nice because there's no, or the GPUs are completely idle during the initialization when it's reading in and distributing the data before the computation starts. But when we're doing our efficiency analysis, we need to be able to know which parts of the GPUs, which parts of the kernel execution are associated with our focus, and that's with the iterate time. In this case, it's relatively straightforward because it's all of them. The different kernels have different characteristics. Some of them take longer than others. What is particularly interesting is that one of the kernels was only executed by a single GPU. There was a set of another kernel which was executed by 4 of the neighboring, what I call nearby GPUs that are close to the one which was the source of the computation. And when we try and understand the performance, that will be a factor. So here, looking at so what are we looking at here? This is showing both strong and weak scaling. Weak scaling is perfect, so the green part we can more or less ignore. The strong scaling is a more challenging problem. It's strong scaling pretty well up until this case, 64 nodes, 256 GPUs. And then after that is where we have our biggest degradation here. And that means that our speed up is not what we would wish beyond 64 nodes. The efficiencies for the weak scaling case show that everything is relatively good. Looking at the GPU perspective, everything's in the green area, everything is very good. If you start looking at what's happening on the CPU is idle for most of the time because all of the computation has been offloaded to the GPU. So the CPU has just been there to orchestrate things, to have the data going back and forward between processes and to and from the GPUs. Whether you want to include that in the efficiency model is an open choice. In this case, it's understandable that it's idle most of the time, and it's of course necessary to be there, but as long as the GPUs are being fully utilized, that's where most of your computational benefit is coming from. The strong scaling scenario is a bit more challenging, or significantly more challenging. Taking our smallest scale execution here, which is 2 nodes with 8 processes, 8 GPUs. Again, we have relatively good GPU utilization, which degrades as we go to 256, 512 GPUs. And particularly with 512 GPUs, we're seeing that the efficiencies have gone down quite a lot. And they primarily have gone down because of this orchestration efficiency, or what Judith refers to as communication efficiency, where you're dealing with the data movement between the host and the devices. When we look at weak scaling, our bar charts show everything is in a good area. In this case, the GPUs are on the left, but there's very little idle time. It's all GPU kernel computation. Everything looks good. For the strong scaling scenario, starts off good, but it quickly starts to deteriorate. And specifically, or particularly with 512 nodes, 512 GPUs, sorry, a very large amount of the time as the GPUs idling, waiting. They're doing the same computation, but they're having to wait for the CPU to be able to do the data transfers, getting the data in and out of the GPUs, and for the other parts of the MPI. So here we have MPI point-to-point communication that has also grown and is taking more time. And there's also more CPU computation because it's having to handle this buffer management, so packing things in and out of buffers and for transfer to and from the GPUs. So the computation on the CPU side is also growing, and all of those factors together are resulting in much lower overall execution time and the GPUs idling. One of the reasons for the idling was identified in the topological inhomogeneity. You saw this picture earlier where we're looking at the 512 GPUs here. The ones in the corner, or the ones which are been processing the corners, are taking significantly longer for this computation. The ones on the edges, particularly the top and the bottom edges, the ones on the left and right edges, and then the ones which have the lowest computation time or kernel computation time are the ones in the interior. So it's all very, it's clear to see that distinction in this topological presentation. It's much harder to see if you're just looking at a list of process IDs and trying to figure out the pattern. What's even more interesting is if you look at some of these other kernels, and these kernels are very minor, they take very small amounts of time, but that's because they're only executed by 1 or by 4 processes, or 1 or 4 GPUs. So here is the same grade of processes, but when we look at at what they're doing, we're seeing that 1 of them is executing that kernel, 4 of them are executing this other kernel, and while they're executing that kernel, that also results in more delays for the other processes, which don't have that extra work to do, but have to wait for the overloaded GPUs to catch up and be able to continue. This is again showing this imbalance again. So this process here, the one which has is executing the add sources kernel, is the one which is in the middle here. It has much less time for CUDA synchronize because it has no waiting time. It's the one that all of the others are waiting for it. So that's why all of the others are this dark red color. They all have 16 seconds here of waiting time, whereas the one that has been executing that kernel has essentially no waiting time. I don't want to take more of Judith's time for her to go through some of her examples. We'll see how to use Scalasca Scorpii in the sessions tomorrow and then on Friday. But I hope that you've had a feeling for some of the things that you get from the Scalasca tools, and we'll see how you get comparable and complementary information from the Barcelona tools. So I'll hand over to Judith.
Hello. So nice to talk to you again. So this slot I'm going to present, as Brian said, some assessment done in POP with VSC tools. I have not, just a small disclaimer, I cannot fit the full assessment. I just reduce them to fit 3 examples in this presentation. Okay, I try to get from on time to fit the slot until 12. Okay, so let's start with a MPI study. Okay, some insights I get on an MPI study. This is a case. This is the name of the code, a portal. It was a MPI plus POSIX threads, but the user wanted me to focus on the MPI part. And the scale was from 141 processes up to 2,241 ranks. Okay, the platform was in Mare Nostrum 4, and you have here the details. And as I said before, one of the first things we do is to identify the application structure and define the focus of analysis. So to be brief, the focus of analysis for this region agreed by the user was one full iteration, where we can see the structure of one full iteration. This is the duration of the computing phases. There is a large computing phase labeled in orange, and then we have kind of some iterative part that you can see is kind of one part, and then it's kind of symmetric to the other way around, okay? It's kind of two waves on the same execution. This is one full iteration, and that was what they want us to analyze. With respect to the granularity of these computations, this orange region is taking 8 seconds. The duration here in average is around 70, 90 milliseconds, okay? If we look at the MPI calls, we see a lot of MPI activity. And in fact, you have to consider when you see the Paraver timelines, in the same pixel, you may have an interval of time, and in that interval, you may have both MPIs and computations, and that's the feeling here. You have to zoom in until you see some details, okay? The coloring is showing you a little bit the granularity, and the communication is done both with synchronous and asynchronous calls, and there is also an MPI already used that is absorbing the imbalance at the end. So one of the first thing we do on the POP analysis, as Brian already showed, is to look at the code scaling. So here we have the 5 scenarios analyzed with this code. We have the linear scaling because this is weak scaling, and we see that in fact it has a bad behavior even with the third run has already bad. But in fact, if we look at the timeline, third one doesn't look so bad, but the last 2 biggest cases really look not very performance. That should be weak scaling. They should last all of them the same amount of time, and you see that things are being increased. And if you focus on the larger run, you see the initial computation that was lasting here 8 seconds is much more larger now, okay? And you see also that the iteration is taking longer, and also the imbalance have these increases. All these processes finalized earlier, these guys take more time, okay? So let's see what the efficiencies tell us, okay? The efficiencies tell us with respect to the scaling, the number of instructions, okay? So is here clearly marked. The main problem is the number of instructions. There is code replication. There is increase of instructions when it should be the same number of instructions if you do weak scaling, same number of instructions per process, but here is being increased, okay? So this is what we name is not the same kind of code replication that in the strong scaling, but with respect to weak scaling. But also serialization and dependencies has an issue, okay? We see here this value is going down significantly on this range of processes. If we look at if we look at the first column, all the values are nice, and the lower values is in load balance, okay? So basically with this table, we focus on these 3 aspects, total number of instructions, serializations, and load balance. Very briefly, summarizing on few slides this study, we use the clustering tool that we will show you how to use it tomorrow or the day after, I'm not sure. And the tracking tools in order to see the evolution of these computing phases that, as we have seen, is one of the main problems, okay? And this increase of instructions. The analysis identified 3 regions. The first one is this large computing phase, then the main computation of the iterations, and the red is the small regions between them, okay? So we can see as before that the lines should keep on the same point, but in fact they are moving up, okay? They are increasing, all the regions are increasing the number of instructions. Nevertheless, the main 2 computations that are these 2 ones do not increase the number of instructions in all the iterations, okay? We see that from the first core count to the second core count, there is an increase of instructions, okay? But then it gets flat until the fourth, and then it go up again. Talking with the user, we understood that the problem is that the number of instructions per instance is increased related to one of the parameters that is the number of frequencies per rank, okay? While in the other ones, the number of increases, when you increase the number of grid points, increases the number of invocations, okay? So you have the 2 dimensions is, let's say, my computations become with more instructions because I have more frequencies to analyze. If I keep the same number of frequencies, but I increase the number of grid points on my mesh, then it also increases the number of instances, okay? So in the 2 dimensions, you have increase of instructions, okay? And the other thing that this tool is telling us very clearly is that the variability of instructions in the last core count is is large, okay? All of them seem shorter variability. This one has a higher variability. So that way we explain to the user the two main reasons for increasing the instructions, that one of the biggest problems. And let's look first at the other problem we identified, that was load balance and serialization. And this is the distribution of the MPI time. Very clearly, you can see here the imbalance is absorbed by the all reduce, but you can see here a kind of a triangle that this is the shape I told you this is a bad guy because it's not going to scale. In this case, it's not with all the processes, it's with a subset of processes. But what you see is that this triangle dominates this execution. And what you can see is that this shape is used the other way around for that one here, okay? This is kind of the triangle with the arrow here, and this is the triangle with the arrow on the other side. And those compensate, and that's the reason this is not expressed as unbalance, but is expressed as serialization, okay? And the user tell me that this is in the nature of the execution, and these patterns of the reduces that is done in these two shapes is almost impossible to eliminate from his point of view, okay? So this is at the beginning between the large computation and the iterative part. This is at the middle before the swap, okay? And the all reduces at the end. But basically with this picture, he understood where is the time in MPI distributed. But he thought that it was easy to fix a little bit this problem with the number of instructions. So a few months later, we agreed to have a new analysis of the same code to see what is the benefit of his improvements. He have worked to refactor the large computation, and in fact, he has absorbed this large computation inside the computation, so it's no longer seen as a unique interval of execution. And he has worked also to reduce the code replication. As a measure of these improvements, the reduction of the time was 7% of the iteration in the small core count, okay? And here we can see the brownish is the new version, the red is the previous one. We can see the improvement of this modification from a few months of work. And I think what is more important is that this is improving the scalability of the code, okay? So the gap, this is the time for the iteration, the gap between the original version and the new one is improving with the scale, is increasing with the scale. So this means that the changes he has been doing increases and improves the scalability of the code, okay? And just the last thing for this example is the efficiency analysis, where you see the reduction of the code replication, that it is still not perfect, okay? But it has been improved from 71, close to 72 to 86%, okay? And the para efficiency is almost the same thing. Small changes in communication and load balance, okay? And this is just one example of MPI to show you that with the right pointing to where to look at, well, some of them are not easy to solve, as I said, because this serialization depends on the nature of the algorithm, and for him, it was not easy to fix. But this part of the code replication, knowing where it happens, being able to correlate with these grid points and with these frequencies, allow him to solve it a little bit. The second example is for an OpenMP study, okay? And in that case, the code is named Explorer. The code is MPI plus OpenMP, but the user want me to analyze by separated MPI and OpenMP. Do not combine them, okay? So in this analysis, I just have one MPI rank, and I am scaling OpenMP, okay? With 4, 24, and 48 that is filling the node. That was again done in by an Ostrom 4 machine. And in that case, the user modified the code to add some events, okay? So as you will learn tomorrow, by default, BSC tools do not instrument user functions to minimize the overhead and to drive the analysis by the parallelization itself. But in this application, the user wanted to control the regions that are being analyzed. So in that sense, he added some events that are displayed here, okay? And this is the region they were interested us to analyze. So they decided the region based on their events, okay? So with the parallel functions, we see the structure of the application at the level of the parallelization. We see the parallel loops, okay? With the user events, we can identify that most of the time is focusing on the solve. The IO is almost not relevant, okay? And within the solve, the computation is the most relevant part, okay? So the scaling, as before, the scaling, increasing the number of threads, we see is quite poor, okay? With 24 threads is 49% of ideal. With 48 threads is only is less than 30% of ideal scaling, okay? But as I mentioned before, this is not an easy case because basically with OpenMP scaling, I am filling more the sockets with more processes, and that has impact on the resources, okay? And this is what the metric tell us. The metric tell us your main problem is the reduction of the computations, so the increase of the computation, sorry, because of a reduction of the IPC, a drastic reduction of the IPC. There is also communication efficiency in all the scales, but it does not degrade. And the load balance has some degradation not so relevant with the scale, okay? But clearly, the main problem that we see here is that the IPC is going down with the scale, okay? As we know, we are with OpenMP and we are filling the node. That may see that the IPC may not be the easiest thing to solve. So we may also consider if we can improve load balance, okay? Communication is the same thing, okay? And we can also have to understand that here is reflecting the time spent on the OpenMP runtime, why this is being increased, okay? So this is the picture I showed you this morning before, okay, where we can see that it's all the regions that have this degradation. Almost all the phases have a lighter color, meaning the IPC is being reduced. And the explanation is because of this filling of the node. If we look at the profiles of the parallel functions, we can see that the IPC, the values of the IPC are low, and they are, except for these pink and red functions, all of them with a larger scale got to very, very bad values, okay? If we go to compare with these same profiles, sorry, about the percentage of time the parallel functions are computing and what is the load balance of those parallel functions, we have to look at the percentage, we have to look to the average value. And we see that with 4 threads is 70–80%, that is maybe acceptable. But if we go to 24, they are computing 60%. Well, we can ignore this one because it is doing a bad scaling, and that's the reason it keeps slow. It's 60%, okay, 40%. So if we go deeper in the scale, same numbers, okay, very, very high percentage of time inside the parallel runtime that make us to consider this has a very fine granularity, okay? This is the first thing we get from here. The other thing about the load balance that was not so important is checking the average divided by maximum, okay? And we see that with 4 threads, it's almost perfect. It's in the 90s. If we go to 24 threads, there are 2 main regions that have suffering problems of load balance, okay, and are the same ones that have the problems. The other keeps on the 80s, 90s, okay? So we can identify at the level of the parallel functions which one has problems of load balance and which one has problems of communication based on the time spent on the parallel runtimes, okay? The efficiency model, okay, we get the values, oh, sorry, I forgot to say. The reason here is this hint of very fine granularity make me to check with them what was the scheduling they were doing, and they were doing the default scheduling of the system that was dynamic with chunk size equal to 1. And due to the size of their iteration, this chunk size equal to 1 was very fine-grained, okay? And that was part of the problem. So during the study, they do some other runs changing the OpenMP scheduling to check what is the impact of this scheduling. We try dynamic 100, dynamic 1000, guided 1000, and static, okay? And you can see all of them have very similar values. All of them have values that are improving the parallel efficiency. The parallel efficiency for the previous run this is with 24 threads. The parallel efficiency was 66.9%. All of them now are close to 80, okay? The best case for the global efficiency is dynamic 1000, okay? The worst case is static. And the reason for that is that if we look at the other components to understand, the reason for dynamic 1000 to be the biggest one, well, it has a higher fire efficiency than the static, but is the computation scalability quite similar? Okay, so is this increase on the fire efficiency the one that makes the difference? But then we have also at the level of the frequency scalability, they are similar, okay? So that was the main component. And if we compare them at the level, this is just one zoom of a very small region, but to understand what's the difference between them is that with dynamic 1000, the regions are much more better balanced, okay? Because you work with chunks and you are able to balance. With static, you get this imbalance that is caused by this time outside the so let's say the chunk is fixed, you have your work and you finalize and you have to wait the others, okay? So the benefits for static is that I reduce the time in the parallel runtime. The benefits for dynamic is that I better balance. So there is a trade-off of the scheduling that fits better your requirements, okay? So let's move to the last case, that is a MPI plus CUDA study. And in this case, I have done 3 studies for the same code along few years, okay? The code is named Tsunami High Sea, and it's in MPI plus CUDA. It was the first MPI plus CUDA case I have to analyze. So, but I have been seeing the evolution of this code along the years, the improvement of this code along the years. The first 2 studies was done in a machine of BSC that was named CTE Power, and the last one has been done in Leonardo. So these images correspond to the focus of analysis for the first study. And basically, after validating that all the iterations have a very similar behavior and there is no correlation a long time with the execution of the iterations, we selected 300 iterations. So we keep some small variability between them, but it's larger enough to reflect potential serializations between iterations. So if my code is MPI plus CUDA, I can view different things. In this slide, I present the 300 iterations at the level of the computations. I see color are lighter, meaning small computations for that interval. I see the MPI calls, so I see the MPI activity, and I can also have a look at the CUDA runtime, okay? And if I zoom until I see the details, I can see, for instance, here 3 iterations where I can see here the CPUs and the GPUs. Here I focus on the CPUs to look at the MPI activity. I see as before the MPI will reduce. I see point-to-point patterns, okay? And I can also see the CUDA runtime calls on the CPUs and the execution of the kernels on the GPUs, okay? So when my code is hybrid, I open more views in Paraver. I'm able to focus on more aspects of my application. Again, we focus on the scalability of this code. The initial version has not a very good scalability, and with 64 nodes, that was 64 MPI ranks and 64 CUDA devices, it goes down the speed up to 35%, okay? That was the initial version. And if we look at the efficiencies, this is a different table because on those days, I was working to develop the hybrid model. So I just have the efficiency as the hybrid level, where I see that the power efficiency is really bad. It's starting low, but it's getting bad and bad. Load balance is a problem for all the scales, but also communication. Communication suffers the biggest degradation. And also the computations, okay? So both communications and computations are the main problem, okay? So load balance is bad, it's getting worse, but the degradation is smaller, okay? So this first version has too much issues in all the factors. And this is a picture where I started to display as a component contribution. And the message here is that there is both MPI and CUDA components, both of them impact, but the MPI has a flat behavior, almost flat, except this execution, the contribution of MPI is the same for all the runs, while the CUDA component increases the problem with the scale, okay? So the message is that I have problems in both programming models, But in one is a scaling problem, while in the other, it happens in all the scales, okay? And finally, computation, yeah, it's true that it is increasing, but it's not so relevant. So some of these pictures you have been looking before. I'm trying to summarize all the studies in few slides, so I have compressed some of the information. And in this slide, I show you a little bit load balance and data transfer, okay? So in this case of load balance, I can focus at the level of the MPI ranks because I already identified there is an increase of imbalance when I increase the number of processes at the level of MPI. So the distribution, the message will be the distribution of work at the level of MPI is bad and has to be improved to reduce the time in the all reduce that is absorbing the imbalance of the previous phases, okay? This is the ideal scenario I presented before on the previous presentation. And if you remember, the message I said for this presentation is that the point-to-point calls are transferring data, are delayed because they require to transfer data. And my suggestion was to overlap this with the computations. So if my application is MPI plus CUDA, what it means is not to do overlapping with a synchronous call, is to execute the kernels while the point-to-point are being executed. Okay, so the GPUs are computing the kernels while this is this MPI point-to-point time calls take care. So this is the second version that was around less than 1 year after the first version. And in this plot, I show you linear scaling, the first audit and the second audit. And you can see a good improvement, okay? For the small core counts, not so important. Okay, if you remember, the one that has more impact with the scale was the CUDA part, okay? And the one that has less impact with the scale was MPI. So here we have the improved with the scale. So it's more related to the CUDA part, okay? But basically they have done 2 examples. So the improve is around 30 or 40%, depending on where you focus. The 2 improvements they have been working during that year was to overlap the point-to-point calls with the kernel's execution. That was one of the suggestions, and the other one was to improve the load balance between the MPI ranks. Okay, so they work in these 2 lines I mentioned on the previous slide. And you can see here this new version, how it looked like. So you can see that this is the point-to-point, while the point-to-points take care, kernels are being executed in GPU, so that is not wasting time any longer, okay? And you can see also that this time in the all reduce is being reduced. What we already see here is there is a gap since the kernel is finalized until the all reduce take place, okay? And in fact, that gap was the trick. Let's look first at the efficiencies, okay? And in this scenario, I was already evaluating if it makes sense to go to all the resources or the GPUs. My opinion is that that depends on the maturity of the code, okay? And in that level, it was kind of better enough, but maybe not too much. So I use both approaches, okay? And here we can see at the global efficiency level, values are very low, but you can see that the main problem is load balance, okay? Because they started to eliminate the task, the work inside the CPUs, okay? If we look at the MPI contribution to load balance, that was one of the improvements, okay? They have now much more better. It's always 90s or very close to 90s in all the scales. So the distribution of work between MPI is quite good, okay? At the level of CUDA, as this consider all the resources, is bad because the CPUs are not doing, but it's quite flat. In fact, improve a little bit, okay? So basically the balance either in MPI and CUDA is quite good, okay? And then the communication efficiency is the one that suffers more degradations, okay? If we look at the contribution, we see that there is contribution, quite similar contribution for both programming models, okay? This is if we look at the metrics at the level of all the resources. Sorry, I forgot to mention the computation scalability that has also some reduction, okay? So if I look at all the resources, I will say computation scalability, you have to look at it, okay? And also the communication. I can't ignore the load balance because I know of this approach. But if I basically focus on the GPUs only, then I can see the efficiencies are much more better. but they also suffering a huge degradation. And then we can see that the computation scalability has some impact, but not so important because I keep on the 80s, okay? The parallel efficiency is the one that suffers a bigger degradation and is correlated not with the load balance, that is almost perfect, close to 95, 96 in all the scales, but related with the communications, okay? So again, I can display, and this picture I think I showed you this morning, I can display between the programming models, and I see that now the MPI component that before it has a flat behavior now increases with the scale, but it has reduced its contribution. Now, most of the problem is on the CUDA component, and we have seen is also related with the communications, okay? But it's almost constant with all the scales, okay? And during this analysis, as I mentioned a few slides ago, we saw this gap that is more clear when we go to larger core counts, larger number of GPUs, that the kernels finalize here, the all reduce take place here, but it takes a lot of time. There is a gap here that does not correspond to any reason for that, okay? So when I was discussing the results with them, I tell them what is doing in that phase your application, because it seems there is some inefficiency on the CUDA runtime processing that part, because it's not part of MPI, it's part of the CUDA runtime. So that was a CUDA reduction phase, okay? And I try to push them to convince them to see the problem is in that CUDA reduction phase. Can you eliminate that CUDA reduction phase? During this analysis, they did a first tricky version that is not, it was not the right answer, but it was kind of a check-in version to validate if eliminating this CUDA reduction phase, things improve. And you can see clear the improvement here. This black hole where the GPUs are doing nothing is almost disappeared, and basically now is absorbing with the all reduced the imbalance between the processes, between the CUDA devices, okay? So with these hints on the execution, they already did the modification, but the latest version that was for the end of last year, analyze of that code, is a much more improved version, okay? That I think it may be 3-4 years since the first analysis, okay? So this is with only 4 GPUs, so it's clear to see things here, but basically we can see that CPUs are doing nothing. This is the computation. The work is done on the GPUs. You can see the GPUs has almost all the time with coloring. If we focus on the MPI calls, we see it's very narrow. The time in MPI is less than 1% in these 30 iterations, okay? We see that the CPUs spend most of the time in the CUDA runtime, in the red, that is the CUDA main copy, around 99% of the time, okay? And we see that the kernels are executing, the GPUs are executing the kernels close to 95% of the time, okay? So with 4 GPUs, the situation is almost perfect. So devices are running kernels, CPUs are taking care of the accelerators, and MPI has a very low overhead that does not make noise on the execution, okay? So this is the scaling, and in fact, in this plot, I show the scaling they measure without the Extrae and the scaling of the instrumented core count, because our instrument, with the instrumentation, the overhead increases a little bit, and there is a small reduction, okay? But if you remember the previous initial figure, it was really bad. It was around 30%. Then in November 20, it was just over 50%, okay? Now we go up to 83% of the top of the linear speed up, okay? So it's a real improvement of this code along the years, okay? And this is the efficiency model. In that case, this code, from my point of view, was mature enough. I think I already presented this slide on the previous presentation, okay? We still see few things, and I will present that on the next slides, but it's almost perfect execution, except that all the CPUs are just wasted because they are dedicated to wait for the GPUs to require some work from their side, okay? But we can still analyze this case, and in this approach where I focus on the GPU, what I check is what is doing the CPUs while the GPU is idling, okay? So the CPU has to fit on the GPU, and I want to understand when the GPU is idling, what is the CPU doing? Why is not feeding more information? And I compare here 4 GPUs with 64 GPUs, top and down, okay? And here I have also the timelines where we see the kernel's execution, okay? And we see the state of the CPUs during that interval. And there is a clear increase on 2 aspects. One is CUDA copy, and the other one is the O-reduce, okay? CUDA copy basically means I'm doing a strong scaling. So I am reducing the amount of work, okay? And the data I have to send, let's say the cost to send the data to the accelerator start to become more important. Nevertheless, you have to remember, we have metrics that are very high, okay? If we go back to the efficiencies, the communication efficiency, the lower value was 85, okay, with 64. So it's still very high. Power efficiency is 83%, 83.5, okay? But the reason basically is doing a strong scaling, you cannot go deeper than that. With 64 GPUs, the amount of data you have to send to the accelerator with the computation cannot scale further, okay? And the other thing is the O-reduce. As we saw, the O-reduce is absorbing the small imbalance. But now what we see is the MPI O-reduce has a better balance with 64 ranks. I see that here, saying that this is 62, this is going to 79. Okay, I check that here in that numbers. I can explain you later this week why I check those numbers. So basically, the fact that there is a better balance with 64 ranks, but it represents a higher percentage of time, is highlighting that is the data transfer. So again, it's because of the strong scaling is getting to a compromise on the amount of work with respect to the communication, you have to do, okay? Last 2 slides is scaling of the kernels, okay? This is focusing, this application have many kernels, so focusing on the scaling of the 11 kernels, each of them represent at least a 4% of the execution time with the 64 GPUs, okay? So I eliminate some kernels that have a very low contribution and that focus, I can see more the variability between them. I can see that for these top 10 kernels, top 11 kernels, 10 of them have a very good scaling efficiency between 94, 98, okay? And only there is one kernel that represents close to 5%, and the degradation is bigger, despite this is still 87%, okay? So this is the kernel they may consider, and this is a reduction, okay? They may consider to improve it a little bit, okay? To improve the computations scaling. Other thing they requested to me is they wanted me to check if the scaling of, if the load balance of the kernels was good or not. So I did this analysis. This is the main kernels of the application, and higher will be perfect balance, okay? We can see that most of the kernels keys in the ratio between 80%, 1% of balance, and there are only 3 guys that has in the 60, around 70%, okay? And for these 3 guides, 2 of them represent less than 5% of the execution time, and there is only one that represents 9% of the execution time, and maybe they want to consider to improve a little bit the balance, and this is the name of the kernel, okay? So I think with that, I'm done. So I just fit on time, okay? I try to briefly see the kind of insight we can see for different flavors of programming models with the tools, okay? So the idea is that now you have a rest, you have lunch, and this afternoon you will learn about more tools, but for tomorrow you will go back to these tools to know how to use them and to explore how to benefit from them on your codes. If there is any question, I will be quite happy to answer. So Brian, I think, and Karina, I think we are ready to go for lunch.
Yes, if there are no more questions, then please let's head for lunch. It is for 1 hour now, so we will start again at 1 p.m.
Okay, so welcome to the session about tools that we develop in from the different POP partners that are not covered by the remaining workshop in detail. And so I will present 3 different tools. The first tool is Archer. It's a tool for detecting data races in OpenMP applications. So what is a data race and why is it a problem? There are different definitions for data race in C++, standard, and OpenMP, but at the end, it's always that multiple threads try to access the same data or the same address concurrently without ordering, and then C++ defines it explicitly as undefined behavior, and OpenMP calls it the result is unspecified, but at the end it's basically also undefined behavior. And the problem with undefined behavior is that anything can happen. The compiler can apply whatever optimization there. And so also some people believe there might be benign data races. In C++, they are not benign. There is the concept of benign data races, for example, in Java, where this notion comes from. So if you have a data race in the application, then you should remove it. Otherwise, you don't know whether you can trust the results or not. So how does might a data race manifest? Here in this OpenMP code, we have a shared variable A. It's shared implicitly because it didn't put any clause. And the idea is that this while loop increments A, and then the while loop aborts when an upper bound is reached. This upper bound is set to 100. And then if you execute this code, you will realize that at the end, A might be 100, 101, 102. Since we execute with 8 threads, for most implementations, A can be any value between 100 and 107, but you don't have a guarantee that it might not be any random number. And then the other issue is that the value that is passed into the sinus function is also not clear. There might be an increment by the other thread in between, and then you will throw in more or less random numbers into scene. And so even if the output tells you the while loop executed 404 times, you might see different results for some. And then we can treat the undefined behavior from the data race by making A atomic. And then A is atomic here. That means it's now not undefined behavior, but we still have a race condition between the increment down here and the boundary check in the while loop. And so executing this application, you will still see output with A from 100 to 107. But what you will also see is that whenever you get the same value for I, you will get a deterministic value for some. And that shows, or that also indicates that we now don't have undefined behavior, but now we just see the result of the race condition between these two separate operations that are not atomically done. Okay, so the good news is there are tools to detect data races, and one tool is thread synthesizer, and we were also working in this extension called Archer, which allows to detect data races in OpenMP code. So thread synthesizer was developed in the context of Clang like 10 years ago from some Google engineers, and it's part of LVM since I think version 5. And now it also is part of the latest Intel compilers, which are also built on Clang. The only thing you need to do to apply the tool is add these two flags. So the fsanitized thread flag will run or will tell the compiler to apply the data race detection, and then this additional flag will just provide you more understandable stack traces. You should also add -g so that you get actually source line information. And then you would just execute the application as you would execute your OpenMP application. Since this workshop is more focused on GPU offloading, Clang, so the thread sanitizer and also Archer can also be used to detect data races in OpenMP target code. And the trick there is that Clang provides a host backend for target regions, and then all target regions will be executed on the host CPU. That means you should reserve enough cores in a node to execute this efficiently. But if you just reserve a single node, then you can analyze OpenMP target code with these flags. All the reports will be on the command line. And because we are limited in time, I don't have a concrete example how this looks like. But I can also point you to a tutorial where you get more details. One thing that I want to mention is that if you try to run it with Intel compiler, then you will need to explicitly load the Archer library. Otherwise, you will get false positives for OpenMP code. If you compile with Clang, the library will be loaded automatically, but with Intel, it's not automatic at the time. Then there might also be some Fortran codes. For Fortran codes, it's a bit more tricky because Clang does not have a Fortran front end. So there are two options. One option is to use gfortran to compile the code, or the alternative is to use a new Intel Fortran compiler, which also has the sanitizer flag. With the Intel compiler, you will not need to do anything special. With the Fortran compiler, and if you want to analyze OpenMP codes, then you should make sure to load or to link the LVM OpenMP runtime, and that needs to be available during compilation, or you compile the code with Fortran compiler, but then link the code with Clang. Okay, so there are more details in a more detailed, in a more in-depth tutorial, and I will show you the link, I guess, in the next slide. So that was everything for Archer. So let's look into the next tool. That's MUST, and MUST is a tool that we developed for more than 10 years now, and just recently, and it's more in the development state, but I think the analysis itself is quite stable. It's just not in a release of Archer of MUST yet. So we added GPU correctness analysis, and in the following slides, I will have the focus on this new GPU analysis. And if you're interested in more details, then you can also check out the MUST tutorial, and the Archer tutorial is actually in the same HPC public directory. There's also a sanitizer tutorial, which has more information about the different sanitizers and then also more details about Archer. Okay, so let's dive into MUST. So what we do with MUST is we detect issues in MPI codes. And This short example also, it's basically just a hello world example, has at least 8 known issues. In a more extended tutorial, I would ask you where the issues are, but now I will just present some of them. So if you are familiar with MPI, then you should know that there needs to be an MPI init, there needs to be an MPI finalize. So that's missing. Then we have a deadlock because all the processes are executing MPI receive. They will all wait in the MPI receive and stall there. Unless one of the processes actually tries to evaluate this thing here, because size minus rank is actually size for rank 0, and size is just 1 above the highest rank in a communicator. So this is communication out of the bound of the communicator, and so this code as it is at the moment will probably crash if we would add the MPI init here. Another issue is that the code is using MPI integer, which is a Fortran type and must not be used in C code because this is C code. Here we have the corresponding C type. Another issue is that the type is created here, but not committed before the use here. And then the send, because of type consists of 2 integers, will actually send 4 integers, which is more than the receive expects. And so what I try to show here is the different kind of MPI errors that must helps to detect. And so the motivation for applying MUS is that MPI programming is error prone. The MPI standard now has almost 1,000 pages, and having all details in mind is probably not feasible. It might manifest as portability issues. That means that your code runs on some system, and then when you move to the other system, it doesn't manifest. The bugs might also manifest in different flavors. If the application crashes, that's basically the best case, because then you know you actually have an issue. The worst case is probably that the execution finishes, but you can never be sure that you have that you get the right result if you don't know whether you have bugs in the MPI code. So resulting questions are: why does the application crash? Why does it hang? Where is the deadlock? Are the results correct? Is the communication pattern correct? And then is it also portable, basically? And MUS helps to pinpoint all these bugs, and specifically MUS helps to detect the issues that I've shown in this initial example. Everything besides this missing MPI init and this missing MPI finalized, because that's where the tool is actually initialized and finalized. And so without these calls, MUS will not get active. So you need at least MPI init and MPI finalized in the code. Okay, and then when you run MUS, at the end you will get a report as an HTML file by default. You can open it in any web browser. And then it shows you which ranks are involved in the issue. You have by default just a collapsed message about the concrete issue, but then you can click on this line and then it will expand to its full message. Then you have a detailed description of what the issue is, and then you have also references to related MPI calls, and then if you compile the application with debug information, you will get also stack traces that tell you where this call came from. In this case, for some messages, you will also have some hyperrefs, and then you will get more details like a graphical representation of the deadlock here. And then this will point you out how the deadlock manifested. In the best case, you have an output like that that just tells you in a green bar that there were no issues found during the execution. Okay, so how do you execute or how should you compile the code and execute it? The only thing to change for the compilation is that you should add the debug flag. Otherwise, you will not get source line information in the report. And then the other step is, so on the left side, we have the normal execution of the application. So you would execute the C code to an Excel file, and then we run the Excel file with whatever MPI command is appropriate. This might be srun, this might be MPI exec, or whatever is used by the MPI implementation. And then what you can just add is must run -- must MPI exec to this command on the left-hand side, and then must executes. So on Carolina, you would use srun here, and that executes, or you could also just execute must run, because if must is probably installed on the system, then it should know what the appropriate MPI exec command is and use that. Afterwards, as I said, you inspect this must output HTML file. At the end of the execution, must will also tell you where to find this file. So if you're wondering where your batch script wrote this file to, then just look at the output of your batch job. By default, must run uses one additional process. So if we execute must run NP4, we will use 5 processes. Everything beyond that is advanced stuff that you can look up in a detailed must tutorial. And I also included some of this information in the slides you can download from the webpage, but I will jump over this advanced usage now and directly get to the compiler edit analysis that we use to analyze GPU offloading codes. Okay, so this is the code pattern we want to look at. So the assumption here is that we are executing with CUDA where MPI. That means all the buffers we want to transport with MPI are already on the GPU. And so this in buff and this out buff used in the MPI communication is actually a device buffer. If you're using shared memory, how's it called? Unified memory, then you would not explicitly copy the data, but then this might also be just a host address. But if you're using separate memory and do manual CUDA transfers, then this is actually a device address. And the idea is that we are passing this input buffer to the kernel as an argument, and then this kernel will work on the in buffer. But for the code to work correctly, we would need to make sure that the input data is actually received before the kernel can start. And what we are missing here in this code is that the MPI receive has an out dependence to inbuff, but the communication is actually only completed with the MPI wait, and this MPI wait does not have an out dependence to inbuff. So the MPI wait can execute concurrently or after the actual kernel execution. And so we have a race condition between executing the in buffer in the MPI receive and the kernel execution. And then we basically have the same issue on the output path. So the idea is that this kernel writes the output or the results, however you want to call it, to this out buffer, and then the out buffer should be sent to this other process. But again, here, according to OpenMP semantics, we don't have a dependence that synchronizes these two calls because we have an out dependence to inbuff, but here we have an independence to outbuff. And so basically here is an out dependence to outbuff missing. And so again, the ISEND can execute concurrently to the kernel execution. And we have a data race between these accesses. And so these are the kind of issues that this new extension to must can detect. What we do here is we apply a compiler pass that actually analyzes the CUDA kernel, checks all the pointers that are passed in to the kernel, and checks whether they are used read-only in the kernel or whether they are used also by writing to this buffer. And then we do the analysis on this high level, on this post-grain level. So we don't track the individual memory accesses that you do in the kernel. It's just if the buffer is written in the kernel, then we assume you basically touch the whole buffer writing, and then if you concurrently use the buffer in an MPI communication, we will always report a race there. Even if you, let's say, only operate on the first half of the buffer space, and the MPI communication only touches the second half of the buffer space, that's the level we cannot distinguish at that point. So there might be some false positives. And then what toolchain do we need there? You actually need to touch 3 tools at the end. So there is Kusan, the CUDA sanitizer, which instruments the CUDA kernel invocation and also the CUDA API calls to get the information about the buffers that are passed into CUDA, and then also to understand the synchronization semantics of CUDA. You need must, as you have seen before, and we also need Archer, respectively thread sanitizer, first to instrument local memory accesses, but then also to have the thread sanitizer runtime available, because at the end all these races are analyzed in the thread sanitizer runtime, and Kusan and must just feed the information about the different memory accesses from MPI semantics, from CUDA semantics into the thread sanitizer analysis. So the first step is how would you use must together with Archer. At the end, you just compile the MPI+OpenMP application, and OpenMP is optional there. It also works if you have a plain MPI single-threaded application. You will still compile with a thread sanitizer flag, as seen in the first slides. If you want to use Clang to compile with OpenMP or Intel compilers, you might need to export some of these flags to tell the MPI-CC, MPI-CXX command that that's the actual C or C++ compiler you want to use. And then the flag is available. And then for the execution with must, you should set the must tsarn flag, because that makes must aware that it should put the memory access semantics of MPI calls into tsarn. And what I mean with memory access semantics is if you have, let's say, an MPI receive, then the semantic of the receive is that MPI writes to the buffer. And so what must does there is it tells thread sanitizer that these parts of the buffer that the MPI call would write, they are actually accessed in writing now. Okay, and then there is this optional step to link in this on report loader. If you use this, then the thread sanitizer output will be included into the must report. The advantage there is that the output is actually aggregated, and you will not have too many duplicates, because if you run the analysis with let's say 10 MPI processes, then each of the processes will report all the detected traces and will quite overwhelm you. But having everything integrated in must report, we can reduce the output and show you only one representative. Okay, and then Kusan, as I already said, that's a tool that we use to find the traces in CUDA calls. It consists of this LVM compiler plugin to instrument the accesses, and then at runtime it passes this information into the thread sanitizer runtime. And then at the end, thread sanitizer will have all information available that is necessary. It will have information about MPI. It will have information about CUDA. It will have information about the memory accesses that the application does. So at the end, it will also be possible to detect traces between memory accesses in a CUDA kernel and, for example, access to the same variable by a different thread, if it's unified shared memory. Okay, so how would you compile with Kusan? If you have a simple make file that uses some environment variables like MPI+CC, then you can just set this variable to Kusan MPI++. The special thing is that for some development state reasons, you also need to use the C++ compiler front end for C codes. And then you can just compile the code, or you can actually set this prefix one time execution. So in that case, you would not even need to touch the make file. If you have different build system like CMake, then there might be a similar step necessary that you will see for Scorpy tomorrow. Then you need to export this environmental variable to tell the compiler wrapper to disable itself for the CMake command, but then during make you don't export this. So this is a variable you should not export. This is a variable you should only set for the CMake command. And then CMake will use this as the C compiler, and during make it will be used. What you get at the end is a report that might look like this. So if everything works well, then you get a warning about a data race between a read of size 8 in MPI send and a write in this compiler, in this device stub, which is basically the result of compiling this kernel function. You also get information about where the MPI send was executed. That's in the source code line here, and then you also get information about where the kernel was launched, and it's in the source code line. So that was the introduction for Must. I will use 2 more minutes to introduce the third tool, and then I will hand over to Felix to provide you a live demo of how to use Must on the machine. So the last tool is to collect performance model factors on the fly. It's called the on-the-fly critical path tool. What it does is it collects information about the critical path during execution of the application. And then when knowing the critical path, it can use this information to calculate the performance metrics. To use the tool, you will just run your MPI code with 2 additional environmental variables effectively. One to load the OMPT part of the tool, one to make it also available for MPI. And then there are different options you can set for the output. And that way you can actually log the output to a file rather than to standard out. And if you do a scaling experiment, basically execute the application with different number of processes or threads, then you will probably get different output files, and you can use these output files to generate a plot. And the script will generate 2 output files. One is a table that will be similar to some of the other tools from the POP partners. And then it will also provide you such a diagram that I learned is hard to read, and we will need to work on this. And so with that, I want to hand over to Felix to show you how to use the tools from Carolina.
I can't share my screen right now. Okay, now it works. Hope you can see my screen now.
Yes.
Okay, so as Joachim said, for those of you who want to make use of the tools or explicitly Must and the Kusan toolchain, we also prepared all the modules on Carolina, and here I have a simple example with a data race between a send and this kernel launch. And if we want to analyze this code, as Joachim said before, we just have to compile it with Kusan, as explained here. Kusan is available, this module here, and Must is also available for the same toolchain here. And that's basically it for compiling it. Then when we want to run this, we just have to replace our MPI exec call with must run, as Joachim said. And what we basically get when we execute this, I can just execute this right now on Carolina. Then we should get some output, hopefully, when our job gets scheduled. Okay, maybe I will just show you the output then. So this is basically just additional output you get from the compiler, from Kusan, from the compiler passes. And then there's the mass output. And this basically is the output of when printed to standard out, so not to HTML actually, because it's maybe more convenient for you to do that on the cluster when you're debugging live or so. And this is only the result when running with this on report loader. Maybe I can also show you when we disable this. And show you what Joachim said regarding the output from thread sanitizer itself, but not intercepting the output of thread sanitizer with must.
Okay, so while waiting, probably there are some questions. Okay.
Are there any questions? Okay. So this is actually the output of thread sanitizer itself and not running with mass, and there's some color also that just reports the arrays. And you also get the line information, but from mass you get additionally the information, which rank it was and so on, and the filtering. And we also, if you want to make use of the critical path tool, which was presented last, it's also available on Carolina for the latest Intel MPI toolchain and also for the latest OpenMPI toolchain, but together with Claim because you need the OMP tools interface for it to work correctly. Yeah, and here I also maybe can show you what Joachim said regarding when you are executing with multiple different configurations, you can set the output or the log path to always a different file basically, which includes the number of threads and also the number of ranks. So you then get some output here with the different configurations, and then can use them for plotting if you want to try that out later on. I don't know whether we can share these files for you to use them later, but maybe that's possible.
Yeah, we can package them up, send it to Brian, and then they will be available on the webpage. Okay, then if there are no questions, we would hand over to the next presenter.
Okay, so I think next up in the running order is Cedric. Are you ready?
Yeah, can you hear me?
I hear you. You're good to go.
Yes.
Okay, great. Thanks. Let me share my screen. Okay, so hello again. This is Cedric from University of Versailles Paris-Saclay, and now we'll present the Macao Performance Analysis and Optimization Framework. So in performance analysis and optimization, there are multiple factors that can impact performance, and the issue is being able to identify which actually is the dominant issue and which are the dominant issues. For instance, we can have the issue can lie in the way we're using the CPU or accessing data, or whether the algorithm is simply not the right one for the task at hand, or the way it was implemented, or of course all the various issues that can crop up with parallelization and that we already saw this morning. for instance. And of course, these various issues can be fixed, addressed by different methods. You can either change the compilation options, you can change the code, you can change the binary itself, and of course, modify the way you are mapping your application on the various processors on the machine. And of course, an important point is being able to make sure that you are using the machine at full capacity and using all the functionalities that it offers. And a last point is being able to identify which are the most rewarding issues to fix, because you don't want to spend a week trying to obtain a performance gain that will be 1% in the end. So for instance, you could identify a region of code that hogs 40% of the total time of the execution time of the application. So the first idea will be that we will start there, but if we manage to predict that addressing this issue will only yield 10% speed up, the total impact will be much lower than if we had a smaller region of code, but that could yield a more significant speed up. So for that, there is no single bullet. We'll have to use various complementary tools that will focus on each different aspect on the analysis process. So the idea behind Macao is that we are trying to provide solutions in addition to identifying issues. So not only can we help in pointing performance issues in a code, we are trying to provide a help to explaining how to fix that, be it at the compiler level or code restructuration or the way your data is arranged. And we are operating at binary level. So the idea is that this allows us to identify, in addition to issues that could be stemming from the code itself, but we can also get information on what the compiler, which transformation the compiler performed on the code. And so this gives you an additional level of information. So the idea is that, yeah, what we analyze is what is being actually executed. So Macao focuses mainly on core analysis with an emphasis on trying to guide users through the optimization process and trying to estimate the ratio between the quantity of effort provided to fix a given issue versus your actual speed up you will obtain. So the idea behind Macao is that it's modular. So we have different modules that we can choose to invoke or not, depending on the type of issues that we suspect, given that some modules can be more time consuming to perform their analysis. Currently, so it's only operating at CPU levels. So for x86 architecture and R64, we have work in progress on GPU support. So hopefully by next year, we'll be able to have some insight on GPU codes. And we provide Macao as a static executable. So there is no need to install it. Basically, you simply need to download it. And it should work out of the box on most Linux distributions. Well, these are just an example of optimizations that we performed thanks to Macao. The idea here is to identify the various type of issues that we can find. For instance, in this case, we found out that there were functions invoked inside the loop and with always the same parameters. So we simply had to remove the function invocation from the loop to obtain a very significant speedup. For this code, for instance, there were a way the way data was accessed had an unnecessary level of indirection. So removing this also yield an important speedup. For that one, we identified that the compiler had declined to vectorize some loops, but our analysis showed that actually these loops could be vectorized safely. So we added some directives to enforce vectorization from the compiler, and we obtained a speedup. And that one needed to understand a bit about the algorithm. Basically, there were some division inside the loop, and we simply replaced by multiplication by the reciprocal, which is actually more efficient. And also, there were some loops with a small number of iterations. And this is actually expensive because you spend a lot of time trying to see whether you are needed to exit the loop or not. So by completely unrolling them, we also obtain some performance increase. So Macao is part of POP, as Brian said this morning. We had also various involvement in various European projects, and our feature have been integrated in some other tools as well. So all information relative to Macao is available on our website. We have a mirror in case this doesn't work. There is a tutorials for using Macao. Let me see the chat. So I think we have a few prototypes of integration in SPAC. I'll have to brush them because SPAC evolves faster than I have the time to maintain the recipe. But yeah, this is on the list. So there are tutorials on the website. You can download the static executable of the latest version of the binary. So we usually do 2 or 3 releases per year. The core source code is also available. And also at this address, you can see some analysis, some of the analysis that Macao performed on various codes that are available if you want to see what it's like. And I will show them after this presentation during the demo. So Macao as the core of Macao essentially will be responsible for extracting information from the binary, reconstructing high-level structures and perform some graph flow analysis. One thing important to note is that sometimes, since we are operating at binary level, it is possible that one single source loop in the source code will correspond to multiple loops in the binary code. So for that, we affect a unique identifier to loops. The idea is that this identifier will be unique, will be the same for the same binary. So if you relaunch the analysis, the identifiers will stay the same. So don't be surprised if you see sometimes identifiers in the Macao reports. It's also possible to perform binary writing to modify the binary to insert probes. The 2 main modules that are involved that are a part of the binary release is the static sampling-based profiler and static code analyzer that performs the analysis of the quality of the code. And finally, the last module does not perform any particular operation by itself. Analysis by itself, it will be simply in charge of launching various experiments using the various modules and aggregates the results to produce HTML reports. Or it's also possible to have them in text or Excel format. So the LPROF, the profiler, uses sampling. So the idea is that it offers a rather good accuracy with a minimal overhead. It does not require any recompilation to add any particular flag, apart possibly the flag, the -G flags that allows to store information linking the binary code to the source code, but that's mostly for comfort when reading the reports. It is agnostic with regard to parallel runtime. So basically, we don't need any specific version depending on the runtime. Of course, the drawback is that since it uses sampling, it will only work for if the application runs for at least 10 seconds. So, but normally that should not be an issue when we're dealing with HPC applications. And it's also possible to obtain results at the function, but also down to the loop granularity. The code quality analyzer performs a static analysis. So the idea is that you simply not only you don't need to execute the code to perform the analysis, but you could also technically you could perform the analysis considering you are running on a different processor than the one you are currently using. So you could, for instance, launch CQA on your laptop and ask what will happen if this code was to run on a cluster with I don't know. Whichever latest processor you have. So it tries to estimate the quality of the code that was generated by the compiler and to provide hints that are written in plain English on how to address them. So of course, the main purpose of CQA is to analyze HPC codes. It tends to focus a lot on loops, since that's usually where most of the time is spent in such a code. But it's also able to analyze functions and to provide insight into what happens in function. And also, since it's static, it will mostly identify issues related to computing and use of the processor. So how does CQ represent its results? Basically, we work by creating ideal scenarios, considering, for instance, that we have managed to vectorize all floating point instructions. And then we provide an estimation of the speedup if we manage to have that. So that's mostly how CQ provides its results, an estimation of the speedup. If you are considering, for instance, that we are not performing anything else beyond computation, so basically no address computation because we have indirect accesses and the like. If we manage to vectorize every floating point instructions, or if we manage to vectorize everything. And finally, OneView is the super module that's in charge of launching the other modules. So basically, you will need to explain OneView how to launch the application with which parameters. And it will take care of launching the application, invoking the modules for each of them. So mostly, for instance, that will be involved invoking lprof to identify the hotspot, invoke CQA on the hotspots, and then it will be able to aggregate all the results to provide some high-level metrics and high-level summary that tries to give an estimation on how difficult it will be to improve the application and where we should start with and with which issues. So OneView has different function mode. By default, the simplest one is OneView 1, so it will simply launch the application, perform the profiling, and perform a static analysis on the hotspots. Then we have the scalability mode, which consists in executing the application multiple times with different parallel configuration and presenting the results side by side. So this is a handy way, for instance, to test, to analyze the application with a varying number, for instance, of threads and see what happens when you increase the number of threads, that it fares as well as you would like. This ties back with what Brian and Judith were talking about this morning. The comparison mode is an extended version of that. Basically, the idea is that you can compare any two reports already generated by OneView. So not only the same binary, but for instance, you may want to compare how the program fares when it is compiled by different version of different compilers or different version of the same compiler, or even different architecture. It's possible, for instance, to compare the same application run on different hardwares, even for instance, Intel or ARM. Last but not least, the stability mode, which should be actually the first step in any performance analysis process. It simply involves running the application with identical parameters each time, a number of times, and just to see how stable the timing of the application is. This is very useful because, for instance, you just want to have an idea of the variation that is expected of the time of the application, just to know, for instance, if you are developing, adding an optimization and want to see the speed up you gained, that you are not just looking at the noise of the execution time. So, as I was saying, to launch OneView, you will simply need to invoke OneView and provide the executable with all the necessary information you want. For instance, saying that, hey, you want to run something with MPI with give this number of threads, the executable will be called like that. You can also create a configuration file and store all the information that you want. There is an extra quote here that has nothing to do here. You can create a configuration file and store all the parameters inside. And then OneView will generate the results. and provide the reports. I will just show this. Actually, this will be simpler than looking at slides. So first, does anybody has any question before I launch into the actual demo of how to launch Macao and how to navigate the reports that it produces? Okay, then I will switch to the demo as soon as I manage to switch here. Yeah, so for instance, here I'm using, sorry, I'm trying to move the zoom bar because it's annoying me. Yeah, I can do that. Okay. So, for example, just to show how to execute Macao, I took the example of a simple dance parlin benchmark, for instance, something you may already be familiar with. It's a very simple benchmark that you can run, for instance, here with 2 MPI processes and 2 threads. And the idea is that if you want to invoke it with one view, you can just, you will need to provide, so first the level of report that you want. So this is a shortcut for the report equals 1. You have to provide the MPI command. You can also provide the number of processes in a separate variable, for instance. Here, I asked it also to generate the POP metrics. And then Macao one view will take care of executing the application. So here we are just launching the application with the profiler. And after that, it will perform the static analysis. So it completed the profiling, and then it's performing static analysis on all the loops that it found in the binary. So this is a simple example for the purpose of this demo. If you are using a batch script, you have to use something a bit more complex than that. But everything described is in the online help of Macao. You have a description of every single option, and you can also generate a standard configuration file. That contains all the various options and how to fill them. And there are also tutorials on the website explaining how to fill these informations. So now the analysis was completed and it generated an HTML report. So by default, it generates, if we don't specify a name for the experiment directory, it just generates one with a timestamp name. And this is something that I can open in my browser. So the path of the files to open is indicated in the command line after it completes. Okay, so this is the summary view of the reports. The idea is that for the summaries to have a high-level overview of the experiment we made and of some characterization of the application and estimation of the complexity of the performance analysis and optimization process. So this first tab is performing some basic checks on the validity of the experiments we just performed, just to make sure that we didn't perform any big problem, any mistake, that we didn't do any mistake when running the experiment that will prevent us to have meaningful results. So for instance, here, as I was saying, since we are using sampling, we consider that a run should need to be at least 10 seconds long. In fact, it's 5, but we put the warning as long as it's below 10. We display a warning to say, okay, that run is too short. The results from the sampling may not be as accurate as are as useful as you want. This is particularly useful, for instance, if by mistake you use the test dataset, for instance, and your run is only 1 second long, there will be this huge red marker here to say that you don't have any useful information. We also perform some basic checks on whether some very useful basic completion options are present. So for instance, here, I compiled the application with some basic options. And by default, the compiler is not told to optimize the application, the compilation for the processor on which it will be executed. So by default, it performs a code that's supposed to run on any type of processor. So it will lack optimization. So we can provide information right here. The second tab, so basically a tab is open only if there is some red. So that one is happy. Basically, the second tab is trying to get an information on the complexity of the application itself and try to estimate whether it will be hard to optimize. For instance, we are detecting whether the loop profile is flat or not, because if we want to try to optimize the code, we don't know. We would like to see the areas of code that take a lot of time. And for instance, we had a pathological case like that once when we had to optimize a code where that contained 100 loops, each taking 1% of the total application time. So in that case, we can say, okay, this will be long. You won't get any quick and fast results because you will have to optimize each loops. For instance, this is the type of information that we check. We check that we are spending enough time in loops, for instance, because we tend to focus a lot on them. And if not, then you will have to spend more time because the issue will be less rewarding to fix. And finally, this last tab contains information on the hottest loops in the application. So for each loop, we have so these are the hottest loops. So we have a number of the execution percentage of the total execution time that they represent. And for each of those, we display the main issues that we identified, and we have an associated penalty score that's an estimation of the complexity that will be needed to fix it. And if we double click on the corresponding loop, it will open a detailed report of the loop. So where we try to be more explicit about the issues that we detected. So for instance, here the loop is probably not vectorized actually, and try to provide hints on how to fix that. So we provide hints at the compilation level, or some of the hints we can provide are also at the implementation level itself. So explaining also why some formation of some code constructs can yield to under-optimized code. Yeah, we can also provide actually, for instance, the flag I was talking about, the flag to optimize the code for the given processor, and various hints depending exactly on the type of processor and the capacities of the processors and the characteristics of the code that we identified. And for those interested to know what's under the hood, there is the expert mode when you can see all the internal metrics that CQA machine models relies upon to create these reports. So you can also get a look at the assembly code of your loop. You can see where it was called from. So that's an ID to know where it is mostly invoked from. And since we're in parallel, you can see also the time that these particular loops takes across the various threads of the application. So coming back to the main tab. So that was for the summary. In the global tab, we present a set of metrics that correspond to that are global for the application. So for instance, the execution time, of course, the time spent in loops, time spent in innermost loops, so basically the lowest level loops in a loop nest. So whenever there is this little blue bar here, it means we have some additional information that we can display. For instance, we detect that some useful compilation flags are missing, and so we display them here. And this tab here will display, let me just change that. This tab here will display the potential speedups I was talking about when I spoke of the what-if scenarios of the static analyzer. The idea is that we are trying to express the quality of the code by term of speedup if it was perfect, for instance. So if we had perfect flow complexity, that means no branches inside loops, because that is very bad for performance. Well, in that case, we will have a very low speed up because in fact, most of the loops have only one path. So basically, actually, the lower the speed up is it means the better the code actually currently is. And that's why it's in green when they have a low speed up, because it means there is nothing to gain here and the code is already good in these areas. And if we have a larger speed up, so for instance, here we see that if we manage to fully vectorize the loops, we could hope to have a 62% speed up. And if we click here, you have a list of the various loops ordered by decreasing potential speed up. And if you double click here, that will once again open the detailed report corresponding to this loop. Nope, sorry. So here below, there is a reminder of the experiment conditions on which computer did we run, which processor was that, the compilation option of the application, and yeah, number of processes that were requested, number of threads that were observed. A recap of the parameters you provided to OneView when asking it to execute the application. On this tab, you have some global metrics concerning the application. So for instance, here, we can see the time that was spent in the various categories of code. So whether we're spending time in the binary code itself, your code, the one where you want to be spending some times. But we can also see whether we are spending time in the MPI runtime, in the OpenMP runtime, or if you are using, for instance, math libraries, they would also appear here, and you can see the breakdown across the different threads. We have also the various POP metrics that Judith and Brian were talking about this morning that are also available. And various also here we can see, for instance, the external libraries that were invoked by the application. On the function tab, so this one presents the profile at function level. So basically, it's if you have been already used a profiler, you are familiar with such a view. You have the different function that we found in the application and the corresponding percentage of the total execution time. And here we also display the various POP metrics compiled for this function, and we can expand them. When they have this little triangle, it means they contain some loops, and you can see the time spent in these loops. And once again, if I double click on a given loop, I will open the detailed report for that loop. And this tab is basically the same view, only here we are also showing, we are focusing only on loops. So by default, we display only enormous loops or single loops, so those that do not contain any loops. We can also ask to have also the outermost loops, all loops. So here you can see various metrics. Essentially, we tend to focus a lot on vectorization. So the percentage of instructions that could be vectorized, and also the average length of the vectors that were used when vectorizing these instructions. Yeah, and once again, if I double click here on one of the loop, I will open the detail report. So this last level, this feature I'm about to show is not yet included in the, yeah, it's included, but you have to activate a special flag. It is by default now in the latest version, which will be released around November, basically. So now we can have a view of the various threads involved in the application. And we can also have a view on the topology on the various threads. So where the various threads executed on the various processors. So here I'm showing an example that was simple. I will switch to our repository to show a more extensive example. So that will be a bit more meaningful. So this is the kind of information you may want to see. If you are using multiple threads, for instance, you can see that there on which cores they had been executed and with which percentage. This is useful to catch any pinning errors, for instance. What can be useful to show on these larger reports? Yeah, we have this view here that allows to see the time spent in the hottest functions across all the threads on which the application was executed. So I'm showing here a report that contains more threads than the short example I showed, but that's useful to identify some threads where the behavior is different from the others. So another example I can show now is the scalability mode. So the idea is that when we're running the application in this in the one view with this mode, we will be running it multiple times with different parallel configurations. So here, for instance, we run it with various number of threads. And we are presenting the results side by side. So it is basically the exact same metrics than the one I showed for a single run, only this time you can just compare them and you can see how the execution time is evolving as we increase the number of threads. This metric here is essentially the speed up you would have if the parallelization efficiency was optimal, that tying back to the talk of this morning. So once again, the higher the speed up, the worse it is. So we can see here that up to this point, for instance, the scalability efficiency is rather good. And after that, in this line represent the ideal efficiency. After that, we are just dropping out of range. Otherwise, what else? Yeah, you can see also the various. Where is it? We're showing the value, how many functions, how the function more or less scales. So, for instance, this will be useful here on the loop tab. So it tends to be a bit crowded. Just let me. For instance, we can see the various efficiencies for the various loops, for instance. So which loops is behaving more or less satisfactorily, and it's a bit crowded here because I'm using a short screen, but yeah, the idea is to be able to see how the various loops scale across the various number of threads and processes that we requested. Apart from that, the remainder is more or less the same, but everything here has been extended to display the various the additional runs. Let me show another. So, for instance, I talked about the stability mode. So here is an example of what it looks like. It's simple but useful. We just run the application with the same identical parameters multiple times and performed a computation of the variability. So we have a view. The idea is to be able to catch how variable the timing of the application is, which can be useful before engaging in any operations. Which reminds me, by the way, yeah, for instance, it's also possible. I showed the load balancing at the loop level. Sorry, my screen just went blank. But we can also get the information at the function level. Sorry, my screen is switching on and off. But yeah, you can also get the information for its function, identify its load balancing. So this will be, for instance, useful if you are looking at an OpenMP function. We can see which of the various threads, how long it took across the various execution threads. And this is also something that we can find if we are looking, for instance, here we can see for each thread, we can open the detailed profile for that thread. So that's useful if we see some threads behaving differently. We can just decide to focus on those threads to see what happens there. So I went a bit fast, but it seems I still have 5 more minutes. So are there any specific questions? Okay, so let me show you here, for instance. So this one is a comparison, a reports comparison report. So basically, the scalability mode will run the application multiple times and aggregate the results of the multiple runs. But when we are using the comparison reports, we can aggregate different ones that were performed completely independently and just show them side by side. So of course, the difficulty here is that we may be dealing with completely different binary codes. So we may not have the same loops inside, possibly, or even possibly not the main code, but that will not be very useful. And the idea here is that we are trying to match the various loops that we identified inside the binary by their source information. So for instance, here we are comparing a same run, but run with different compilers. So here GCC or the Intel compiler. And we identified that these different loops corresponded to the same source loop. And as I was saying earlier, it is possible for have one single source loop correspond to multiple binary loops, depending on whether the compiler, for instance, if it's vectorized, it will need an additional loops to fill up the register and empty them, or it can have performed versioning depending on the properties of the loops. And so, for instance, here we can see that perfectly. For instance, in GCC, the single loop, sorry, not what I wanted to do. Yeah, the single loop corresponded to 4 assembly loop in the binary code, but Intel managed to perform additional transformations, and there were a lot more loops corresponding to the single source loops, but we're able also to identify that they correspond to the same source loop and so present them side by side. So this is what possibility. We can also, of course, present the same information at the function level. So that one is theoretically simpler because we can just rely on the function names. But as we can see, it can happen that some compilers are sneaky and will use different function names. Some codes actually can use different function names depending on the compilers used. Let me show, for instance, here. Yeah, this is the type of information we can see. So here I'm showing another comparison report, but that is this time performed across different architectures. So it was a comparison between Intel and ARM. And we can see the comparison at function levels, for instance, comparing the various functions because here this time we can detect that the names are identical, and we have also the same type of comparison across the different loop versions. And the global tabs allow to see side by side how the different code perform, so that can be useful if you want to compare, for instance, with different data sets, different compilation options, different architectures. So, are there any questions? So you can check the Macao website we have. So the latest version of Macao is available. So as I was saying, we will release a new version probably around November. There are various tutorials explaining how to, for instance, how to execute one view, how to fill the various options, and how to read the generated reports. And for those interested, you can also have a list of the various papers and publications that were made around Macao. We had a few theses and papers around that. And with that, I think I'm okay. I thank you for your attention. And if you have any question, we still have a minute or so. Okay, so I think it's good.
Yeah, thanks, Cedric. If you release the screen, then I think that Jose can share his now.
Yes, I'm going to share now.
Yep, I see it.
Right. So, hello everyone. I'm José Margado, and today I'll be presenting you the CARM tool. Starting with a bit of introduction and motivation. So as you may know, modern high-performance computing systems are becoming increasingly complex and heterogeneous, which results in them becoming harder to understand due to so many differences in implementations and architectures, which leads to an even harder time when attempting to optimize applications for those systems. So with this, we need something like an accurate but also easy to understand model that can facilitate the application optimization process for different systems. And this is the main appeal of the CARM model, the cache-aware roofline model. It provides an easy to understand and accurate performance overview, along with some good optimization hints for your profiled applications. However, the main problem here is that the CARM model is only supported by Intel Advisor, which limits its potential users. So this is the main problem that the CARM tool attempts to fix, to port the CARM model to other CPU vendors in an open source format, specifically AMD, ARM, and RISC-V CPUs, alongside the support for application analysis in the scope of the CARM, and finally combining all of these functions in a single tool, which is the CARM tool. So this is actually a complicated process because in order to build the CARM model for a CPU, you will need some tailored micro benchmarks that can take full use of the CPU memory system and its floating point units. So this requires having a good understanding of the different underlying architectures and the ways to maximize their utilization. And at the end of this talk, I'll show you some more experimental results obtained with the CARM tool, such as a CARM-based architecture and application analysis. But now, talking about the CARM itself, so how does it actually work? So the CARM has two main roofs, these sloped roofs in red, which you see here, which are based on the maximum bandwidth of the different memory levels of an architecture, and then the flat roof in blue, based on the peak floating point performance of the architecture. So these roofs designate two main areas of the CARM model below them. So this is the memory bound area in red and the compute bound area in blue. So what we do with these areas is that if our profiled application ends up, for example, in the memory bound area, like the first point in this graph, the CARM model is basically indicating to us that we should first try memory-related optimizations in order to see the best performance gains. While if we fall on the compute bound area, we should try to improve the utilization of the arithmetic units of the CPU, for example, via vectorization of the arithmetic operations when this is possible. And finally, if we are in the mixed area, then both strategies should be considered. However, to build the CARM properly, we must use micro benchmarks in order to get a realistic sense of the maximum performance of the CPU, instead of relying on possibly unachievable theoretical values. And so this is done via memory micro benchmarks to determine the maximum bandwidth of each memory level, and floating point micro benchmarks to determine the peak computational performance of the CPU. So the main objective of the CARM tool is to fully automate this process via the automatic generation, execution, and measurement of these assembly micro benchmarks that can fully utilize the target system to build the CARM model on any platform. So here's a general outline of this presentation. So now I'm going to go into the CARM tool itself, then move on to some results, and finally the conclusion. And I will also switch from the slides sometimes to show the different features of the tool live. So now in this section, I'll give you an overview of the CARM tool, starting with a high-level view of its functionalities, like the graphical user interface, the automatic benchmarking, and the application analysis, and then with some more detail on some more important parts, like the benchmark generation, frequency measuring, and benchmarking itself. So starting with the high-level view, the CARM tool can be described through its various independent modules, which implement each of its main functions. So to utilize the tool, you can use both the command line or the graphical interface, and from which you can then start the necessary benchmarks to obtain the CARM for your system and other types of benchmarks. And besides that, you can also then perform the application analysis via either performance counters or via dynamic binary instrumentation. So currently, the CARM tool supports most vector extensions of the main CPU vendors, with the only exception of ARM-SV, which is a work in progress. So with this, I mean that the CARM tool is capable of generating the assembly micro benchmarks that can make use of these vector extensions when they are available in the system. So now this overview here of the high-level modules, which are implemented by the various files present in the source code of the CARM tool, I'll now give you a brief overview of what each of these modules does. So starting with the graphical user interface, here you can, this interface runs on your browser using the Dash framework, and as you can see, it can be used for some result visualization of both CARM models and the application analysis in the scope of the CARM. And you can also launch the CARM benchmarks directly from the GUI using the sidebar. And finally, you can also start application analysis in the interface itself. And now for a quick demo, I will switch to the interface here in another tab to show you. So basically, to start up the interface, it's a very simple Python script, which you just call. So I'll call it now, and then you will receive a link to open in your browser, which I have over here. So basically here we have the sidebar, like I just showed you, and from here you can run your CAM benchmarks. You can configure them however you'd like. You can select different ISA extension, different thread counts, precision, floating point precision, load store ratios, among other things. And you can also just let it run the default settings by simply clicking the run CARM benchmarks. And what this will do is then show you some intermediary output here in this terminal, where you can get some of the information, for example, the detected ISAs supported in your CPU, the different cache sizes, and the tests that it will be performing. So in this case, the default is to run double precision tests for all your available ISA extensions for one thread. And it started one right now, and it's actually finished the first one, which is an L1 benchmark. So I sped this up to make it easier for the live demo. So basically here you can get some metrics about your L1 performance in this case, like bandwidth, bytes per cycle, instructions per cycle measured, among other things. So then you can also, I didn't want to pause that actually because, sorry. So anyways, then you can also run application analysis. And I'm just going to refresh this because I didn't want to stop the script. But anyways, here you can also analyze an application. So for this, you just need to provide the executable file path and the arguments that it takes. And then you can select from the different options we have. So in this case, I will input a name here for a machine, which then correlates with the CARM results that I already have stored. And you can do DBI without the region of interest. And in this case, you don't need to do anything to your code. You just need to have the executable and everything will work. And then for the region of interest, of course, you need to mark that region of interest in the source code before compilation. And that's what I will select now. And I will leave this running an SPMV application that in this case takes matrix input in the arguments and the number of iterations. So I'll just leave this running in the background. And as you can see, it started up over here. So I'll let this be for now. And then to see results themselves, when you open here this dropdown, it will automatically check your results folder and see what you have. So I'm going to open the ones from my laptop. And in this case, then here you can select the different settings you want from the results you have. So in this case, I have a lot of results stored with different thread counts and different precisions. And you can select up to 2, so you can compare the performance of different settings of benchmarking. And then you can also plot some applications that you have analyzed with the CARM tool or the results of some other benchmarks. So for example, here we have some results from an application and also a benchmark, and they will show up here as dots that you can then use to your advantage via the optimization hints that the CARM model gives you. So with this, I will return now to the slides. And now I'll talk more about the automatic benchmarking part. So this part, first, to facilitate the utilization, the CARM tool automatically detects the more important aspects of your system, like you just saw now with the cache sizes and the available ISAs. And this is done via the configuration folder where we have some files to run these detections. This includes things such as, for example, the maximum RVV vector length in a RISC-V system, among other things. And then these details are used to generate the different benchmarks to build the CARM model. So as you can see in this GIF, with some examples of different micro benchmarks that can be generated for different ISAs. And this is coordinated thanks to these 2 modules, which I'll talk in more detail later. So finally, I will also give you an overview of how the application analysis is implemented. So this was done via the integration with other performance tools, such as PAPI, DynamoRio, and IntelliSDE. So starting with PAPI, which allows us to access the performance counters of the system, we take advantage of the high-level API from POPI, which allows us to define a region of code to be analyzed, and from which then we extract the necessary performance events to plot an application in the CARM. And then for the dynamic binary instrumentation, we use either Intel SDE or DynamoRio, and we also developed a way to automatically interface with them and define regions of interest from which we obtain a breakdown of the executed opcodes in your application. And then we use those to calculate the CARM metrics like the gigaflops and the arithmetic intensity so that we can plot your application in the CARM. And this last integration is facilitated by the DBI CARM ROI header file, which contains a simple API that we developed to interface with both DynamoRio or Intel SDE to define the regions of interest. So now I will also quickly show you how you would do this yourself. So for example, if you wanted to profile an application, here I have a simple SPMV implementation. What you would have to do is simply include the DBI CARM ROI header file, and then you can start right away by using the CARM ROI begin and CARM ROI end functions to define your region of interest, then just compile normally and feed it to the GUI just like I did before. And of course, you can also do this with POPI. So in this case, you include POPI, and instead of CARM ROI begin, you use the POPI high-level region begin API functions. And as you can see from the terminal here, we already finished the DBI analysis, and what we get from this analysis is not only a breakdown of the different opcodes organized by their categories of memory, scalar, scalar integer, we distinguish between most. We also get then the total floating point operations measured, the execution time, gigaflops, bandwidth, and arithmetic intensity. And then this will now automatically show up here in the UI if you just refresh. So for example, if I go back here and just select these two, here it is. So it was at 13:30 that it finished, and this SPMV example was the one I showed before, which is all the way down here. So it's very memory bound, as to be expected of these kind of applications. But yeah, so now what I will do is show you a small example of how you can see some speed up here. So for example, since our problem is mostly memory, I'm gonna re-execute the application analysis, but this time I'm gonna use an RCM reordered matrix, which takes better advantage of the caches here. So for that, I just launch again the same application. I just switch my matrix. You see now that was the RCM one, and now I just need to grab the path, and again use the same name here, and I will leave it also running, which actually it should be quite fast. So it's already started here. So first we do a timing test because the DBI does incur some overhead in the execution time. So timing test is done now. So now we are running for the opcode data. So this is the part that incurs some overhead from the DBI process, but it's also quite fast when you have a region of interest like this. So as you can see, we got some more gigaflops. It will be more noticeable when I now refresh this so that we can see it. So here, let's see. So this is the new one. This is running on one thread, so that's why I'm comparing with one thread results. So as you can see, our new function, our new application here is now quite higher. So it looks like about 2 times increase that the RCM reordering helped us. Of course, there's still a long way to go with this, but this is just to give you a quick idea of it. So now I will switch back, and now I'm going to talk in some more detail about what was done to allow for the support of different ISA extensions in the CARM tool. So this starts with the automatic generation of those micro benchmarks, and they follow a similar general structure for all vendors, but they are then adapted to the limitations of each ISA. And then that's followed by a frequency measuring step, and then some preliminary timing tests to ensure stable results, and finally the benchmark execution itself. So all of these steps are implemented by these various files you see here. And I'm going to start with the benchmark generation in the blue module. So the benchmark generation model, okay, there we go. So the benchmark generation module is implemented by these various C files, which have as a final product these various benchmarks you see here. And these files store different assembly instructions and registers used by each ISA that we support to automatically perform the necessary calculations to generate the assembly code that can respect the specifications of the user. And most benchmarks will have an inner and outer loop, as you can see in this GIF, in which the inner loop contains a fixed number of iterations to ensure that we perform the specified number of instructions, while the outer loop can be adjusted externally, which allows us to vary the execution time of the benchmarks. So I'll quickly show you this in action by starting up some benchmarks with different specifications, and you'll see how the assembly code changes right away. So for this, I will go here to this file, which is where we store the actual assembly that will be executed during the benchmarking. And now if I bring up a terminal, just to make the switching easier. So this is also, you use it for the command line. So to run benchmarks, you just call the run.py script. This is just the verbose flag, so we get a lot of information. You can then select what instruction you want. The default is to do add and FMA, the ISA that you want, and the test that you want to do, and then the name, and you have some other options like threads. But yeah, so now I'm going to do a scalar L3 memory benchmark. So this will now change everything. So now we are just changing the assembly to use the scalar instructions. And now, for example, I'm going to change it to be a floating point test using AVX2 and FMA. So in this case, you just start it up. And again, we get this change here, and this is now what is being executed. And finally, you can even mix the memory and the floating point. And in this case, I'll do a mixed using SSE, which will now spawn us some code that is mixing both the fmed instructions and the movupt, which are the memory instructions. So this does not need any assembly knowledge. As you can see, you just need to specify what you want to test and run. And you can even add your own ISA configurations by specifying the different registers that you will be using, how many of them they are, and the instructions that you want to run. However, this part is not yet fully automated, but it's in the works so that you can quickly add your own ISA to generate the benchmarks. And so that concludes the part of the benchmark generation. And so now the next step will be the frequency measuring. So in this one, this measurement is actually based on an assembly function too, with a series of dependent additions, as you can see here for the different vendors. This leads to one instruction per cycle execution, which then by knowing the number of instructions performed and the time taken, we can then obtain the frequency of the CPU. And using this method, on all machines that we have tested so far, has showed under 1% error from what we were expecting. So, for example, the maximum speed of the underlying CPU was almost always achieved, no matter the architecture. So, to measure the time taken by this execution of this function, we use the timestamp counter in Intel and AMD CPUs, and for ARM and RISC-V, we use the clock@time function. And so now to finish, after generating the benchmarks and measuring the CPU frequency, we are now ready to start executing them. So all of this happens in the main test.c file, which coordinates the creation of threads, memory allocation, frequency measuring, and benchmarking. And as I mentioned before, the CARM tool first will run the benchmarks to determine how long they will take, to then adjust their execution time via the outer loop to ensure that they last enough time to produce stable results, but also don't take unnecessarily long times. And then finally, once this is done, the tool then actually executes the benchmarks 1,024 times, and then the best run is selected, from which the bandwidth or peak gigaflops values are calculated. And this concludes the overview of the tool. So now I'll talk about some experimental results that were obtained from using the CARM tool. So this includes, like I mentioned, the CARM-based architecture analysis of different vendors, a comparison with Intel Advisor, and the analysis of an SPMV application using the CARM tool. So starting with the machines that were used to obtain these results, We have one from each vendor, and these are the Venus machine with the Skylake X CPU that implements the SSE AVX2 and the AVX512 extensions, the Cara machine with an AMD Zen 3 CPU, which implements SSE and AVX2, and the ARM-Q machine with the Vulkan architecture with the Neon extension, and the Milk5 machine with the RISC-V system that has RVV 0.7.1. So besides that, the CPUs of all machines have 2 floating point units per core and between 3 and 1 load store units per core, which are used to define here the theoretical limits of each architecture, which I'll now go over. So starting with the memory side, for that I will use these bandwidth graphs that show how the measured bandwidth and the instructions per cycle change as we increase the amount of memory used in our tests. So this graph is also generated by the CARM tool and uses the same benchmarks that are used for the CARM generation. Starting with the Venus machine, we can see that we stayed slightly above 2 instructions per cycle, which is quite low compared to the expected 3 instructions per cycle that the 3 load store units should be able to support. However, this limitation is also reported by Intel, which in their hardware optimization manual also specify that the Skylake X architecture is only capable of sustaining around 2 memory instructions per cycle, which matches correctly with our results. Then in the Cara AMD machine, we did reach the expected 3 instructions per cycle with a load store ratio that best matches the 2 load and 1 store units of the Zen 3 architecture, as you can see. And we can also even confirm the presence of this exact number of units, since in the load-only tests, we only reach 2 instructions per cycle, and while in the store-only tests, we only reach 1 instruction per cycle. Then in the ARM-Q machine, we also reach the expected limit of 2 instructions per cycle, and again we can see that only one of the units is capable of performing stores, since we only reach 1 instruction per cycle in the store-only tests. And then finally in Milk5, we reach the expected 1 instruction per cycle, while in the store-only tests, we have some unusual behavior where we maintain around 0.5 instructions per cycle until 16,000 kilobytes. And from where we have found this is likely due to an adaptive write allocate policy that this RISC-V CPU implements, which actually deactivates the write allocate when multiple stores are detected in series, which ends up bypassing the cache levels. So that's why we don't get the expected slowdown as we move along the cache levels. So to sum it all up in this table, we can see that it was easier to achieve the expected values in the memory levels closer to the CPU. And in the case of the ARM-Q and Milk5, there were really no realistic theoretical data with which to compare for these levels. So for example, the cited theoretical L2 bandwidth value for the ARM-Q CPU should allow for 4 instructions per cycle, which is already twice as much as the load store units in this architecture. So now moving to the analysis of the computational capabilities. For this, we use the CARM itself for each system, which defines, like I said, in its flat roof, the peak gigaflops obtained during benchmarking. And here I also added the instructions per cycle measure to compare with the theoretical limits. We also check the performance obtained from mixed benchmarks that mix both floating point and memory instructions at the same time to see if we can stay close to the performance roofs of the CARM, which are these various dots that you see here in the plot. So starting with the Venus machine again, we nearly obtained those 2 instructions per cycle for both AVX512 and Scalar. However, the mixed benchmarks also stayed relatively close to the CARM roofs, except for the AVX512 FMA, which reached a 25% deviation. And then in the CARM machine, we also accurately reached the 2 instructions per cycle expected, but the mixed benchmarks, again, some remained very close for the addition instruction, but then on the FMA side, we got up to 10% deviation. Then on ARM-Q, we again reached 2 instructions per cycle, but the mixed benchmarks here do not perform as well, getting a 17 deviation on Scalar and then a 25 on when the Neon instruction set is used. And finally on Milk5, we again obtained 2 instructions per cycle, but we also get some smaller deviations with the highest ones being from RVV. So basically, the floating points limits were easier to achieve in all of the architectures, as you can see from the table that sums up the deviations. But however, the mixed benchmarks show that when you stress the memory and computation, you can have some pipeline conflicts that can lead to some slowdowns, particularly with more complex floating point operations, such as the FMA instruction, and when ISAs with bigger operands are used. So now we also compare the AVX 512 results of the CARM tool with Intel Advisor, which is here in red, and the CARM tool in black. So as you can see, we managed to get some similar values for floating point and L1 roofs. So around 222 gigaflops for single precision FMA and 479 gigabytes per second for the L1. However, Intel Advisor obtained some considerably higher values for L2 and DRAM with 216 and 17.2 gigabytes respectively. But this is mostly due to the fact that Intel Advisor adapts its load store ratio to each memory level to get the best possible results, while the CARM tool always employs the same load ratio across all the tests for consistency. So for example, if we configure the CARM tool to run some load-only tests on the L2 level, we can again match the results obtained by Intel Advisor, and the same thing for DRAM. So we can still match the expected performance. And so finally, to demonstrate the application analysis functionality of the CARM tool, we analyzed an SPMV implementation using the Eigen library in the Venus and ARMQ machines to compare the difference in the implementation of SPMV by the Eigen library in different architectures. So besides that, we also tested the impact of using an RCM reordered matrix, which I showed you before here in my laptop, in the performance of the SPMV execution. And as we can see, also the Venus machine obtained more gigaflops in ARMQ, which is expected due to its superior CPU. That this can also be seen from the higher CARM roofs in black that belong to the Venus machine versus the ones in red from the ARMQ machine. But besides this, we can also see a discrepancy between the arithmetic intensity of both machines, which indicates to us that the Eigen library might implement SPMV differently in ARM and Intel architectures. But now, looking at the performance difference between the original matrix in blue and the RCM matrix in green, we can see, like we just did in the live part, that the RCM reordering basically doubled the gigaflop performance of the SPMV execution. And besides that, in the CARM machine, we only managed to perform DVA analysis since we did not have the necessary permissions to access performance counters. However, this was done for the Venus machine, which corresponds to the dots outlined in red here, while the DBI analysis corresponds to the dots outlined in black. And here we can see that both analysis methods managed to obtain quite similar results with only slightly discrepancies, even though they are very different approaches to performance profiling. And so now that we have reached the conclusion, but before that, I'll just give you a quick showcase of how the different ISA extensions and memory levels used can affect performance. So for this, I'll switch to the GUI again. And here I'm going to clear this. And I already have ran here some different mixed benchmarks, not to take up too much time during the demo. So basically starting with a scalar DRAM benchmark in this case, we can see that our dots over here is completely exploiting the maximum performance possible by when using addition with scalar. So if this were your application, the only way to improve your performance would be to try to vectorize your code, in this case with AVX2, for example, which is what brings me to the next benchmark that I have here, which was the same thing, but using AVX2, so it's still DRAM. And as we can see, now we hit this roof here, this black dotted roof, which corresponds actually to the DRAM limit of the system. And now again, if this were your application, you would want to do some memory optimization that should allow you to take more advantage of your caches. And to simulate that, I just have here the same benchmark, but now targeting the L1 level. And as you can see, it will show up over here, this new dot that is now maximizing the possible performance when using the add instruction. And again, as a last step, in the cases that it is possible, using the FMA instructions can result in an even higher performance, which is what I just selected now. And as you can see now, we fully reach the peak performance possible from the CARM roof. And this also results in twice the arithmetic intensity. And this is because I actually kept the same ratio of floating point to memory instructions. But as you may know, the fused multiply add instruction performs 2 floating point operations per instruction. So it results in twice the arithmetic intensity. And so now I will finish by just briefly mentioning the CARM tool GitHub and its paper. So the CARM tool is open source and available on GitHub. And we also have an accepted paper about the tool, which will soon be published to ISWC 24. And finally, the CARM tool is the first and of hopefully many tools to be developed in the scope of the CHAMP Hub, which is the Heterogeneous Computing and Performance Modeling Hub created by INESC. And with this, I conclude my presentation. So if you have any questions, feel free to ask.
Thank you, Jose.
All right.
Okay, so those were some of the other tools that we're not going to be working with in the rest of the workshop. They're part of the POP Centre of Excellence, and if you're interested in them, then there's a chance to get some additional studies using them as part of the POP services. And I think that there's work in progress to get them installed in Carolina and on the other systems, but I think only the tools from RVTH are currently installed. So I think we have essentially reached the end of our presentation part of today's part of the workshop. After the break, we would be continuing with a chance for the people who have accounts on Carolina to do some to get some hands-on assistance. So we have some example codes that you're welcome to try out if you don't have codes of your own. If you have your own code, then it's would be good to let us know some details about it so that we can prepare as necessary for tomorrow and for Friday. Those of you who don't have codes, who are not with accounts, then we would see you and see everyone again tomorrow morning when we would continue with so the focus tomorrow would be on looking at MPI and OpenMP, things running on the Carolina CPUs. And then on the Friday, we would go into some more advanced material and look at using the GPUs and performance analysis of GPUs as well.
So good morning, everyone. Thank you for coming today on time. I suppose some participants will join us later, but I would like to just welcome you for the second day of our workshop, and would like to remind you that the tutorials are being recorded. So today it's the morning sessions that will be recorded. And with that, I will just pass the speech and the presenting to our first speaker, which is Judith today.
So good morning. So today we are going to present the tools during this morning, and we start with VSC tools. So basically yesterday you already have seen some pictures of some captures of VSC tools, and today you have to better understand all of them. So I typically name my presentations Understanding Applications with Paraver, because I think, as I tried to start expressing yesterday, that is very, very important to understand things. It's not a matter of just knowing what's deficiency, but understanding why I get that deficiency, okay? And it's important, this understanding, because it allows me to go to the right path. I will show you some examples during this presentation. This presentation should last approximately a little more than half an hour, no more than 40 minutes, and then we go to the demos, okay? So be patient. This is just to recover a little bit on the tools, and then we will start to show you live demos of the tools. So my first slide for many years, let me try to go to the first slide. is this one here, okay? And I hope you will agree with me that as humans, we are visual creatures. The ability of our brain to work with images is quite powerful. Even when we do not want to find a structure in images, we are able to find them. It's very easy to extract information from images, to memorize things from images, and to identify patterns. In fact, this is something our brain loves to do, is to identify a structure. You look at the clouds and you start to see structure, even if it's not there. Okay, you look some stones and you find a structure, if it's not there. And if I ask you, what do you see in this picture? What do they have in common? This cloud, this rock, and the moon, okay? Well, I hope many of you will see it, okay? But for sure, when I tell you I see rabbits, you will agree with me that they are rabbits, okay? They are not real rabbits, but you know how a rabbit looks like. You know the structure, the shape of a rabbit, and you are able to match that structure here, okay? So the idea of having this slide is to start saying that we can have tools that use this ability of our brain to find a structure, to understand, and to process images. And it's simple, it's kind of a game. You start with simple images and you learn how to read them. Once you have this ability, you can master it and you can improve it, and you can able to very quickly, more complex images, identify the structure, identify the pattern, identify the meaning of that picture, okay? So that's the goal of VSC tools, is to work with images, detail images, and identify the structure. VSC tools were developed early 90s, so long past since then. And we are proud to say that the basic core and the basic approach of the tools are the same for so many years. So things have changed a lot. There are huge changes in applications and platforms, but the core ideas that were initially developed are still useful. And for sure, we have also been evolving, and we have also been adding more tools along the years. So those tools are based on traces because, as I said, we wanted detailed pictures. And in order to have detailed pictures, we have to have details. And those details are captured in the traces, okay? The tools are open source. You can download it. You can play with them. You can install it. You can modify them, okay? So, and the structure of the tools is we have Extrae. Extrae is our camera, is the one that takes the pictures. And you will learn how to use it today. And this, let's say, this is just capturing data. And then we have Paraver, that is the main core tool, that is a visualizer, is a post-mortem visualizer. And DMMAS, that is a what-if simulator, it's a message passing simulator that we will also see in this presentation. And this presentation, the other topic I want to mention are the performance analytics modules that were the ones that were more recently created, maybe for the last 10 years, okay? So in this presentation, I will cover everything except Extrae. Extrae will be part of the live demos where you see how to use that camera, okay? So as I already said, our focus is on the detail because we believe that the variability express the issues of the parallel applications, and we consider very important to have flexibility. You will see that our tools are very simple, but also very flexible. We work with visual analysis because, as I said, our brain are quite powerful working with images. And during the last years, we developed, from now on, there are so many years, but around 10 years, we have been developing what we name performance analytics, that are modules that are data analytics modules applied to performance data. You will see some of them today, but you will see more of them tomorrow. Okay, today in this presentation, you will see some introductions, but you will be able to use the ones that work on the hands-on tomorrow. The ones that are keeping on the morning, you will see the demos. And one thing that when people tell me, okay, what's the difference between your tool and other tools, okay? I think one of the more important, all tools are useful, and in fact, the best tool for you is the one that better fit your needs, okay? But one thing that I think is maybe the most relevant difference between our tools, VSC tools, and other tools is that we base the analysis on the behavioral structure. We are driven by the behavior, while most of the other tools are driven by the syntactic structure. What do I mean by that? Many tools, and I understand the reason for that, associate the metrics to the code structure, to the syntactic, to the user functions. And that's very important because that facilitates that user that knows the code and knows the meaning of that function can correlate the metric with that function, okay? But what we do is we base on the behavior, and the reason to base on the behavior and ignore the syntactic structure is because we want to understand when we go to the parallel runtimes, what is our behavior. And you will see that on the examples, but basically we want to distinguish if, let's assume I have two functions, A and B, and they do the same thing. Why do I need to distinguish them, okay? They may be unbalanced, but if they compensate and when you call to the parallel runtime is when you are unbalanced, then I don't care they are unbalanced, okay? So the behavior is driven by the calls to the parallel runtime. As we saw yesterday in the model, okay? Useful is computations, parallel runtime is the overhead, and then I can identify the regions based on the useful time, okay? And maybe the most important example also to drive by the behavior is that, let's assume I have one function that every 5 iterations do some extra computation. And I have seen that in some cases in real codes. And the reason for that is that extra computation is expensive. So it's only done one every 5 times. So what happens if I accumulate by the function? I will say that the behavior is the average. And in fact, the average never happens. You have 2 modes, the short one and the large one, okay? And that can happen a long time or that can happen across processes, okay? So that's a benefit of basing on the behavior is that I ignore the syntactic structure. But for sure, I recognize that they had some benefits of using the syntactic structure. So we also have some path to correlate some data to the syntactic structure. And the final focus of this application, as I said, is to keep simple and to identify the key factors and then to work with them. And examples for that are the efficiency model we have seen yesterday, but also DMMS. When you saw how DMMS work, you understand this idea of working with the key factors. So let's start with Paraver, okay? Paraver is a performance data browser, but in fact, it's a data browser that is being used mainly for performance data, okay? During the execution of my application, I capture what we name the raw data. With my camera of Extrae, I capture the raw data that is basically timestamp information. It's a trace file, okay? And based on that raw data, I load it in memory to do this analysis. And I can compute only 2 types of view, quite simple, okay? So I keep simple, but it's, as you will see, it's quite powerful. I have timelines. We have seen already that yesterday. So I have time on the X dimension. I have on the Y dimension my objects. And that object may be my MPI ranks, my OpenMP threads, the CUDA devices, but it also can be the nodes. It can be the full application. I can compute a metric for the full application, okay? And from that timelines that are a long time during my execution, what I did, and maybe this is one of the first images you see, but you saw some of them yesterday from Paraver, but you can already find the structure here, okay? I see at the beginning, at the end, some like blue, but then I have a repetitive pattern that happens 3 times, okay? And I see this repetitive pattern has also some internal structure. I see 3 times this kind of bluish and pink region, and then the orange, and this is repeated, okay? So I don't know what it means, but I already find the structure, okay? And from those timelines that are based on time intervals, and I can zoom and detect what is the time interval that I'm interested in, I can compute tables. And with the tables, what I do is I ignore the time interval and I collect the data, okay? So basically, this is more to visualize, this is more to measure. And as we will see in the next slides, I have different flavors of tables, okay? But let's keep that for the next slide. So the goal is to have flexibility to compute those metrics. So the tool doesn't know how it is MPI, doesn't know what is OpenMP, doesn't know what is a CUDA call, okay? But can work with anything of that, okay? So the benefit is that Then if tomorrow you tell me, if today you tell me, okay, I have a new programming model, I am generating your traces, can I use them Paraver to work with it? Sure, it's ready. You just need to load it and you can program it. To keep it simple, instead program it, you can save the data of the programs and then you reload the images very easily, okay? But then supporting new scenarios for Paraver is very, very simple with this flexibility, okay? And also, it's not only new programming models, but also new bottlenecks, okay? I don't need to do any change if there is a new bottleneck. I need just to learn how to process that data and to detect the bottleneck. One of the easiest scenarios for Paraver is doing a comparative analysis. The idea is I load multiple traces, I can synchronize the scales, and I can see the differences, okay? And this is typically is maybe the easiest approach when starting is I want to look, let's say if I check what are the IPC or the MIPS of my application, maybe it's difficult to know if I should be happy or not. But if I increase the number of processes, I can check if the IPC improves or not. I can check if the duration of the calls are enlarged or are shorter, okay? So I can do this kind of comparative analysis. And in fact, you will see that in the demo, driving the analysis also with comparison, for instance, with the scale. Last thing, we load the trace file in memory. It's an iterative tool, so we want to be fast replying, so we work with the data in memory. So we need to load the trace, and this means Paraver is limited by the size that can be loaded in memory, okay? Despite this is becoming longer along the years, okay? Many years ago, we developed trace manipulation tools. We will see a little bit in the hands-on today, sorry, in the demo today, and we will also see one slide of it, okay? But the idea is that I can filter traces to get shorter things that either keeps in memory or that ignore the traces I don't want to analyze, okay? For instance, today it will be used to focus on the focus of analysis. So I cut the trace and I get a trace that only have my focus of analysis. I do not want to have initialization and to have to redirect every measurement to that region. So let's start with the timelines and with the tables to read them, how to read them, okay? So there are, in fact, the timelines can be classified in two main flavors. The first one is when my metrics is a category, like the MPI calls. I have a limited number of MPI calls, despite it's a large number, I have a limited number of MPI calls. In that case, typically what we do is we display those metrics as a code color, each color representing a different MPI call. So if I tell you those are the MPI calls, okay, and then black means outside MPI, mine means computing, you can see, okay, my application spent a relevant time in MPI, but there is also quite a large number of black, okay? Then I see processes that are doing MPIs while others are running at both corners, okay? And then also at the middle. And then I see some structure. I can count even the iterations. But if I want to measure things, the best thing is to compute a table. So clicking on a button, I get this table. As my metric was a category, what I get is a profile. I get a column per MPI call, and I can get a metric. With that metric, I can have the reference, what I was not able to see here, okay? And for instance, what I see is that there are processes that spend 42% of the time computing, while there are others that spend 74, 72, okay? So I see two flavors of processes, and I can see the different MPI calls, what is the percentage of time, okay? At the bottom of these images, I have some summaries for the columns that you will see that are quite useful, and you will see that on the demo. But as I tell you, we work with images, and this image is not, with the numbers, is not so scalable, it's not so easy to read, too fast to read, so I can put that on zoom mode, okay? And even here, I don't see the numbers. Well, I will see the number if I move my mouse around it, okay? I can clearly see the most dominant execution, the most dominant time is the outside MPI is computing, so that's good, okay? Even I saw that in average, it was not so big because there are some processes that are smaller computing, small time computing. I see also that for all the MPI for many of the MPI calls, there are 2 different colors on each column, okay? Meaning that there are 2 different trends. And in fact, there are MPI calls that are only called by some processes, okay? Some MPI calls that are called by some other processes. And basically, this is telling me my application is not SPMD, it's not a single program multiple data because different processes has different MPI calls, okay? Well, if this was a very, very small region, then it may not be the right answer, but as these are many iterations, then that's the answer. But what happens if my metrics cannot be a category, it's a continuous metrics? Like useful duration that I think I already mentioned yesterday a little bit, this is one of the most important metrics for us in our tool. The useful duration is the duration of a computing burst since I left the parallel runtime until I'm back to the parallel runtime, okay? I go back to MPI to keep it simple, since I left the last MPI call until I go back to the next MPI call. And this metric is very important because basically it's expressing if there is balance or not, if stress is expressing also what is the granularity of my computations, okay? And these continuous metrics in Paraver are expressed as a Paraver gradient that goes from light green to dark blue. The darker, the higher, okay? So if I want to read this image, I see there are 2 trends of behavior. The light one is very small, okay? And seems quite uniform. And then the biggest one, the most important one, because it takes more time, that I see some guys are darker and some guys are lighter, okay? If I want to measure, again, I will click on the same button, and in this time, I will get a histogram, okay? The histograms are a little bit more difficult to read. You have to get used to it, okay? But once you learn it, it's simple. And in this picture, I tell you that because that depends on the metrics, the color expresses the relevance. So the darker, the more important. And what I see here, if I start with the darker points, I see some shape, some kind of waves. So this guy takes more time in the computation. This guy takes less time. The timeline tell me this happens at the same time, okay? Then I see these vertical lines. Vertical lines are showing good performance because meaning that if that happened at the same time, all the processes will last the same amount of time. So when they enter the parallel runtime, the overall deck will be ready and there will be no delays waiting to each other, okay? But this pattern that is far from being a vertical line is expressing this imbalance that will be paid as MPI waiting time. And in fact, this picture is a real case for too many years ago, but I think it's so nice to learn about it that I keep using that in my slides for so many years, okay? This was the developers of Competence Centres many years ago come to Barcelona because they have seen the time in MPI was increased, so they were considering to do overlapping of communication and computations. To answer that question, the right tool is DMMAS, and we will see that in a few slides. But let's see what Paraver can tell us about this code, okay? And we have already written this picture saying my main computing phase is unbalanced, okay? With that information, I need to keep asking myself questions to answer and to understand why it is unbalanced, okay? So I have, in this case, this is a SPMD code, so all of them are executing the same region of code. What can be the reason that some of processes taking longer than other, okay? Well, maybe the most intuitive reason is because they have a different amount of work to do, different amount of instructions. I check with instruction counter. And focusing on the dark points, I see variability. These guys do this amount of instructions. These guys do more instructions, less instructions, more instructions. So there are trends, okay? There are variability on the instructions, but it's not the same. It's far to be the same shape, okay? So if it's not the same shape, means that it's true that there is imbalance of instructions, but it's not the only reason to justify that there is this time imbalance, okay? So I keep asking myself questions. I then say, okay, what can explain that I have 2 guys that they do the same number or almost the same number of instructions, but they have so different duration, okay? Well, if it's not the amount of work, then it's the speed that work is being executed. I check with VI-HPC, instructions per cycle. And I focus on the dark points, and I see this wave of variability on the IPC. Okay, so the combination of the variability of the IPC and the variability of instructions is the one that explains this duration variability. Okay, so I have the two problems. My instructions are, my work is not balanced, but also they are not running at the same speed. And I need to ask more questions to understand why two guys that execute the same number of instructions can have different IPC. Well, in many cases, this is related either to the type of instructions or more frequently to the access to the data. I check level 2 miss ratio, number of level 2 catch misses per 1,000 instructions. I focus on the dark points and I find this kind of wave. Okay, that is somehow quite similar to the one I see at the level of IPC. For sure, it's just, let's say, opposite, because when I have more miss ratio is when I have lower IPC. Okay, when I have less miss ratio is when I have more IPC. Okay. But then with this, only these 4 pictures, we can say, okay, don't waste your time doing asynchronous communication. Your problem, your MPI time is caused by imbalance. And this imbalance has 2 different natures. One of them is the amount of work, the instructions, and the other one is the access to the data. The variability in these 2 accesses is causing you this problem of imbalance and this time inside MPI. So they go back home, and after 6 months, they came back with a new version. These pictures are on the same scale than the previous one. And you see now the most frequent duration is almost perfectly balanced, very close to perfectly balanced. Is very perfectly balanced at the level of instructions, very small variability on the IPC, and the level 2 miss ratio has been not only balanced, but also reduced significantly. Okay. And I think for me, that's a great example that if you know, if you understand the problems, you are able to solve them. Okay. If you only see the reasons of increasing MPI and you blindly make a decision of changing your code, well, you may be lucky and succeed, but you may be wrong, and then you are wasting your time. And let's explain another example of imbalance, more complex. Up to now, the pictures of the histograms were quite easy to read. If I tell you this is also a histogram for a code of the useful duration, you see this much more complex to read, okay? Because it shows a high variability. This is for another real application. This is says is that the climate model is running 2 full days with 16 processes, okay? And if I see like that, is quite difficult to read. Well, I see vertical lines for the smallest values, but for the larger values, it's harder to know what does it mean. What the tools allow me to do easily is to select a region. Well, sorry, if I see the timeline, okay, if you are used to the tool, you may start to see things, but if you are not used to the tools, it may be harder to read. To facilitate this exploration of a given range of values, the tools allow me to, sorry, I see a message in the chat that says, in histogram, does each line denote separate thread? That's it. It will be a thread or an MPI rank. It will be one of your objects, okay? It's true. So going back, if I want to focus on this region, I can just select that region and open a new timeline. This new timeline is quite easy to read, I think, or at least it's much more easier than the previous one before. Okay, I see darker points that mean larger, and I see lighter points that mean shorter. Okay, and basically what I can see is kind of dark blue clouds that are moved around time over a background that is in green, something like that, okay, or just the opposite. So let's zoom at the beginning some small region and let's read that data. And I see the first processes do large computation, then they took less time, then they took more time, okay, for few iterations. After a while, when the clouds move down, okay, it's just the other way around. Okay, now the first points are lighter, okay, then they do more work, they do less work, okay. Then for that reason, this means that this is unbalance that is compensated a long time, okay? So in these regions are the first guide that take more time. In these regions are the last, the second other processes take more time. So as I am simulating 2 full days, this is fully balanced for the 2 full days, but a long time is always unbalanced, okay? So this is a problem harder to solve. There are other mechanisms to do balancing or to map, balancing online or to do mapping to try to correlate that data, okay? But basically this is dynamic imbalance, okay? And we will use that to show how does it work, the efficiency model. I see another comment in the chat that is saying, how did you decide the focus area in the timeline? Well, in the timeline, I will decide, we will see that examples later, but I will decide if I want to do the focus of analysis, I can do it in the timeline when I see the structure, okay? But typically what I do to decide the focus is I use the timeline and the table, and looking at the variability in the table and the timeline, then I decide the region. In that case, when I did the last zoom, it was just selecting a small region, okay? When I want to understand and to read things, if you are used to the tool, you can already read it here, okay? But if not, my suggestion is to zoom until you see a region with enough detail that is easy for you to read it, okay? This is just one slide as a reference for the trace manipulation that can be used when your trace files are large, but they can also be used when you want to do the focus of analysis, you want to chop a region, you want to chop few iterations, and you want to ignore the rest, okay? So in that sense, we have 3 main tools. The filtering, what allows you to do is eliminate data, okay? And I use this tool when I want to, I have a huge trace and I want to cut it. In order to cut it, I need some reference. So basically what we typically do is we filter only durations that are larger than a given value. And based on that, I get a very light trace file that I can load. And with that trace file, I cut select a region and do the cutting, okay? And this is the example here. The original trace file was 2 GB, that in fact, it can be loaded in memory as of today, but you may want to consider something smaller. I can compute a filtering that is only 5 MB, and from that filtering, I select an interval, and that interval is just 36 MB, okay? So, and it has 4 iterations. And then the other trace manipulation tools that is not so much used is the software counters that allow to combine data, basically to mimic hardware context metrics based on software information, okay? But today you will see how to use the cutter. Let's go to DMMAS. DMMAS is a coarse grain simulator that is based on traces and with the idea to keep on the more relevant key factors that affect a parallel architecture and affect the run of a distributed memory approach. So the architecture is abstract, and this picture displays the basic architecture of DMMAS, despite it can also have multiple of that machines. But let's say one cluster in DMMAS has this shape. I have some CPUs, because this is an old tool, so we don't have the multi-core effect in DMMAS. It has some CPUs that has a local memory, because basically we are targeting we are targeting message passing simulations. I need to simulate the local memory, because if I communicate with someone else in my node, I will do that through the local memory. But if I have to communicate someone outside my node, then I use the shared network. And this shared network, there is only one topology, that is, I have a given number of buses that provide a bandwidth, and then my node is connected to that network through a given number of links that have a given latency, okay? So basically there are 2 Bs and 2 Ls in this picture, despite I only show one, okay? And this is a very simple model, but allow me to do many simulations, and basically we use it in 2 different flavors. One of them is to do parametric sweeps. The idea of the parametric sweep is that I explore a range of values and I see the behavior. And this is one example of a parametric sweep where I am changing, I am evaluating the impact of bandwidth with a given latency and with a given contention, okay? This is B of buses. So 0 buses means there is no limit on the buses. There is no contention in the network. There can be as many messages in the fly as needed. And the latency is 8 microseconds. So I explore different values of bandwidth from 1 to 1 gigabyte. And I see how my applications from different flavors of my applications and different flavors of core counts behave, okay? And plotting these values from the MMS, and I gain, let's say this is the efficiency, so getting in the top is the most important thing. I can see that some executions are able to keep on the higher efficiency, reducing the bandwidth, while some others drop down sooner, okay? So the sooner you drop down, the more sensitive to the bandwidth you are, okay? And that way I can check what is the configuration, what is the flavor of my application that is less sensible to the bandwidth if I have to move to a machine that has less bandwidth, okay? So this is the kind of scenarios of the parametric sweep. So maybe tomorrow we will see some others, okay? But one of the most used scenarios for DMMS is what-if analysis. And the idea is I simulate a given scenario, just one, not exploring many of them, just one, because one of the benefits of DMMS is that it can generate as output a Paraver trace file, okay? So this trace file will allow me to understand what is going on that simulation. And the most frequent scenario we simulate is this ideal machine I already mentioned a little bit yesterday. That is the instantaneous network communication, okay? So it's 0 latency, unlimited bandwidth. So it will be the ideal machine, will never be built, but it helped me to understand where are my time in MPI being caused, okay? And let's go to this scenario where we have the code of Spectrum 3D. We were mentioning the code of Spectrum 3D, where I wanted to do asynchronous communication, okay? And this is, in this picture, like blue means computing, all the other colors, the different MPI calls, okay? And this is the real execution that I have 1, 2, 3, 4, 5 iterations, okay? And I simulate this ideal scenario. And what happens is almost the same thing. Okay, you see a little bit more here, but it's almost the same, not change at all, okay? There is no impact. I make instantaneous communications and there is no benefit at all, okay? Then I can do a prediction in Mare Nostrum. Of those days, Mare Nostrum, I do not remember which Mare Nostrum is, but it's an old one, okay? And I get almost the same thing, okay? So then I can start playing with reducing the bandwidth, different scenarios, because I see the ideal do not give me any answer, okay? And I have to go to very, very low values of bandwidth to have a penalty, okay? So with these simulations, looking at the results, what we can tell to the developers of the code was, don't waste your time doing asynchronous communications. You just answer that with that, okay? There is no benefit. You will not gain anything, okay? As we have seen with Paraver, because the problem is that the MPI time is not caused by transferring data, but because of imbalance, okay? But I can also tell them, okay, and don't be worried about the bandwidth of your machine. You can move to quite bad machines, and your performance will still be great, okay? So it's not only that you are not having transferring problems, is that even with a very low network, you will still be on time, okay? Because your problem is basically unbalanced. But in many cases, this ideal scenario allowed me, as I showed you yesterday in the slides, to split the time inside the MPI in 2 sets, okay? The one related with the transfer of data and the one related with load balances and serializations, okay? And this gadget is an astrophysics code. And in this simulation, again, light blue means computing, all the other colors mean the different MPI calls. I have put some labels here, okay? And I run this ideal machine with instantaneous communication, okay? And as it happens in many cases, there is a reduction. In this case, there is a significant reduction, around 20% of the time reduction with this ideal machine, okay? So that seems good, okay? But we can also understand, as I did yesterday with the other picture, with the other example, to understand what this is telling me, okay? What this is telling me, for sure, the light blue will keep the same because it's computation. But there are regions that are basically same thing, okay? This one is advanced a little bit, meaning this is a little bit shorter. But let's say from here to the beginning, almost the same thing, almost no impact of this instantaneous network. Because all this time is either imbalances, as you see here, different guys arriving at the different times, or temporal imbalances that compensate, okay? But what happens with these guys? All these guys, almost all these guys are drastically reducing its time, okay? And we have here the all-to-all, the send reg, the wait all, okay? All those calls are drastically reduced. This means on those calls, I am basically transferring data most of the time, okay? So that means if I can move to a faster machine, a faster network machine, I will improve my speed, but that also means I may consider to revisit my code if I want to optimize it. To revisit my code for that region, what I have to consider is, can I reduce the volume of data? Can I use different calls to reduce the volume of data? Can I group some data? What can I do to try to reduce this pressure on the transfer, okay? While for this first part of my application, well, as we see, the percentage of time in MPI is smaller, but if I wanted to improve, I should consider, can I better balance my computations? Can I try to identify if there are serialization or imbalances that I can compensate, okay? So depending on the answer of the ideal machine, the way to face an optimization of your code will be different. So let's revisit the efficiency model we showed yesterday to understand it as a way on how it is computed and why it is defined that way, okay? And let's start displaying a very simple case where I only have two processes. Blue means computing, red means communicating, okay? And I have two iterations and they have the same behavior, okay? So that will be kind of Spectrum 3D code where on each iteration, some processes were shorter, some processes were larger, okay? And this is expressed here, okay, with the example of only two processes, one short and one large. If I accumulate the time for the full execution, either computation or communication, if I use a profile of MPI, okay, I will get that. That means 50% of my time I spend inside MPI, okay? If I only care about the time in MPI, in fact, I have seen some tools that diagnose this case saying, you are MPI driven. Your problem is MPI, okay? But you haven't listened to me for around half an hour, okay? And you know that in fact there is some time in MPI you cannot blame to MPI because basically you were getting your partner, okay? And that happens on each iteration. So that is being accumulated, okay? So this time inside MPI is not caused by MPI, it's caused by load balance. But this time on MPI is caused by the communications. With this initial model, we have these two splits, okay? So we can compute the parallel efficiency, that is a percentage of time I spend computing, as the product of these two numbers, okay? And let me explain you how do we compute load balance and why. Load balance is the average computing divided by the maximum. And the reason for that is because you have to consider what is the waiting time in the load balance, okay? There are guys that express load balance as the ratio between the minimum and the maximum or some other things. But if we consider the ratio between the average and the maximum, you have to consider the guy that is computing more time, okay? And the average time that is people computing. So if there is a huge difference between these two numbers, it means that many people is waiting to the one that lasts more time, okay? That means that is a bad load balance. If these two numbers are closer, okay, then there is no problems of imbalance. So if there is one guy, only one guy that finalized earlier, okay, then the ratio between load balance and average and maximum will be very close because there is only one guy that is lasting more time. So it's only one guy that is waiting to all the others, okay? Let's assume I have 100 guys. But if it's just the other way around, if we have just one guy that is being delayed, then we have 99 guys that are waiting for this one. But then the average divided by the maximum will be smaller, okay? So this ratio between the average and the maximum expresses the waiting time for the average guy that accumulates everyone else, okay, to the one that spends more time computing. As you will see, that can be computed with any profile of MPI. That can be computed, I think, with almost any tools that profiles MPI, okay? But in fact, let's go back to recover this scenario where we have the climate model that on each iteration, it was a temporal imbalance that compensates a long time, okay? And that was the reason why initially we named this metric micro load balance, okay? So in the first iteration, the first guy is faster. In the second iteration is the second one that is faster. If I accumulate, as I did before, now load balance is perfect, okay? All of them have been working the same amount of time, but I still spend half of my time inside the MPI time. But as you know, there is time in MPI I cannot blame to MPI because on each iteration, one guy was waiting to the other, okay? And that's the reason where I initially named that micro load balance, okay? Because it was in fact load balances that compensate a long time, okay? But you can see that as a micro load balance, or you can see that as a chain of serializations, okay? So that's the reason we finally, when we include that in POP, we decided to rename it to serialization. That maybe was a simple concept that micro load balance was somehow confusing for some people. So that is basically identifying serialization and dependencies. We label that micro load balance. And the way we use it to simulate it is we do dim as ideal network. That way the transfer efficiency becomes perfect. And that way I can isolate what is the micro load balance, okay, with this simulation. But also Scalasca measured that, identifying what is the transfer time, okay? So I think you have seen this picture yesterday. So unless someone else wants me to explain it, and in order to be on time, I can skip it. The main message here is when I care about the scaling, I should focus that not only looking at the speed up, but understanding why the speed up is good or bad, okay? So if it's bad, I'm sure you will be motivated to know it. But if it's good, please also consider understanding why it's good, okay? And the second message is that maybe your parallelization is bad, but the evolution of the computing phases is taking you benefit. And as I said yesterday, I have seen many cases where this is happening, okay? So in many cases, we see that at larger scales, the IPC improves, and then, or there is some reduction of instructions, okay? And then you get benefit, not because you have done a great parallelization, but because the computations are helping you to get a better scaling. Again, I presented this slide yesterday, okay? And I wanted just to use it today to summarize two things. One of them is when you do the analysis, either on your own or you are in the hands-on this week, consider what is the focus of analysis. Consider that it's very important. The first step you have to do is understand the structure of your application and select the focus of analysis area, okay? So if this is my application and there is only MPI activity here, there is no reason to keep this time, okay? And if these are the MPI activities, depending on what this computation is doing, okay, I think I will eliminate it because I think it's done after all the MPIs, just before the MPI reduce, the MPI finalize. But this one here maybe is relevant, okay? So maybe that depends on my structure. So I may consider maybe I will, if I do have to analyze this code, I will check with the code owner, with the user, but maybe I will use from here to there, okay? If this is something that is only happening once, because maybe he just put one iteration. If this is something that only is happening once, then I may focus inside this area, okay? And the other important message is take care when you see this shape. If you obtain a trace file with our tools or with any other tools, and you see this kind of shapes, that is a step triangle going down, okay? Or going down or going up. Take care, because this means this is something is not going to scale at all. Because this means this is really saying the longer my MPI rank is, more time I spend here, okay? And that means that if I increase the number of processes, that is going to be worse and worse, okay? And maybe the last message here, because in that case, this is what's happening, that what was happening is check, if you obtain a trace, check that things are what you want to do. Because in fact, in this pattern, they were talking each process to each other, and that was a mistake on the programming of that loop. So let's go to the analytics, okay? And the analytics will be shown in the hands-on tomorrow, but let me introduce a little bit the analytics today, okay? Because maybe if someone have more time this afternoon and wants to start having a look, we can also help you to do it, okay? So the idea of the clustering tool we have is to help us to identify the structure. I typically have shown some examples where I work with the amount of work and with the speed of the work. Sorry, I see a message saying in timeline, if you zoom, the colors are changing. No, typically in timeline do not change. You can change them, okay? When you need to adjust it. You will see that on the demo later. But basically, I keep with the same coloring scheme, but I can, if I maybe wrongly answered your question. Let me redo it. If my application is code color, if my timeline is code color, meaning it's a categoric metric, then for sure when I zoom, I will see something different, okay? Because the area focus on a given values, and that's the reason on the previous picture where I see different colors when zooming, okay? Because here it was a given scale. It depends. We will see the tool has a drawing mode that decides how to put a color a pixel, okay? But inside one pixel here, you have many colors. So that's the reason the coloring here is changing, okay? But then if you have a gradient mode, then the full scale will not change. So it may happen that also do not change. So the reply will be, it depends. But for sure, when you are zooming, you are seeing more details. What you have to take into account when you are looking at a trace is that unless you are in a very small area, each point is representing an interval. And then in Paraver, this is called in the drawing mode. We can show you that in the hands-on, okay? And you can select if you want to see the mode, if you want to see the average, if you want to see the minimum, if you want to see a random, if you want to see the maximum, okay? And depending on the metrics, you may want to focus on one or the other or play with them to see a difference, okay? But basically for this picture, I will never say this is everything brown. I will need to compute a table to decide it, okay? Or I will need to zoom to go to the details. It's easier to find the focus of analysis from MPI calls instead of useful duration. Well, it depends on the application. It depends on the patterns of the communications. I think yesterday I saw some examples where I typically use both, okay? I load the timelines and then I select the focus of analysis. Because typically if I only use the one of them, it may depend on the coloring, it may depend on the frequency of the calls. The benefit of the useful duration is that show me the granularity. The lighter means small computation. So I may, let's say, if I put here the useful duration close to each other, I will see this is very, very light green. Okay, this is darker, and this is very, very light green, flat dry green, okay, because there is only these small computations, okay? And this will show me this is not a black box brown, but there is something inside, okay? So I typically use the two views because they are complementary, okay? One of them is telling me when I am inside MPI, the other one is telling me when I am outside MPI, and with the two of them, you will see how to drive the selection of the focus of analysis. Sorry, so let's go back to the clustering tool. So the idea is that I get these timelines of the amount of work, of the speed of the work as a way to measure how is the complexity of the code, how are the computing regions being executed, okay? But it may happen if I have to find the structure here, it may happen that it's not very difficult or seems not very difficult, like in this one, where it seems it may be 2 iterations with something different at the end. It seems the coloring is quite similar, okay? But if I try to do it here, it's even harder. It's not sure if this is the same or not, okay? So the idea of the clustering tool is help me to identify the structure, moving all this data, no matter which processor or web execute a computing burst, to a new space, defined by instructions and IPC, amount of work and speed. So we can do the clustering with many other dimensions, but 99% of the cases we use these 2 dimensions because we think there is a good characterization of the computing phases based on these 2 axes, okay? So if we move all this data from all the processes, all the execution to this space, around 90%, 80% of the cases of the HPC applications, we see isolated clouds, okay? Different shapes of isolated clouds. Then we use a density-based algorithm based on the DBScan to color those clouds. Those clouds have different colors, and then I feedback that to the trace file, okay? And that way, now I can read this picture, and I can say, well, it's close to 2 iterations, but it's not right because the first region is different. Then I have the green, the brown, the dark green, okay? So the other part of the iteration is the same, but not the first computation, okay? And it's true that at the end, there is different things. But for instance, if I want to understand what's the difference between this one and this one, okay? Is these 2 clouds here, okay? And in fact, this corresponds to this scenario I mentioned in one of the first slides, when every X iteration, it does some extra computation, okay? So many iterations are pink, and from time to time, one of them is red, okay? And this is driven by the behavior. I automatically do this analysis and isolate them, okay? And identify the ones that are pink, the ones that are red, okay? So what I do want to see on this square, ideally, I want to see dots. That means there is a small variability. And ideally, I want to see them in this part or in that corner, okay? With what means that corner? That corner means higher IPC. Always have to look at the numbers and higher computing phases, okay? Things that appear in this corner means they are smaller as a burst duration, and they have a poor IPC, the poorest in my range, okay? And let's say things in that corner will be my first target for optimizations. Things that have a lower IPC, but they have a relevant computing phase. They are computation phases that are larger enough, okay? One thing important to consider in the clustering that you will see tomorrow in the demos is that the coloring, the order of the clusters is telling me the relevance in the execution. So the first one, here we don't have the labels, but the first one is the light green, is the most relevant computing phase, okay? So if I consider what happens with the more relevant computing phase, it has this shape, and I can read this shape just reading the corners. Let's start with this corner here. This corner here is doing 300 million instructions with an IPC of less than 0.7. What happens here? This corner is doing less instructions, okay, with a higher IPC. Okay, so this is a bad situation if this is happening at the same time, because it's meaning I have imbalance because of IPC and because of instructions, but the guys that do more work, they do it slowly. The guys that do less work, they do it faster, okay? So the 2 axes are just pushing me to spend time in MPI, okay? Tomorrow you will see more details on that, and you will see examples where we will help you to read those pictures, okay? But we can combine, just one slide to combine DMMAS and the clustering tool, okay? So the idea is that we have blocks of tools that can be combined to each other. And we can use DMMAS and the clustering tool to simulate what-if scenarios and to decide, for instance, at the level of potential improvement, what should I improve on my code? Okay, this is my code. This is the clustering image. So in this picture, The colorings mean the two clusters, the two main clusters, okay? And white means either computing or inside small computing phases. Sorry, either communication or inside small computing phases, okay? So what I see is a repetitive behavior where I have two clusters, and if they read this scatter plot, what I read is that there is two clouds that has huge variability on instructions, okay? But between them, the difference is on the IPC. So more or less similar variability on instructions, the range of instructions, okay, that is expressing unbalance, but the green cloud has a lower IPC than the yellow cloud. So one potential optimization I can do is increase the IPC of this first cluster, but basically means moving this cloud closer to the other. I can do the simulation with DMMAS, and I see DMMAS tell me, it's just an approximation, but DMMAS tell me you may gain around 13%. Okay, and you say, well, that may be acceptable, depending on the effort that requires to understand why the IPC is lower, what kind of computation is doing, and how to improve it, okay? And a second optimization I can do is balance, because I see this variability that is causing timing inside MPI, okay? We have learned this causing time in MPI. So I can better balance the clusters, both clusters, okay? That means I have this histogram in Paraver that has variability, and I can create my perfectly ideal vertical lines, okay? And I can do the simulation of that scenario, and the tool tell me the benefit will be higher, close to 20%, okay? And show me where, okay? These two scenarios were very simple, okay? But in general, it show me where happens the improvement and what is the amount of improvement, an estimation of that improvement, okay? Doesn't tell anything about the complexity of doing one or the other, okay? But it helped me to decide if I want to do one or the other. Let's try to become a little bit faster, because I want that Lau has enough time to do the demo, okay? So that case is use the tracking tools is a tool that you will see also tomorrow. And the idea is clustering is an unsupervised algorithm. So if we want to correlate different clustering, it's better we use the tracking tool that identify who is who in the different scenarios and displays plots that the one we saw yesterday, okay? And here in this case, where we are doing a strong scaling, what we expect is things moving down. And as in the example we showed yesterday, we have three guys that do not matter how many processes they execute, from 64 to 512. They keep executing the same number of instructions, okay? So this highly pinpoint to three regions that have to be parallelized in order to have good scaling. Methodology, so the very last slides. The idea to use many performance tools, but the one we recommend with our tools is you generate hypotheses on what's going on, and you use the tools to validate the hypothesis, okay? And the idea is that will raise you to the next question, okay? I try to use the examples a little bit with that question brain approach, okay? So why I am unbalanced is because of time. The time imbalance is because of instructions, is because of IPC, and I keep asking me questions until I get some answers that allow me to do some steps outside the analysis, okay? Nevertheless, don't be scared. The first steps of analysis are very simple, and in the case of the VSC tools, Paraver comes, you can download with some tutorials, and there is one that is generic that you can use it, that is Introduction to Paraver and DMMAS Methodology. Those tutorials come with traces you can use, and the first steps are mainly the same things, okay? First steps are easy, and then you move on. Also on the demo now, you will see first steps when you have multiple executions, okay? But the idea is I will check the parallel efficiency because I want to know how much time I'm doing what I want to do, and I want to identify when I am inside the parallel runtime, what is the cost for that time inside that runtime, okay? I need to check the CGI efficiency, okay? How far from the peak performance is clear that I am not going to get the peak performance, but I can correlate with other execution or even with my regions. If there are regions that obtain twice the IPC than others, I can ask why this is because the instructions are easier, is because the access to the data is better, okay, I can check that either inside an execution or with the scaling. Things to check if you are checking the scalability, code replication, total number of instructions. We also have seen many cases where there is an increase on the total number of instructions. And in general, look at the behavior structure, the variability, okay? Because basically, if you run in parallel, variability a long time is not so bad, but across processes will many cases cause delays and waiting times. I see one message said, if computation overlaps with communication, how does that show up in the graphs? Well, you don't see, you see, basically, if it's overlapping, what you see when you put the communication lines, we can show you that in the demo, we see that it's basically being done while you are computing, okay? You put the arrow or the communication and you see it start earlier and you see that the transfer of data is done while you are computing. And another way to see it is basically if the MPI wait or wait tolls are shorter, means that all the data was sent before, okay? To know the internals of what, you can do some simulation of the MMS to get it, but for knowing in the real execution when it happens, basically what I can check is if the wait tolls take very small amount of time, means this is working, okay? Maybe this doesn't justify if it was used for the full computing phase or it was used at the beginning of the computing phase, but I do not pay for it, okay? So when you have to be worried if you are trying to overlap communications and computation, but you still have a large amount of time inside the wait or wait tolls, means that this overlapping is not working enough, okay? And you still need to wait on the wait tolls. This slide is used as a reference for the tools website and get it started, but I think you just get it as a reference and very few recommendations to get from this presentation. The first one, I try to promote that and I will keep trying to do it tomorrow. The importance of understanding things, not just knowing things, but understanding them, okay? So keep asking questions for the analysis. The suggestion to use visual tools, to use your brain with images, but let's say if you prefer to work with numbers, let's say there are people that is more efficient working with numbers, okay? But basically, in my opinion, it's easier to work with visual tools because the images are easy to read, are faster to read. The importance to work with the details, okay? Not to work at outside global levels, but to go to details to understand things, not to get summaries and just keep on the summaries, a profile of MPI of the summaries, and don't understanding why I spend time in the wait toll, for instance. And in general, don't expect what may be expected and be flexible. And just as a friend, easy to remind, be water, my friend. So that's the presentation. Just one slide to introduce, because I'm just getting the time from Lau. One slide to introduce it, and I just remove it, is we are going to use Lules with 27 core counts because it's a nice number that pushes a little bit the machines, okay? And this table you will see on the slides is just saying the same application, as I tried to say yesterday, the efficiency model characterization both the machine and the application. So I see with the same applications, this application has no communication problems with this scale, but you see it can have issues, and you can have issues even in the same machine, just depending on the flavor of MPI. It can have huge issues, okay? So basically there are huge variability on the load balance depending on the architecture, and you will learn about that now. So I stop talking and stop sharing, and I think it's better. If you have any question, we can ask later. Sorry, Lau, I take so much time.
Okay, well, I'm Lau, and as Judith said, I'm going to present Extrae and Paraver, and we'll do a quick demo about these two tools. Let me first start with Extrae. Extrae, as Judith said, is a camera. It's like a recording machine. It records the activity of our application and saves it into a trace frame. Don't you hear the drill? No, that's okay. This trace file can then be visualized and manipulated and analyzed postmortem in Paraver and with other VLC performance analysis tools, as Judith said. Extrae works on many platforms, and we keep adding them as we need. And with the main programming models, parallel programming models, we find in HPC. And if we can, we also add them. Apart from capturing the parallel runtime activity, Extrae also captures the performance counters using POPy. So we know what the machine is doing, how many instructions, how many cycles are lost, accesses to cache, and like that. And also offers links to the source code. So we can pinpoint where the activity of our application has problems, and we can go there and fix it. The Extrae also offers periodic sample to add some more information to the trace file. And the nice thing about this is that you don't need to recompile or relink your application with Extrae to capture all this data. It's done automatically by you. Of course, if you want to add custom events, you can do that with the API, OpenMP, where you put the start and end of your selected region, and it's also added in the trace. Of course, this needs to recompile and relink. And you may ask, okay, that's a lot of information. Surely there is some overhead in doing this. Well, there is, but the good thing is that it's small, and most importantly, that it's uniform. So these are the values I obtained yesterday, 2 days ago in Carolina. And just to know this, of course, as the more events you have on the trace file, the more of this overhead you will see. But as I said, it's very uniform per event. So how does Extrae work, and how can we get all this information without recompiling or relinking? Extrae does this using library interpolation with LD preload, where the Extrae library gets loaded before the application's library and first captures the information of the activity of the application, and then calls the real runtime, the real functions the application has to call. This is the recommended way. We offer other methods, such as dynamic instrumentation using dynist, and as I said, static linking with the Extrae API, which also includes compiler instrumentation and function instrumentation. Using Extrae is very, very easy. You just have to do 3 things, or 2, depending on how you look at it. So you have to adapt your submission script, which is adding 1 line. Then you have to select what you want to trace. So this is done using the XML file in Extrae, and you can find many examples in the installation of Extrae. And then you just have to submit it to the queues, to the scheduler, to the Java scheduler queues. Extrae usually installed in the main HPC machine, the HPC clusters, but if it's not, you can install it at home or in your custom cluster. Sources are available both in our website and in GitHub. And you have the documentation here, the manual, where you can find some examples of how to compile it, or information on how to do it by yourself. All of these is in the slides that you will find on the web page. And even you have some steps for the first analysis and how to obtain traces and all of this. But now I will go to a terminal, okay, and we will obtain our first trace. Okay. The first thing I have to do is connect to Carolina. I have an alias as Radim suggested yesterday, so you can just do SSH Carolina and everything is done in the background. So I have prepared some material. So I copy this material from my links to the Scratch folder, to the project folder, and to the Scratch folder. This material includes, well, how to obtain the application binaries, how to obtain the traces for MPI, for MPI+OpenMP that hopefully we will see today, MPI plus CUDA and basic analysis that I think you will see tomorrow. Okay, so first we will see how this is modified. So this is a typical script for the slur, which is the scanner that is found in Carolina. And this is the observation that also of the resources we need, and everything the observation is one. So I'm implementing it. The modules I need, the name of the trace file. This is optional. If you don't specify this, the Extrae takes the name of the binary and adds an extension. And it just does, I don't want to do this. And running with Extrae just needs to prepend this script to the binary. Now let's take a look at what this script contains. So this script contains where to find Extrae, which configuration I want to use, and which tracing library I want to use. Then it's very important this $* or dollar @ symbol, because this is actually running your binary. Without this, nothing will run, and you will say, okay, let me start the name. This is nothing. The tracing library will depend on what do you want to capture and what are your parallel runtimes. In this case, we only want to capture MPI information, so we just use the MPI tracing library. But there are a lot of them, and in fact, if we go to Extrae home /lib, there's a list of them. In Carolina, in this installation, we installed some of them, but there's a large selection of tracing libraries. Now let's run it. Okay, we modified our JavaScript. It's important that this trace.sh is executable because it needs to be run. So just submit this to the queues. And in the meantime, let's take a look to the XML configuration file. This XML configuration file has a section for every runtime available in Extrae. MPI, OpenMP, POPHPC, blah, blah, blah. There's also a section for CUDA. So we select what we want to capture from every runtime. We also can specify if we want colors pinpointing to the source code, how many levels, and if you want input output, if we want to capture user functions defined on a file, which hardware counters do we want? In this case, we just want instruction and cycles. Then the size of the buffer, this has to be a compromise between the memory used by the application and the flashes we want to do to disk, and many options. So if we want to obtain malloc information, PEP sampling, syscalls, blah, blah, blah. So lots of information. Okay, we wait a bit. We can check if our job completed. So it's completed, I think. So Extrae generates the output. So these are intermediate files. And the important files that you have to look at are this PRV, PCF, and row. This PRV has the actual data. So timestamp events. This PCF has the semantic information. It translates the timestamp information into human readable information. And this row has information about the resources used and how they are. Okay, now let's take a look at at the file we obtained. For this, I will open another terminal. Maybe I put this like this. I create a folder where I will put the trace file. Usually Paraver is run as it's a graphical application. Usually it's run locally. I think Radim said that there's some version of Paraver installed in Carolina, but usually running remotely goes very slow, and we prefer to use it locally. So first we need to copy the PRV, PCF, and row files to our machine. This is official. To our machine. So we have these three files and open Paraver. Do this, and this, and this. So by default, Paraver shows nothing. Okay. So we go to File, Load Trace, browse IT4i, and open the Lulesh PRV file. So by default, it shows nothing. Well, nothing. It doesn't open any window. But I see this workspace thing that it shows that this trace has computing information, so time computing information, MPI runtime information, has PAPI counters, call stack references, resource information, and flash information. So with this, we can say, okay, it seems that the trace has everything I need, right? And this information here can be accessed using the hints menu. The hints menu shows you suggests some views to start your analysis. In this case, we will start by opening the deficiencies view. So we get a quick look of the efficiencies of the POP efficiencies of the application. It opens this small table with the average being parallel efficiency, 86%. So it's higher than 80, so okay. The communication seems to go almost perfectly, and the load balance being an 88%. So we can say that the problem here would be load balance is the factor that is affecting the most the parallel efficiency. But let's check which region are we computing these metrics for. So if we open the MPI timeline, so we see that in this trace we have a lot of initialization here, right? So let's select a focus of analysis. So we will select the iterative region. So we will start from here until the end. And then we can copy and paste the times from one or the other. and the efficiencies changed a bit, right? So the first part, the initialization part was whoa, sorry, I'm gonna move this. So the initialization part was put as useful, so efficiencies were a bit higher than they should be. Now they got a bit worse. So load balance is still the main issue. Communications, it's almost perfect, and parallel efficiency is 84%. Okay. What else? So what?
You can load the profile of MPI and see
Yeah.
and the useful duration histogram to see the variability.
So this is the profile of MPI calls, and we can see the duration of each call. We can order them by their weight and remove the zooming. So, and I have to copy and paste the time again. Or I can synchronize the view. So I can select that this is the view. I click on synchronize and it automatically. So now the efficiency should be the same or very, very similar. Let's see there. And I see that most of the time I'm in peer-to-peer weights in the weight all. The second MPI call that takes the most time is the all reviews and the weight. So these three, in fact, is if we look at the timeline, we see this behavior here. And if you focus on the first iteration and the last iteration, it seems that it gets better a long time. So it seems that our communications are compensating a long time, or the system is getting warmed up, or that something else is happening, right? We can open the useful duration view. I'm going into here, not this, sorry. Useful duration view. Click on synchronize also. So we see this same behavior, and it seems that it's not always in the same process, it's a bit random, right? And this may be related with how the system is assigning the processes into the machine. So how the Scalasca is assigning the process into the machine. Or maybe there are migrations and things like that. We can check if this is the reason by going into the resource mapping, the process mapping. We can synchronize this again. And in fact, we see that there's a lot of random noise here. So it seems that the right part, which refers to the second socket, is more populated than the first socket.
Explain how to read that table. What are the columns here?
Well, each column is a CPU core. So y-axis, as I said in the chat before, are the processes, and the x-axis is each CPU core. This machine has 128 CPU cores split in two sockets, 64 and 64. And then there's the NUMA partitions, which every 16 cores belong to one NUMA partition, something like that. So from 65 to the right is the second core. From 65 to the left is the socket, sorry. From 65 to the left is the first socket. So it seems that the second socket in the right is much more populated, right? What will happen if we balance this? So we can go again. Let me move this into another not here. I don't know what I did now. Sorry. This here and this. So let's obtain a trace file that it's balanced, okay? That balances the
But don't generate it because we are running out of time. Yeah, I think it's better that you explain how to do it. And you
okay, but well, I generated a trace file that is balanced. I have this in my materials folder. It's this one. So
just one comment is basically by default, it seems like kind of a random distribution of my MPI ranks along the two sockets. And then to balance, what Lau has done is to add a couple of flags in the MPI rank command to specify that I want to bin processes and I want to distribute round robin through the NUMA nodes. Is that right?
Radin commented these commands yesterday, but I can show, I cannot show. But yeah, it's just a couple of parameters in the S1 line. It's bind to cores and distribution cyclic, something like that. So now if we open the resource mapping, we see that it's much more cleaner, right? So we have a number of processes here, and it seems that the machine does the round robin between NUMA nodes, not between sockets. So each 16 cores is placing a process, right? It's 16. So, and with this mapping, we have 15 processes in the first socket. These 3 here are not in here, and 12 in the second socket. Okay, now if we open the efficiencies for this or we open the MPI calls for this balance regions and zoom in the focus of analysis, and open the efficiencies and copy and paste the time. So let me compare this. The load balance got better, right? From 85, we moved up to 90. And the communications are more or less the same because they were almost perfect. And this improving load balance also improved the parallel efficiency. And it's true that now, if we compare these two views, this one is much more cleaner. We can also open the...
Synchronize the scale, so we get the black hole of the benefit from top to down.
Copy and paste time. So now this, not time, sorry. Copy, you mean this, right? So now these two are representing the same interval of time, the same amount of time. So we see that just by mapping the processes into a proper mapping, let's say, balancing between sockets, we obtain, I don't know, more or less a 5% of improvement by doing nothing to our code. Right? We can check where this time, these weights that we have here, how they improved. We can open the bound version, the MPI profile, and do the same thing, order by total, and copy what? And do copy time. And right before, the weight all was the MPI call that we were spending most of the time, with almost a 7%. It has been reduced to a 250. So a big improvement, right? And well, the all reduced increased a bit, but the weight almost disappeared. So we reduce the time in MPI by a great amount just by balancing the processes. Okay, what should I do?
I think we may need to stop here because the break was starting at 30. So maybe just show how to do with MPI plus OpenMP without obtaining the trace, just showing how to do it. And then I think tomorrow we can extend the demo to cover what we have been doing today.
Okay, I also obtained an MPI plus OpenMP trace, where let me unload something right this one. So this is the MPI with binding. Okay, and this is the OpenMP with binding. We can do the same. We can open the efficiencies. We open the useful duration, so because it's not cut right. Yeah, this is already cut, so we remove the initialization and finalization. And this is showing the global efficiencies for both runtimes, MPI plus OpenMP of the hybrid application. So in this case, the communication refers to both MPI and OpenMP serializations or scheduling and things like that. And well, we have the same metrics: the load balance, communication efficiency, which refers to also to OpenMP, and parallel efficiency. We can, I don't know, do I show the instructions? I don't know.
Maybe I think we can stop here because if we have to come back in 10 minutes, they will need to stop for a while. You can extend this demo tomorrow in our slot. You can start with completing that part, I think.
Okay. Okay, so let's stop here. Let's go for the break, and tomorrow you will hear a bit more of me. Thank you. Yeah, you have this in the slides more or less. If you want to start playing this evening, this afternoon with Extrae, if you have your own application or you are doing the hands-on. Okay, let me close.
Okay, thank you for your presentation. And now we should have a coffee break and we will continue at 10:45.
Okay, so this last session this morning is to look at the Scalasca toolset from Jülich Supercomputing Center. So that's using Scalasca, ScoreP, and Cube. We'll mostly be looking at ScoreP and Cube today, and then return to Scalasca and what it can do more of on Friday tomorrow. And we'll also start by focusing on the CPU only today and look at the additional information available from GPUs tomorrow. So let's see, next slide. Okay, so this is our generic performance engineering workflow, which involves a preparation step where we'll use ScoreP. We'll then do measurement, which is then a combination of using ScoreP with potentially Scalasca. That's optional. And then the final step is where we have a measurement we've collected, either a profile or a trace. We'll be focusing on profiles today, but then look at traces tomorrow. And then we have different tools that we can use to look at those measurements. Having examined those measurements, we hopefully get some ideas about what we would like to adjust in the measurement of what we've collected, and that can be a simple reconfiguration of the number of processes, threads, the nodes that you're running on, or it may be a more substantial change to the code itself, where you have to rewrite some of the code, move things around, implement something that's missing for load balance, for example. So that's left up to you. That's not something that our tools will help you with. And then having done that modification to your code, hopefully it's hasn't introduced any correctness issues, but has it produced any impact in the performance? Has it improved performance? And the best way to do that is to run it again and verify that it has, hopefully it's running faster. But if it's running faster, you still might want to do another more detailed examination of its profile or its trace to verify that the parts it changed and hopefully improved didn't actually have a detrimental effect on some of the other parts of the execution. Because there can be all sorts of interactions between changing one part of the code and changing data structures, for example, might have a bigger impact on some other parts. So this cycle then repeats that having modified the code, you would rebuild it, make some additional measurements, look at those, and eventually you would decide that the performance is as good as you find it needs to be at this point, and you can break from this cycle, move on to some other work. So SCORE-P is the measurement infrastructure that was developed by us. It handles the instrumentation of the application executable as well as the generation of measurements in different formats. There's a profiling format where you get a detailed call path profile, which we'll see later. This is the cube format. There's also a trace format called OTF2, which is a very detailed specification of the events, much as you saw with Extrae, but in a different format that's open and used by multiple tools. Depending on the programming paradigm that you have, if it's an MPI application, you'll have information for every process and their communication and interaction. If it's a multi-threaded application using OpenMP or POSIX threads, we'll see the different threads, what they're executing. For OpenMP, you'll see synchronizations and critical regions, for example, everything you get from the OpenMP side of things. And what we won't look at today, but we'll see more of tomorrow, is where you're using accelerators. If you're using CUDA, HIP, OpenACC, Cocos, or one of these paradigms, you'll see those kernels and the events on the host to launch those kernels, transfer data to the GPUs. All of those are provided by the measurement infrastructure SCORE-P. So SCORE-P is structured as a set of components. You can think of them as components. Depending on what the application is using and which adapters, which components are activated, SCORE-P can capture what's happening at the process level through MPI, what's happening at the thread level from OpenMP and P-threads, what's happening at the accelerator level. If there's I/O activities, we can interpose on those and capture those. And it may be that there's additional context you need to understand these other events. That might be something that the compiler can provide in most cases, so it can instrument all the functions. Or you can actually annotate the code yourself with the specific regions that you're interested in, whether that's a loop or a function or a phase of execution. That structure can provide additional context for any of the other analyses so that you can distinguish initialization from finalization from the core of your solver or different phases of your solver. So those are the main adapters where we which we're instrumenting. For the application that's running, we can also, when the application runs and those adapters capture events, then those events go into the measurement infrastructure, and then the measurement infrastructure decides what to do with them. The simplest thing it can do is just store them in an event trace buffer, and we'll see those event traces tomorrow. Something else it can do instead is to actually aggregate the events together. So if it, instead of recording individual events for every message transfer or every function implication, it can aggregate them together into a profile, not just a flat profile where it's looking at individual functions and individual MPI calls, for example, but it will actually keep the call path context. So the path of events to that, to the current event would be recorded or maintained in the profile as well. So those are what we'll be looking at and see in more detail today. Those are primarily in cube format. There's also an older tau format that's supported. Depending on which tools you're familiar with or prefer, you can use the tau visualizer called Paraver, or you can use the cube visualizer, which we'll see a little bit later to look at those profiles. Also shown in this picture is the various trace analyses, which we'll look at tomorrow. One of those is using Vampire, which is similar to the Paraver visualization of the timelines that we were looking at this morning. There's also the Scalasca trace tools. Those do an automated replay of the entire measurement, all of the events in the trace, and generate from it another cube file, an augmented cube file that has the additional metrics that come from the trace analysis. And then those can be viewed as previously with the same cube GUI that we'll see in a moment. All of the events that are collected get time-stamped, they get context information, they can be annotated with hardware counter events or usage events from the Linux kernel. So there's all sorts of different information can be used to augment these basic measurements and enrich them as appropriate. Not everything is enabled by default. That would result in way too much overhead. So a subset of information is provided automatically. You can augment this. You can eliminate things which you're not so specifically interested in at that specific time. So we're going to be looking at the red part this morning, which is what's happening when we're doing profiling, and we're looking at an MPI+OpenMP application, the one which I was introducing yesterday afternoon. And then tomorrow we'll go back and look at the orange part here. We'll also have a quick look at Vampire to look at the traces, but we'll focus on the profiles this morning and get started with that. ScoreP is open source. It's portable across major HPC platforms. We're trying to get it installed in all of the HPC systems at the moment, and we already have it on most of them, but not in the standard locations yet. So that's something that we're developing. It's highly scalable. We've used it on our BlueGene systems with over 1 million threads. We've used it on other systems, including the current GPU systems as well. It has the functionality which I just briefly summarized, and we'll see how it works in combination with Cube. Cube is our tool for writing profiles, for handling those profiles, manipulating them. And the part that's most visual and the part we'll spend most of the time on is the GUI that is used for browsing and exploration of those profiles. And the picture of it's here on the right. This was originally part of the Scalasca toolset, but it's now maintained as a separate component used by ScoreP and by Scalasca. I found it quite usable remotely on the Carolina system. If you prefer to install it locally on your notebook computer or on your workstation, you're welcome to do so. You don't need to install the Scalasca and everything else, but just the cube part is usually sufficient. Here I've summarized a couple of the options that you can consider. As I said, for me, using Cube remotely works fine. So you just log in, load the module, use it locally, that works fine. There's also the option, as I said, where you can install it on your own system. Here it's said it's recommended. That's depending on how much you're going to use it, whether it's worth that effort. Once you've installed Cube locally from one of the available packages or building it from source, which is a lot more effort, then you can either copy the Cube files or the entire measurement directories to your laptop, or just mount the remote file system from Carolina remote system and then use that. That's typically the much more convenient way, but requires a little bit additional setup. All of those three options you can experiment with and try out as you wish. Cube presents the information in three different, in a multi-dimensional display using three hierarchical axes. So that's where the name Cube comes from. One dimension are the different performance properties, the different metrics that are being collected, whether those are time metrics or bytes transferred or other more specific metrics. That information is collected for every execution call path, so that determines where in the program execution, which functions were being executed at the point where where something was done. And then the third dimension are the different processes and threads or execution contexts for GPU events that where those events occurred. So that naturally leads to three browsers which are coupled together. What you select on one affects the others, and Cube, as we'll see, presents this information, the severity information in value form, numeric values in colors, which make it easy to identify high and low values. And by using the tree structure and expanding it and closing the nodes of the tree, we can show both inclusive and exclusive values depending on what you're interested in. So an inclusive value is the entire time within a subtree, or the entire metric within the subtree. The exclusive value would distinguish the sub nodes of that tree from the node itself. And that might sound a bit weird, but we'll see examples of that in practice, which I hope will explain it. It's all highly customizable. We'll show you some of the basic options to get you started in the remainder of this morning session. So this is our cube display here with the three panels, as I said, performance metrics of various types on the left-hand side by default. The source code location in the middle, by default, you're seeing the entire executable. On the right-hand side, we're seeing all of the processes and threads aggregated together into a single machine. Once we expand these trees, we see that the execution consists of a number of processes, MPI processes, each containing a number of threads and running on various compute nodes of the system. And depending on whether a node is open or closed, you see the individual thread values, or you see the aggregate value for a process, or the aggregate value for the node, or at higher levels. Similarly, in the middle, as you expand the tree, you expand main, it goes down through various function calls, down into parallel regions, into do loops inside the parallel regions. And then whenever you select something from this middle panel, that's determining the focus, which will show which metrics, or the metrics for the processes and threads for this selection are then the ones on the right-hand side. Similarly, if I change the metric that's selected, then the metrics to the panels to the right change as well. So where does this numeric value here come from, this time of 8,000 seconds? That comes from aggregating everything across all of the call paths and across all of the processes and threads. So you can think of when you select something on something to the left, such as the first panel here, that's determining the focus for things to the right, but the values are aggregated from the right to the left. So if I've selected bytes here, then I'll be seeing bytes on the right-hand side, and the bytes get aggregated, and we see which call paths those bytes are sent or received. And then we see the total number of bytes sent and received as the value in the panel on the very left-hand side. Lots of numbers, lots of things to take in, but we'll hopefully see things a little bit more clearly when it comes to the interactive live part of the demo. I mentioned that Scalasca provides us a little bit more information. So instead of just seeing the basic time information, we can actually look at more specific metrics, which will tell us about waiting times, about inefficiencies in the execution. That's not information that's readily derivable from the profile itself, but if we've done the trace analysis, which Scalasca does, then it will augment the basic profile and split the metrics so we can see not just point-to-point communication time or collective communication time, but we can break those down into a more detailed form, which will allow us to distinguish the weighting components of those. As I said, Scalasca is the trace analysis. We'll see more about tomorrow. So just understand it's the automated trace analyzer that we'll be using tomorrow. It's taking the very detailed information that's in these execution traces, doing an automated analysis of it to produce a distilled summary of the trace information that's much more compact and easy to analyze, and it will be presented in the same three-dimensional cube display that we use for the basic profiles. This automated analysis complements the interactive visual analysis of Ampere or Paraver,
but it guarantees that everything is distilled into a fashion, and because it's done in parallel, it's also much more scalable, so it scales up to very large traces with very large numbers of processes and threads without needing to put everything into single large files or move files around. Also open source, and it has various limitations, which we'll discuss tomorrow, but basically for MPI and OpenMP, it will be able to handle most of your applications. So we saw yesterday how it all works together. Applications get instrumented. The linked version of the application has our measurement libraries incorporated. When we run that, it's collecting information that's then collated at the end and producing a summary report. That summary report can be processed to examined and processed to optimize the measurement configuration, add additional information, or remove things that are not so relevant. And then the final summary report is something that you can explore in more detail with the interactive GUI. When you're ready, you can turn on the event tracing option, generate event traces, and then those get analyzed by the trace analyzer or looked at with Vampire. The Scalasca trace analyzer generates the trace analysis report, and that trace analysis report is again in the same format as we were using for the summary report, so it will look very similar, but it's shown in the as additional metrics in the metric tree here. So this diagram hopefully explains how the different pieces fit together. We'll be focusing primarily getting things started with the yellow part with ScoreP, and the pale orange part, I think here, which is using Cube. And then tomorrow, when we're ready, we'll start looking at the event traces. So just to quickly summarize what the outline is for our plans. Yesterday, we showed some example assessments using Scalasca. Today, we'll be starting with ScoreP and Cube, hopefully do some an initial measurement. We'll look at that. We'll figure out that we can improve it. We'll do some scoring, which tells us where are the things that we can improve things. Generate a filter, which is one way of customizing the measurement. And using that filter, we'll have a refined measurement that is more appropriate for subsequent work, and certainly for trace collection. And then tomorrow we would continue with the trace collection and the trace analysis with Scalasca and with Vampire. And at that point, we'd also be ready to look at what's happening on the GPU side of things as well. So that was the first quick presentation, and now I need to switch to my second one, which would be on ScoreP itself. So ScoreP is, when it's preparing the application, it's putting information in. Let me do that again. So it's inserting the extra hooks, which would collect information as the application is running, just as you saw Extrae was doing. The measurement libraries, when they're linked into the application and the application is running, are collecting the performance information in various buffers, whether it's a profile or it's a trace buffer. And at the end of execution, that's aggregated and written out to trace files or to profiles. At the analysis part, we'll be then looking at the various metrics that have been that we can calculate from that raw data. What's going on? And exploring the results in various ways.
I still see the previous slides. I don't know if it is just my case or I see. Yeah, I think there's the same comment in the chat.
Let me, I can't see the chat, so yeah. You'll have to interrupt me if that's the case. Let me see what's going on. So
yes,
are you seeing the ScoreP now?
Yeah, ScoreP joined instrumentation and measurement infrastructure. Yeah.
Okay, good. Hopefully it will work better from this point. Yeah, I don't want to go through this again, but those were the different parts of the engineering workflow where the extra hooks get added to collect information that's written to profiles and traces. Those can be augmented and processed in various ways to calculate metrics and help you identify performance issues, and then hopefully lead to insight as to how you might modify the application to address some of those issues. This slide just are the same ones as we had before. SCORE-P is involved at the different stages of doing the instrumentation and measurement, so those are what's highlighted here. On the Carolina system, which I'm going to switch to in a moment, I'm going to load the Scalasca module. You can load the SCORE-P module if you prefer, but the Scalasca module itself loads SCORE-P and Cube as dependencies. The key thing to note is that SCORE-P is very dependent on the MPI and the compilers which are involved. So if you're using, depending on the tool chain, in this case, the NVIDIA OpenMPI one, you need to make sure that the version of Scalasca and SCORE-P that you're using is appropriate for that. Sometimes the module systems do that automatically, but that doesn't seem to be the case on Carolina. So you have to make sure that you select the correct version yourself. I'm going to be working with examples that we used yesterday. Here on the slide, it's mentioning Cloverleaf, but I'm going to be using the BTMZ one, which is the one that I had slides for yesterday. But before we get into the live part of the demo, I just want to mention that the way in which the SCORE-P instrumenter is used, it's a preposition to compile and link commands. So where you would normally be running your Fortran compiler, your MPI F90 compiler and linker, you'd be using SCORE-P in front of those. It's using various heuristics to determine what it needs to do at that point. If it sees the OpenMP flags, it should hopefully enable the OpenMP processing and measurement. If it sees something called MPI F90 or linking in an MPI library, it should also link in its measurement library infrastructure for MPI. Those are the basic heuristics it uses. It doesn't have any heuristics at this point for CUDA or OpenACC or COCOS or any of those other things. So in that case, you would need to explicitly tell it that you want those. So if you run SCORE-P with the help option, it will give you all the different options. The CUDA one would be enabling CUDA, disabling memory instrumentation if we're not interested in that. Those are just some of the options that are available. Typically, we would use, you can either put the preposition directly into the makefile that you're using, or you can define it on the command line, redefine the compiler on the command line. There's lots of different methods depending on what you're familiar with. And that's also the place where you would put in any additional options that you need for your for SCORE-P. So in this case, it's an OpenACC application, so I add the OpenACC flag. I'm interested in what's happening at the CUDA level, so I add -CUDA. And if I've done some user level annotations, which I have for this benchmark code, then I can enable those as well. So having a preposition that is defined in this way and is in your makefile can be a convenient way of allowing you to build the application without SCORE-P or enable SCORE-P and configure what it's doing. And then when you run the application, or when you build the application, you set the preposition or you enable it, and then SCORE-P with its options is then a preposition to your compile and link, and then it will link in all of the various source files and object files and produce an output executable. For the benchmarks that we've provided for those examples, we typically have used a separate directory, so it's not overwriting the executable that would produce without SCORE-P. That's just to keep them apart. You can give them a different name rather than a different directory, but a different directory was just the approach that we have found most convenient for the workshop. Up on the right-hand side here, it's showing some of the options you can use for enabling or disabling compiler instrumentation, saying that MPI is necessary if it hasn't figured that out itself. And there's a whole range of other ones, but those are the ones that this example uses. Some of you will be in the unfortunate position of using CMake or AutoTools and needing to handle the fact that those don't handle make files very well. So how do you configure those to allow you to use ScoreP? Well, they don't like the fact that ScoreP is a preposition, so you have to replace ScoreP and the compiler with what we call wrappers. So we have wrappers for various compilers, in this case, ScoreP ICC or ScoreP IFORT. And if you use those wrappers instead of the compiler, so not in addition to the compiler, but instead of the compiler, then that wrapper will underneath or inside it will use ScoreP. So ScoreP-ICC will inside run ScoreP as a preposition to ICC. Now you've lost the opportunity to add any flags and options, but those have to be specified or can be specified through environment variables. So if you need to specify instrumenter flags, then setting them at ScoreP wrapper instrumenter flags would be the way to do that. ScoreP wrapper-help will give you the information about using those wrappers, or we can take you through that in the afternoon. ScoreP, when you run the application, will do its measurements. We'll see that what it does by default. Those can be configured to add various additional information, or enable disable profiling, for example, or to enable disable OpenACC or CUDA. So there's lots of environment variables we can look at and adjust. I think I'll stop at that point because I think that's enough to get us going and get a basic measurement. Yesterday I was, so let me just log into Carolina and we'll continue as a live demo for a little bit from there. So this is my my terminal session, which I hope you're seeing. Can someone confirm that they're seeing me logged into Carolina?
Yes.
Yes.
Okay. When I logged in with -X because I need to use graphical tools at some point. So that's just a warning for you. I have a work directory in the Scratch partition, which we set up yesterday. That's where I have a benchmark that has been prepared. The basic build and run for this, I can quickly run through, but is just to show you the comparison, how things change when we use when we're using ScoreP. So by default, I don't have any modules loaded, so I need to load a toolchain. I'm using the GNU OpenMPI toolchain for this example, but you can use one of the others. Now, when I do make, the benchmark tells me how to build and run it. So I'm going to build the BTMZ version in class C. Do that again, because I had already built this copy. So it's going to run through the various source files, compiling them. OpenMP is enabled, both compiling and linking, and then the executable goes into a bin directory. And if I go into that bin directory, I can submit that. I ran it earlier, but this is my batch script that I have. I basically just set the number of processes and threads. This version I ran yesterday, so it has a reservation in here, so I'll just remove that. And submit it, and let's see if it's going to run quickly. It's already running, that's good. So that was quick and easy example of building and running a benchmark code on Carolina. It runs for 200 time steps here, so it should run in less than a minute. $18 is what it's reporting here as the benchmark time for the kernel, and it's also saying that the solution it came up with was within its expected tolerance, so it ran successfully. So how does this change when how does this change when I have score P in the picture? So make clean, just to get rid of the object files that I had from before. I now need to load score P. So let's see what score P versions are available on Carolina. There's two versions by default, one for the Compy toolchain, one for the NVIDIA toolchain. And helpfully, the default version is for the NVIDIA toolchain, so I better load the other one. Try that again. So now I have score P on my path, and I can do score P help to see what the various options are. I'll let you digest that at your leisure. But basically, I need score P in, but I'm going to be using it now. In the makefile, there's a makefile configuration here, so make config.def. Inside that is where it is telling me that I am using the MPI+90 compiler, so I could redefine that. Actually, what I prefer instead is to define this preposition that I can use, and that allows me to adjust things without needing to adjust the makefile itself. Put things in the makefile if you prefer, but on the command line, I can adjust things instead. So I already did the make clean, and I'm going to do the make btmz class C again, and this time define the preposition I'm going to use, which would be, surprisingly, score P. That would be enough. Just for fun, I'm going to add the user option because I know I've put some user instrumentation in here. If you don't have any in your code, then user will have no effect, but we'll see what impact it has in this case in a moment. Because this makefile has been adjusted to put the instrumented executable in a different directory, I now have the original version in the bin directory, and I have the new version in the bin score P directory, just to keep them apart. Just going to compare them, compare the sizes at least. The different sizes, if you do a more comprehensive comparison, you'll see that there are additional libraries linked in with this version, which aren't in that one. So the two versions are different, but the instrumented version is the one that I'm going to be working with. I can take the job script which I have and just run it and see what happens, which should be relatively quick and easy. I have job scripts already for Carolina that I can use for that. Think that, yeah, I can just run it as it is. So just without doing anything and running the instrumented application, what happens is that as it's executing, score P is involved. As soon as it starts measurement, it has produced a directory. Inside that directory, it will be storing some information as it's going on. First thing it has produced is a record of the configuration it's running with. There's a manifest which will describe what sort of information it's expecting to be written into this directory. It's still running at the moment. The application output tells me that it's still running. So let's see how far it gets. I'll let it continue a bit longer. If I did the score P info command, which I had on one of the slides, and looked at the config vars, that gives me a list of the different environment variables I could set. By default, I didn't set anything, and that's why the experiment directory, the one that is producing, is the default. And the default is to use this temporary directory, and then at the end of execution to rename it to give it the date and a time and some long list of random numbers, which is hopefully unique. So now the measurement is complete. I now have inside this directory a profile. profile.cubex, and that's the interesting part. I'll quickly look at the manifest just to show there's nothing mysterious there. It's just explaining which files are produced, including the score-P profile. This is the minimal configuration. We'll see more of those later. In the score-P config, it has a record of the different environment variable settings. So this is what you might want to use if you wanted to repeat this measurement and have exactly the same configuration used. Or if you're trying to debug why something has changed that you're not expecting, then comparing and examining those that configuration will help you determine if you set the environment variables that you expected to, and score-P picked them up. If it's not in the score-P configuration, then something you did meant that transfer didn't happen. So I have an initial measurement. So what do I need to do something with that? Well, Cube is the utility that I'm going to use. Cube is already on my path, or not on my path. Maybe I have to load it Cube GUIs. Score-P is not loading Cube, so I loaded Cube GUI separately. So now I have Cube on my path, and now I can use Cube to look at that profile. So hopefully you're seeing the three panels which I kind of mentioned earlier. I'll try and change the display to use a larger font size so it's a little bit clearer. I hope that's large enough for you to see clearly. So there's a various metrics on the left-hand side. Some of them might be a bit obscure, but things like time might be a good one to start with. This time, 2,800 seconds, might sound a little bit mysterious at first, but that 2,800 seconds is CPU time. So that's the aggregate of all of the processes and threads that we're executing. On the right-hand side, under machine, on the node of Carolina, I'm seeing the 8 MPI ranks that I was running with. And for each of those 8 MPI ranks, I have 6 threads. And for each of those threads, I then have the time that each of them was executing here. So they were running for roughly 1 minute. 62 seconds, 58 seconds, roughly 1 minute. And the aggregate of 48 threads running for 1 minute is this 2,800 seconds. Hopefully that's clear. Of course, they were running the BTMZ executable, and if I expand this, I can see the various functions that were executed within the BTMZ. There's some initial MPI setup with the MPI init thread. Should be no surprise that MPI init thread is executed by all of the master threads, but not the worker threads, because no OpenMP worker threads at that point. And it's taking a couple of seconds on all of the different ranks. Don't treat that time as being the absolute gospel, because there's all sorts of score-P overhead associated with the MPI init, because that's the point where we are creating these directories, setting up our measurement, doing some adjustments of exchanging of information to synchronize clocks between processes. But it's fairly representative of the time that the MPI init would require. If I look at one of the other metrics, visits, it's telling me that MPI init is executed 8 times, and it's executed once by each of the threads, each of the master threads, which is hopefully what you would expect. I can also look at the bottom and see MPI finalize, also executed once by each thread, each master thread. So that's, again, what we would expect. So the basic information we have there, I'm going to go back to time, because time is usually the part that's more interesting. The color coding, let me see if I can move this up a little bit. Hopefully that's a bit better. The color coding you're seeing here is not the default color coding, but it's a color scale from yellow to red. The lowest values in the yellow color, the highest values in the red color. So that's why if we look at this scale here, what it's marked as iteration here is the majority. So of the 2,800 seconds, 2,786 seconds are in iteration, and that is what we're seeing here as 98.5% of the total time. By expand iteration, I see the two functions which are called inside it, called exchange QBC and the ADI solver. And then the ADI solver has X, Y, and Z components, as well as some compute of the right-hand side. So by expanding this tree, I can go down as far as I am interested in. I can see the proportion of time through the color, or through the numeric values. And as I select something here, I can compare the values across the processes and threads in the panel on the right. So the X solve, the Y solve, the Z solve, the numbers change accordingly. They're all roughly the same, but the numbers are changing. If I expand the Z solve and the X and Y are the same, they each contain parallel regions, and inside the parallel regions, I can see the do loop. And then inside the do loop, there are again various functions which are being executed here. And I can see the time for each of those. So I'm able to distinguish not only between the time for these functions, such as this left-hand side init. This is the version inside the Y solve. This is the version inside the Z solve. So I can aggregate all of those times together, or I can see them separately according to the context from where they're executed. And there's also a version in here in the X solve as well. So that's distinguishing what you'd get from a flat profile, just showing functions, to a more augmented profile where we actually have the context showing where not only functions are called, but where MPI is used. MPI is used, I believe, in the right-hand side. No, it's MPI is in the exchange. So here are the MPI operations here inside the exchange, as distinguished from MPI operations which are used elsewhere. So there's a lot of different things we can do here, changing the metrics, looking at the number of bytes which are sent and received. Again, the bytes sent and received are sent in the ISend, received in the wait all. There's an additional reduce down here, which also sends and receives bytes. In this case, they're received by rank 0. They are sent by all of the other ranks because they're all part of the same communicator. So we distinguish, that's one way of distinguishing the collective operations from the point-to-point. We'll see a lot more detail about that later, but one of the key things that maybe you already noted was that the measurement which we did here, if I, for example, look at the execution time, it was saying 60 seconds. And that 60 seconds is also the 60 seconds that we would see in the application output itself, because if I look here, the time in seconds is also 59, 60 seconds. And that's quite different from what we had in our original version, which is in the other directory. And there it was only 18 seconds. So factor of 3 perhaps different. So something has changed quite substantially in terms of the impact on the measurement, and that's something we would like to understand. One of the obvious reasons why things have changed is that everything is now instrumented. So we're collecting a lot of information that wasn't there originally. And some of the functions in here are executed very large numbers of times. So inside this iteration ADI, where all the red stuff is, there are lots of functions here that are called millions of times, and sometimes hundreds of millions of times. And this was a relatively short execution, so the fact that they're called hundreds of millions of times or tens of millions of times by each thread in this case has its impact on the measurement. So those are functions that might not be so interesting to have in every measurement that we do. You can be, of course, very interested to know that they're executed however number of times and to have some sort of estimate of what time they are taking. But the fact that the measurement overheads have been so substantial, and that overhead is primarily for these highly instrumented functions, highly frequently executed functions, means that those are a trade-off that typically we would prefer to avoid. So instead of having separate measurements for all of these functions here and the similar functions which are in the other parallel regions here, ideally we would filter those out. We would still get the information that we're really interested in, which is about the MPI and the MPI synchronizations, but we wouldn't have all of the detail about what's happening inside the OpenMP do region itself. So, of course, we could find this by exploring the cube file itself, but there's a more convenient way of doing that I want to show you, where we can take a little bit of a shortcut for this. So the process which I'm interested in is called scoring, and there's a score utility that I can use. I give it the profile, and that scoring tells me at a glance how often different types of events in that profile were encountered. It tells me the time for them, but the time, as we have seen, is not something that's reliable in this case. But the visits is reliable. So the MPI functions were called 33,000 times. That's something that's reliable from run to run. That for a deterministic application execution, that's not going to change. And what we see here is that the MPI is actually a relatively small component of the total number of visits. The OpenMP events are quite a bit more, but they're also much, much less than this large number here, which is related to the user source routines, the functions of the application that the compiler instrumented for us. So those are where the huge majority of the instrumentation time has been. If we were to do a trace, we would need something like 21 gigabytes of data per process to store all of those events and then write all of the events to disk at the end. And this estimate up here is that roughly 160 gigabytes would be required for that trace for our 1 minute execution. So this is quite excessive and something we would prefer to avoid. So so this is where scoring and filtering will help us reduce things to something that's more manageable. But how to get to that next level of information? Well, if I add the -r flag here, I'll get a region level breakdown, and I'm going to just look at the top part of that. The summary at the top is exactly the same, but now it's giving me a breakdown for each of the application functions, or each of the events which were in the measurement. What are the contributions to these totals that are coming from them? And we see the various OpenMP parallel regions here. We see MPI activity down here. But the thing which is up at the top, because this is sorted, are some application functions, these user source routines. And those were the ones that I pointed out that were inside the OpenMP parallel region. So those are the things that we would potentially be willing to sacrifice and eliminate from the measurement. And if we were to successfully eliminate those, we would still have all of the OpenMP information, we would still have all of the MPI information, but hopefully we would substantially reduce our measurement overheads. So I can put that information, I can put the names of these functions into a filter file, and an example of such a filter file is here, not in the make file, but in the score-p filter. So it has a specific format. Here I'm using the region names. I could use file names or some other format, but here these are patterns, which should match the names of functions, which would be candidates for filtering. And if I apply that, which I'll do by adding -f and the name of it here. So now I have an extra section here, which is summarizing the effect of the filter. And I have annotations to each of the routines and events to say whether they match the filter or not. So these ones that have the pluses match the filter. And if I go further down this list, I'm seeing that I'm still keeping all the OpenMP and MPI, which is good. But I'm also eliminating some of the timer functions. So, I mean, the application is doing benchmarking, it's doing its own timing. I don't need that as well. So I chose to eliminate those as well. So feel free to eliminate things which you think are not interesting. They're still, of course, executed. You just won't see them in the profile or in the trace. What was the advantage of doing this? Well, by filtering out our 21 gigabytes of events, I've reduced the total amount that's collected from 21 gigabytes per process to something like 80 megabytes. This is still quite a bit of information, but much less and much more manageable. So I can handle a trace buffer of 100 megabytes per process instead of working with gigabytes, which was what it was before. So I have a filter file, but I need to apply that filter file to a new measurement. And I'm going to, in the interest of time, I'm going to show you a variation of the measurement which I just did, which is using one of the Scalasca utilities. So that's going to be called Carolina's scan. So you can do this with ScoreP as well, but I'm just going to skip a couple of steps. So instead of specifying it on the command line, I'm going to specify my filter file through an environment variable, ScoreP filtering file. The same environment variable works for ScoreP as it works for when Scalasca is used. If I was to just run with ScoreP, it would generate a new measurement directory. I'm going to not specify an explicit name, which I could here, but just leave Scalasca to come up with a name. And I'm going to run Scalasca Analyzer as a preposition to the run command. So instead of srun and btmz, I'm going to be using scan as a preposition, just like I use ScoreP as a preposition to the compiler and linker here. Here I'm using scan as a preposition to the run command. That means that the measurement is under Scalasca's control. It can set some environment variables that it wants, as well as do some additional things, which we'll see in a moment. One of the things it does is it chooses a default name, which is a bit more meaningful than just the timestamp. It's actually going to use the name of the executable. It's going to use the number of processes and threads and use that to generate a more appropriate name. Oh dear. Yeah, so let's try that. And let's see what that has done. Yeah, that's what I suspected. It's a good idea to load the Scalasca module, but you have to make sure you load the correct version. And since I can't remember the correct version name, I'm just going to comment it out instead. And use the version which is defined from the path that is from the environment that is submitting the batch job. The advantage to having it in the batch file itself is that you remember that the Scalasca module is noded, and if you load the correct version, it will use that when it's executing. So where are we now? Scan command not found. Very good. So I need to load Scalasca, and I need to load the appropriate version, which is this one. So there we go. Now we have everything we need. Very good. So this time it's naming things, as I said, based on the executable name and number of processes and threads, and it's added _sum just to indicate that it's a summary measurement. Inside the output here, it will have also given us a little bit more commentary about what it's doing. So the scan S run was what I was executing, and it just confirms that. These are all of our OpenMPI warnings, which are normal. At least on Carolina, they seem to be normal. And at the end of execution, it tells me my measurement is complete. And I already have a good sign here that I've eliminated most of my measurement overhead because I'm back down to 19 seconds here. So, so now I have a new directory, which has a lot of the same information as before. It has a copy of the filter I used because it recognized I was using a filter, and it's put a copy of the filter inside that directory just so that I have it available for reference. So hopefully no surprise there. The Scorpy log file is just a copy of the job output as it was running, or not the job, the srun output of the execution. So I have a log of the run command and its output. That can be helpful as well. And now I'm in a position where I could actually look at the new kube file. So the new kube file, if I compare them, should be very similar. So this was the original one produced by Scorpy with all of the measurement overhead. This is the new version. It's slightly smaller because we've eliminated some of the additional measurements. Some of those functions that were called very frequently have been eliminated. We're not doing tracing or anything expensive at this point, but the profile is a little bit different because we don't have those functions that have been filtered out. I could look at the new measurement as before with Cube, but I'm going to be using instead the Scalasca. So Scalasca provides a more convenient way of looking at the Cube files. Instead of using Cube, I'm going to use Square. Square works with Cube, and it takes the name of a directory. So it would work with either of them, but I'm going to use the new one. It tells me that it has done some processing of the original measurement, the profile, to produce something which it's calling a summary. And that's just an augmented version, a restructured version of that profile. Somehow the font has got very large, so I'm going to try and make it a bit smaller again. I think that's still large enough. So we have restructured the metrics on the left, and that's actually the main part that has been restructured. So I'll come back to that later. But for our time metric, instead of having 60 seconds for each of the threads, I'm down to 21 seconds. And for the timed part of the benchmark, which is this iteration, it's down to the 19 seconds. So this is giving me a lot more confidence that what I have for the iteration now corresponds to what the benchmark was initially measuring. If I delve down deeper in here, I'm still seeing X, Y, Z solve. I'm still seeing the parallel region. I'm still seeing the do loop and the barrier at the end of the do loop, the implicit barrier. But I'm not seeing any of the internal functions that were called within the do loop itself. Those are what we filtered out, so now those don't appear. And I have the time for them in the do loop itself. I still have the barrier time at the end of the do loop, which is some measure of the load imbalance, but I don't have the overhead and the redundant information from the details of the functions inside here. So this is looking a lot more promising. As part of the restructuring, time has been changed as well. So time has this arrow that allows me to expand it and allows me to distinguish execution time and what is a new metric called idle threads. I'll come back to that in a moment, because the execution time is what we had before, what ScoreP provided. But that execution time is what we can split into computation time versus time for MPI, OpenMP. And then for OpenMP and MPI, we have synchronization and communication and point-to-point and all of that stuff. If I want to see where the collective time is, I can see the reduces where those collective operations are happening. If I want to see the barrier synchronization, that's in here. So this restructuring of the metrics allows me to more quickly identify the significance of them in terms of their time, but also where they occur in the application. OpenMP here, you might think is all of the time in OpenMP, but it's not. OpenMP is the OpenMP runtime overhead, which is related to, in this case, synchronizations and flushes and things. So, for example, there's a critical section which I can identify down here inside the parallel region. It's actually an atomic, but that's a form of critical. It's very insignificant here. It's in the verification, which is executed once, and there's no significant cost, so I can ignore it. But it's not telling me the computation time, because the computation time is not an overhead. The computation time in the parallel loops is the part that we're interested in. That's the part in the do loop that was in the functions of the do loop, as opposed to the barrier synchronization, which is the overhead of OpenMP at the end of that parallel region. We already saw that MPI is executed at selected parts of the execution by only the master threads. When the master thread or the primary thread is executing, that means that the other threads are idle. And what Scalasca has done is it's quantified that as idle time for the entire execution. That's the time when cores have been allocated and are available but are not actually being used. And if we were to compare that to the execution time, so inside the exchange here, the execution time of all of the threads is 0.67 seconds, of which the majority of it is on master threads, with very little execution on the worker threads. The idle time is only on the worker threads, and it complements the difference. So adding both of those together means that I get the same number, the same time for all of them. So that's one way of quantifying how much resource wastage there has been inside this measurement. That's also the sort of metric that we were looking at earlier from the POP efficiencies. So for that information is available here in a different panel. I'm going to switch here to something called BSC, and here it's going to calculate these POP efficiency metrics. It's calculating them for the call path that I have selected, which is in this case the computational kernel iteration here. And it's now telling me the load balance efficiency, the parallel efficiency for this specific part of the execution. And here it's actually relatively good, so there's nothing to worry about. But for other applications, for other cases, you might find that that's not the case. So this is a convenient way to get a quick assessment of the various efficiencies, and if there was a load balance efficiency that was a serious one, then that would tell you that's something that you'd want to look into. have only a couple of minutes left before we stop for lunch. So I think that that's enough at this point. That is taking you through there's lots of more things that we could do or look at here with Cube and do with Scorpy, but that should be enough to take you through what you would need to do this afternoon with your own application or with BT or the other example that was provided, to be able to go through this process of getting a measurement, of doing a scoring and filtering of it, and then generating a refined measurement, which has a more accurate and representative profile. We'll see we can do a lot more in the session, which we'll have tomorrow morning, where we can add hardware counters, we can look at the GPU events, but I think that that has shown you the basics to get started. And if I go back to my presentations, let's see if there's anything that I would want to mention here. So in the presentations which are on the website, it shows you more examples of what you can see with Cube. I'm not going to go through it here because it's, I think, better to get a feel for it and go through things interactively yourself. But it's explaining this this difference between inclusive and exclusive components of the metrics and how they're shown in Cube. So that's something that's important, but you'll get a feel for when you explore things yourself. And then lots of other things that you can do with Scorpy and some examples at the end. I think all of that should be sufficient, and maybe we have time for a couple of questions, which I can't see. So if someone has questions, then they'll need to call out to me. So there's some information about the format of the filter file on the slides. For those of you this afternoon, I'll point you to a document which you can work through, and that will take you through the steps of applying a filter and using BTMZ as I just did. There's a way to automatically generate a filter, which you can do as an alternative. And then, yeah, we'll look at some of the other optional things when we return on Friday. So I think that will be my concluding slide for now. So is everyone clear about how to get started with the exercises this afternoon, or we'd be returning at 1, so we have a bit of an hour to have lunch.
So thank you, Brian, for your talk. And let's have a lunch break, and we will continue at 1 p.m.
Okay, thank you.
And the final day for the POP3 and NCC's workshop, which is also the 46th VI-HPS tuning workshop on profiling and optimization. And also we have started the recording again, so the tutorial part will be recorded today as well. So please accept the notification that you have received. And we are still missing quite a number of participants, but they keep joining in. But I think we can start with the presentations.
Okay, so I'll take up from yesterday to explain a couple of things first, and then we'll move to today's agenda with Herman. But first, let me explain how to do a couple of things with the traces. If you remember from yesterday, we ended up with binding processes to the cores, and we obtained better efficiencies, a better time. But if you remember, we were doing zooms here and there, right? To focus, to select the focus of analysis. Right? We're doing a zoom here, we're copying, pasting the time, so we have the same region. So this is a bit cumbersome with needing to do this every time you open a new window, copying and pasting the things. of course, we have the synchronize feature, but still every window has to update if we modify the zoom on one of them. One convenient tool that Paraver offers is the trace manipulation features, where we can select one of the regions and cut this region so we obtain a new trace with only the focus of analysis. I will show you how to do this. It's very easy. You just need to select the region you want to cut. Let's start again from the full trace. So as we said yesterday, we want to focus only on the iterative part. So if I see this here, the iterative part is this. I see many iteration, 10. So what I want to do is to focus on these 10 iterations. Let's do this copy and paste thing. So maybe I don't want this first MPI communications here because this is the MPI init, the first intelligent of MPS. Maybe I can start at this first computing phase. You see this is in black here, which this is the view of MPI. So black means outside of MPI. In this case would be, as we only have one runtime, would be running. So we can see here that this is in fact computing duration, is useful duration. So we are computing here. So we can select from anywhere in this large computing region to the other point where MPI or here until the last all reviews. And we also see a long computing phase. So we select from here to here. We have the zoom focusing in our iterative pattern, and we can right click and run the cutter. Okay, this is a new window. This opens. It already shows that the starting time, the end time. It suggests as a new name. I already have it cut, so this is big. That's why we have the 2 here, but we can change the name. And it's just a matter of clicking apply. So it cuts the trace and it loads the new trace into Paraver. You see here, chop 2. This is the new trace we have generated. And if we open just one view, or the 2 views, the 2 same views, the useful duration and the MPI calls, we will see that this is the region we cut. Well, it's a bit displaced because what Paraver does when cutting is to adjust the computing region, the regions, so we don't miss any data of the region we're in the middle of. So it adjusts the timing, so we obtain the full region. Okay, but now if you see the timing, if I select all the time scale, this is only the iterative pattern. If I do the same in the uncut version, you see that there's a lot of time for initialization and finalization here. This is not the only way to cut traces. I can also select this run cutter here, and instead of selecting the whole region, I can say, okay, so I can say select region from here and point at the, I don't know, from here to here, for example. I can do this clicking in one point and the other and click apply, and we'll obtain another trace just with, no, it's not this trace, sorry. Is this job 3? Come on. With just one of the iterations, okay? So it's a convenient tool to reduce the size of our trace files in case they are very big, or to select a region of analysis. Okay, after doing this, I will show you a comparison of 3 scales of already cut traces. So I have 3 scales of this with 8 processes. Just if you remember yesterday, I think I said that so okay, thank you, Judith, for answering the question in the chat. That Lulich needs to be a cube number of processes. So the first cube would be 8, cube of 2. The second cube would be this 27, cube of 3. And the third one would be 64, cube of 4, right? These are already cut traces, so I can open the useful duration and the MPI calls, and I see that they only contain the computing region. So I will open side by side the 3. I hope I can open side by side. Maybe I will do this the bottom. So side by side, and finally the views for the 64 processes one. So when I click in this triangle here, what Paraver does is fitting the coloring, okay? It sets the minimum and the maximum values that are found on the timeline and changes the colors accordingly. So the clearer one is the minimum value and the dark blue one is the maximum value. Okay, I have these three traces. And what I first see, do you see the timing here? 2.3, 2.7, 3.5. So this is 8 processes, 27 processes, and 64 processes, right? What I expect is as I increase processes, the timing should be reduced, right? This is not the case. I can copy the time from this one to the other ones, for example, and I will see this. So the time keeps increasing. Why is this? I'm increasing, I'm increasing the number of processes. I want to take less time, right? So why is that? Let's take a look at the counter for instructions. Okay, for the 8 processes, this is 27. So instructions, and the last one. Okay, it's here. Okay, let's copy and paste the scales. Control. And so these are in the same scale. The maximum value is 100. So it should be the same because I copied it. So these 3 windows are in the same scale. So the maximum and the minimum should be the same. And what I see here, that there is no change in the number of instructions, right? Meaning that this scaling is weak. What it means is that each process keeps doing the same amount of work, even if we increase the scale. Okay, then they are still doing the same amount of work, but I'm increasing the processes and timing increases. So why does it increase and does it not remain the same? Well, we are adding more processes, so we are sharing resources with more and more processors, right? So if we take a look at I cannot look at the mapping for these 3 because they are a cut and the mapping is only in the first the first part of the trace. But what I know is that in here, 8 processes. If I used a round robin between NUMA nodes. Carolina has 4 NUMA nodes for one socket, 4 NUMA nodes for the other socket. So I have 4 processes in each socket, so very low sharing of resources. In this one, I had a bit of imbalance between sockets, right? If you remember from yesterday, I had 15 processes in the first socket and 12 in the second socket. It's an increase. It's an increase and it's an imbalance. And we already see that this trace is a bit more noisy than the other two, right? And finally, in this one, I have 32 processes per socket. So this increase in processes affects the shared resources. For example, we can take a look at the IPC to see how it goes down by this sharing of resources. So what I do is going into PAPI counters and open the instruction space per cycle view. Okay, for these 3 ones, so I copy and paste the scale from the one with less sharing of resources to the one with higher sharing of resources. And this one gets a bit more. Okay, so
that may be inside IPC, MPI.
Yeah, maybe it's inside MPI. But you see that the coloring in the computing phases, the computing phases are this blue, it's getting lighter and lighter. So this is dark green, not so dark green, and very light green. And we put the mouse on top of this region. In the case for 8 processes, we have almost 3 instructions per cycle. In the case of 27 with 15 and 12 processes, we have between 2.5 instructions per cycle. And finally, in this
64.
In the 64, I have 270, right?
So 2.7, but if you zoom in one iteration, it's easy to see.
Maybe it's easier in one iteration. So, and maybe copy and paste on the grid. Okay, and you see how the coloring changes from dark to light, right? Then what else? The sharing of resources. What I can see, hopefully, if I zoom in this region here. And if I fit the time scale and this one is not so clear.
I think it's better that you focus on the one in the middle, but it's
maybe I focus in this one because it's very clear how the sharing of the NUMA node affects the IPC in this particular region, right? If we remember, maybe I can open the view for this one.
Or you unzoom and you see basically that the ones that take longer.
But I wanted to show the resource mapping.
Mm-hmm.
So this is the resource mapping for this case. So I have, this is the socket delimiter, 15 and 12 processes per socket. But in the first socket, I have these 3 more, right? Which share resources with the first, with the 9th, with the 17th, and with the 25th processes. So for the 1, 9th, 17th, and 25th, I have 3 processes, which are these ones that have lower IPC. This is why they are on the 3 first NUMA nodes, and they are sharing the resources of the respective NUMA nodes, and so they obtain less IPC. They are sharing, these are more people sharing more the same resources as these other ones, which can obtain this 320 and 315. Is not a very high difference, but just one extra process can affect the performance of the NUMA node because of the sharing of resources. And I think that's all what I wanted to say. So if Herman is ready, I'll pass the screen to him.
Sure, go ahead.
Thank you for listening.
So can you see my screen?
Yes, we can.
Okay, thank you. So this is Herman. Good morning.
But we see an agenda, right?
Yeah, this is the
Okay.
agenda. Before I start, I wanted to do a quick comment that we have a really small set of slides uploaded for today that you can get from the VI-HPS website. It's this one called Basic Analysis, Burst Clustering, and CUDA. It's only 5 slides, and it's basically a reminder of the commands that I'm going to be using. So you have them as reference, okay, to know how to launch the tools later if you want to try them this afternoon. And then in the end, there is some brief explanations on which changes you need to do in the tracing scripts in case you want to get CUDA traces. And if we have time at the end of this demo session, Judith maybe will be able to present some CUDA examples, okay? But this is just a reference that we don't need right now. You have it for later. And so the idea of this next part is to focus on 2 new tools, which are the basic analysis and the clustering, to try to do the kind of analysis that Lau was doing, but a little bit more automatic. And then with the basic analysis, the idea is to obtain the efficiency metrics, the POP metrics that have been presented previously and used the previous days very easily, and get an idea very quickly on how the applications are scaling. And then with the clustering, the idea is to identify structure in the application and to understand better what the efficiencies are telling us. So as a very quick recap of what Lau has been explaining, okay, we have learned that Lulesh is an application which is very sensitive to sharing resources, and thus it is very sensitive to the way you map the processes in the course and how much do you stress the socket and the NUMA node, right? And the other thing that I wanted to comment is that we have 2 versions of Lulesh, okay? Lau has been showing a pure MPI version, and he has shown that it is using weak scaling, okay? So we increase the number of processes, but each process individually does the same amount of work, okay? But there is another version, which is hybrid, MPI+OpenMP, and I will give you a heads up, okay? This version, the scaling is different, it's strong scaling, okay? And we will prove that with the tools later, okay? But I wanted to comment this straight ahead because I will try to compare these 2 versions, okay, with the basic analysis, but we have to keep in mind that they are not exactly the same, okay? And for example, because of the hybrid version being a strong scaling, we are reducing the amount of work when we increase the number of threads, and this might improve the use of the caches, okay, because we are working with smaller chunks of data. And so maybe this version is not so much affected by sharing resources, okay? And also in strong scaling, as we increase the amount of resources, the computations become smaller and smaller, and so the ratio of communications to computations also becomes smaller, and the communications take more importance, okay? And so maybe we see this reflected in communication efficiencies, okay? So having these two ideas in mind, let's try to use the basic analysis to do a first comparison of these two versions of the code, okay? So we can start with the pure MPI version, okay? And in order to run the basic analysis, I have this script here. You only need to call this Python script, which is called model factors, okay, which is under the installation folder of the basic analysis, okay? And these installation folders, please allow me to explain that in Carolina, we have prepared a script, okay, which is this one here, that if we look at it, it's setting all the paths, okay, for all the BSC tools. And then it's loading some modules that are necessary with Python dependencies. And one little comment that I have to add is that this is, as you are seeing it now, as you have it in Carolina, this loads the environment to use the basic analysis, okay? To use the clustering, we also need GNU plot, but we detected yesterday that loading GNU plot changes the versions of these modules here and makes the basic analysis incompatible, okay? So you need to load these three to use the basic analysis. Later on, you need to load GNU plot, okay? But once you have done that, if you want to use the basic analysis again, you have to clean all the modules and then resource this script, okay? And only load these three to use the basic analysis, okay? Because GNU plot changes the environment, okay? And we didn't find a good combination that doesn't mix versions. And the other little thing that I need to say is that to use the basic analysis, the first time you need to install this dependency, which we didn't find available in the system. There might be, but we didn't find the module that contains it, okay? So with this command, this dependency is installed in your home folder, and that's it, okay? In any case, to load the environment, you only need to source this file. You also have this in the slides, so you can refer to that later if you want to use it, okay? So to use the basic analysis, we run the model factors, and basically we need to pass the traces that we want to analyze, which in this case, it's the pure MPI traces, and I am using the one with 8 ranks, the one with 27 ranks, and the one with 64 ranks, okay? So I'm running this script. Now it's processing the traces. It's running simulations in the background with ideal scenarios. This allows to compute all the efficiency metrics, which are reported first with this table over here, which is a quick overview of the speed up and the average IPC and frequency to have a very general idea on how well the application is scaling, okay? So here we are going from 8 to 64, so 8 times more resources, but the speed up is capped at 5, so not great. And then we can dig down into the efficiency metrics, the POP metrics, okay? If you remember from the previous presentations, this is a hierarchical model, so it starts with a global efficiency, okay, that you can see already that it's going down significantly when we increase the scale down to 60s, okay? So it is decreasing. Okay, and this decomposes into parallel efficiency and computation scalability, and this in turn decompose into more specific metrics, okay, that compose this model, okay? And on top of this textual output of the tool, you also get these numbers in tables that are colored, okay, in images, okay, which are these images that are produced over here. So let me open these colored tables, which are more pretty to see. And so, for example, we have the efficiency table, okay, which is this same one that we have over here, but with this coloring where you if you see yellows and oranges, you start paying attention. If you see reds, okay, something is going on over there and you have to really look at it. Okay, and in addition to this table with the efficiency metrics expressed as percentages, you also get, for example, this other picture is called model factors matplotlib, which shows the same but as a line chart. Okay. And sometimes it's easier to look at the lines to see which one is going down faster, which ones are going up, okay, or you can look at the numbers, okay? They are expressing the same thing. Now, if we look at the numbers, I already mentioned, you can see the global efficiency is going down significantly. And if you see the metrics that compose the global efficiency, you can see that the parallel efficiency stays in high numbers, around 93s, 90s, 92s. Okay, so parallel efficiency is pretty good, but it is the computational scalability that is going down. Okay, and the factor that is making the computational scalability to go down faster is the IPC, which is going down at 30% from 100 to 70s, around 70s. Okay, and we can also see that the frequency scalability, it is also going down around 10% when we increase the scale. Okay, instruction scalability, this one is not going down. Okay, this means there is no code replication. It actually is able to improve a little bit in the highest scale, which is good. Okay, so in this example, it is the frequency scalability and especially the IPC scalability, which is limiting the efficiency. Another interesting thing that we can see that Lau just explained is that we are using Lulesh with 8, 27, and 64 because it needs cubic number of processes. And 27 is a tricky number because it is difficult to balance. The case of 8 processes balances everything perfectly. So we have 4 processes per socket and the same amount of processes per NUMA node. With 64, again, everything is perfectly balanced. We have 32 processes per socket and the same number of processes per NUMA node. But with 27, we introduce an imbalance, okay? And this imbalance reflects in the efficiency metrics here in the load balance, which decreases a little bit from 93 to 89. Okay, and when we move forward to the next scale where things are balanced again, we recover from this. Okay, but this imbalance that Lau explained, it is expressed in the efficiency metrics here. So now let's try to compare this with the hybrid version, MPI plus OpenMP. So in the same way, we would run the model factors on the new traces. Now I am using 8 MPI ranks and 1 thread, 8 MPI ranks and 4 threads, and 8 MPI ranks and 8 threads. So I am increasing the number of OpenMP threads, okay? Because this command takes 2 or 3 minutes, I am going to save you the time and I have the output already prepared, okay? Same as before, it produces these global metrics with the overview of speed up, average IPC and frequency to have a general idea. Then you can dig down into the efficiency metrics. And if you remember from the explanations of the model, now I am using a hybrid application. So it is applying a hybrid model, okay? And in this case, the tool produces 2 sets of metrics. The first set of metrics is this table over here, which contains the efficiency metrics, okay? The global efficiency, parallel efficiency, load balance, but these are global load balance, global communication efficiency, and this is not splitting between the contribution from MPI runtime and the contribution from the OpenMP runtime, okay? This is combining everything, okay? And there is another way to compute the metrics that it is able to split the contribution from the 2 parallel runtimes, which is this second set of metrics where you have here the hybrid parallel efficiency, which is composed of the MPI parallel efficiency and the OpenMP parallel efficiency, which in turn decompose into their own specialized efficiencies. Okay, so in the same way, we have these numbers in more pretty pictures. So allow me to go there. And so we have the efficiency table. We also have the line chart. Okay. And here we have the hybrid case, okay, where we are increasing the number of OpenMP threads. And what you can see immediately is that the global efficiency is dropping even further. Okay, now we were at 60s, now we are below 50s. And the reason for this, it is still mainly due to a decrease in computation scalability. And again, the factor that is contributing more to this degradation, it is still IPC, which is going down by a 30%, and also the frequency scalability, which is going down a 15%. So same as before, it is frequency and IPC, the ones that are the main bottlenecks and reducing the efficiency. But we can also see that when we have introduced OpenMP, the parallel efficiency, it is also going down slowly. And it is because the load balance, it is, well, maybe, the numbers, I mean, it is going down from 93 to 88 is not a huge decrease. You can see maybe in the lines, okay, it is the red line. It is decreasing a little bit, but mostly you see the communication efficiency is going down from 98, 91, 86. This would be the green line in the chart, okay, that starts here. Okay, it's going down faster. Okay, it crosses the load balance at this point here. So if we continue scaling, we can, this suggests that communication efficiency is going to be more of a problem, even though load balance starts lower than communication efficiency. So in the smaller scale, load balance is more of a problem than the communication efficiency. When we increase, this is going to switch. Okay, so all in all, these efficiencies of load balance and communication efficiency, to understand where do they come from, what we can look is at the hybrid metrics, okay, to understand whether this comes from the MPI parallelization or from the OpenMP parallelization. And for this, we have the other table. Put it here. I also put the lines here. Okay, and here you get the hybrid parallel efficiency that splits into MPI parallel efficiency and OpenMP parallel efficiency. And you can see that from the point of view of MPI, we are in the 93s, 93s, 94s. This is not decreasing, okay? Load balance stays very high, 93, 95, 98, 96. And communication efficiency, it is also very high, 99, 98, 97 point something. Okay, so from the point of view of MPI, we are doing very good. But when we look at the OpenMP parallel efficiency, you can see that it is going down by a 20%. Okay, and it is going down because the load balance is going down by about a 10%, and the communication efficiency, it is also going down by a 10%. And just a little reminder, okay, communication efficiency. Remember that this model was originally developed for MPI, and then the term communication efficiency reflected the idea of the communications of MPI, you know, where you send messages over the network, and then the communication efficiency refers to the transference of data. And it is a very clear concept. In OpenMP, there are no sending messages as such, but we still use the same terminology. But you have to think that communication efficiency covers everything that is not load balanced, okay? And in the case of OpenMP, these are the fork and joins, the scheduling, the dispatch of new chunks of work, the synchronization of OpenMP barriers, atomics, these kind of things.
And temporal imbalances that compensate a long time.
That's
a long time or across parallel loops.
Yeah, thank you, Judith. So anyway, this new inefficiency that we see that has been introduced by adding parallelization with OpenMP is not that bad, okay? We are in the 90s, 89s, okay? The numbers are still not that bad, whereas the drop in IPC is very large in comparison, okay? And comparing the two versions, both versions, pure MPI and hybrid version, show similar symptoms, okay? They are both showing a drop in IPC, which suggests that both versions are very sensitive to sharing resources. And when we increase the load in the socket, the IPC just drops, okay? So scaling is bad for this application in its two flavors, okay? And because IPC is the main factor that limits the efficiency, let's focus on understanding this, why this happens, where this happens, okay? So to continue, now we are going to analyze in the traces where this happens to understand better the IPC degradation, okay? Let me close all this. And we'll start using clustering, okay? I will start with the, sorry, I actually have Paraver open already. 1 second. Yeah, it's here. I will start loading the first trace. We'll start looking at the pure MPI version, okay, which is simpler, okay? So I will start with the first MPI trace with 8 processes, which I have it here, okay? So if we show the MPI calls and the computations, you can see that in this trace, I have already selected the focus of analysis, as Lau explained. So I already did the cut in the iterative region, okay? And in order to apply the clustering, you will see in the slides that there is a command that you can use from the terminal. And actually, we have prepared scripts for you if you want to try this on your own applications. I will show you this at the end of the presentation. But you can also run the clustering inside Paraver, so you don't have to leave Paraver and the session of analysis to use the clustering, okay? And it is as simple as you have to select any window that is showing the time interval that you are interested in. So the focus of analysis that you are interested in, okay? So each of these two is selecting the whole iterative region. So each of the two can be used for this. Then you can right click on the timeline, go to run, go to clustering. It pops up this dialog where it basically is asking me for a configuration file, which is this XML file. Okay, and I have prepared one for this example, okay? And I will show you how this configuration looks like here in the terminal, okay? The clustering algorithm that we use is a density-based clustering algorithm, and this family of clustering algorithms have 2 parameters which are very important, which are these 2, the epsilon and the mean points. And these basically determine how the clusters are going to be formed, okay? The mean points is pretty straightforward. This describes how many points, how many neighbors need to be close to consider that as a cluster, okay? And the epsilon is the distance of how far away I am going to look for neighbors to keep the cluster growing. Okay, so if we use a very big epsilon, the algorithm will tend to look very far away for points, and then it will tend to make like one big cluster that contains everything, okay? And if we use a very small epsilon, then the algorithm will not look very far away for neighbors, and then it will tend to create many, many small clusters that are separated from the other clusters. So this depends on the data. This depends on the application. So it needs a bit of trial and error. Okay, there is no good clustering, bad clustering. Every clustering exhibits and exposes a structure. But then depending on the data, you need to play with these parameters, and you will be splitting more or less the clusters, and this will highlight better structure or not, okay? So I have it tuned for this example already. And well, the rest of this configuration file, basically, it's in a normalized space. There is one question in the chat of the unit of the epsilon. So it's in a normalized space of 0 and 1. And well, this is basically telling the tool that we want to make the clusters based on instructions and IPC. Okay, so with the clustering tool, what we are doing is correlating the computing phases of the application with how much work they do and how fast the work is done. And this will give a very quick characterization of the program, okay? As well, I will show you, which will be much easier. So we just click run. Okay, all right. Oh, okay, 1 second. Because I opened the tool before setting up the environment, so it doesn't know where the clustering is. So I just need to open it again. I use full duration, right click, run clustering, browse. I select the configuration, just run, and this produces two things. One is the same trace that we had where the computing regions have been colored. Okay, and the other thing is a description of the clusters that have been detected. Okay, and with these two things, we can characterize how the computing regions behave. Okay, and you can think that this clustering tool, what it is doing is it is like summarizing all the information that is contained in the trace, and each cluster is expressing one of the computing phases, one of the computing intervals. Okay, and here we have a description of how these computing phases behave. For example, the green cluster is the most important cluster. It's on the top. This means on the top of the y-axis, this means it is doing a high number of instructions. It is also on the right corner of the plot. Okay, to be on the right, this means that in the x-axis we are having a high IPC, okay, above 3, which is very good. Okay, so this phase of the code is doing high amount of work at very high speed, which is very good. Okay, and you can see in the timeline where this is happening. Okay, this is the first large computing burst of each iteration. Okay, and you can see that the structure is very repetitive. Okay, you see the same colors over time. This is telling that the performance behavior of the computing phases is the same over iterations. Okay, so we can focus on just one and analyze one iteration, which is representative of any of them. Okay, you see the green cluster covers almost 50% of the iteration time. Then the second most important cluster is the yellow one. Okay, it does less instructions than the green one because it's on the bottom, but it's also on the right, which means it has high IPC. So this is also good. No? In general, we want to see things on the right end of this plot, okay, which means we are doing things fast. in general, we don't want to have things on the left side of the plot, which means we are doing slow things, okay? Especially we don't want to see them in this corner over here. That would be the worst case scenario. Okay? That would be to do a high amount of work slowly, okay? So that is what we don't want, okay? And just by looking at,
that may be easy to solve. Let's say if it's larger computation, it's easier to solve that. Smaller computations with a bad performance.
Yeah, of course. And this can give you intuition or a first candidate of optimization, okay, when you see these kind of things. So the next region we see is the red one, okay, which is in this phase over here. But look, in this case, the clustering algorithm has detected two trends. Okay, it is the red one and the purple one. And when you see in the timeline where this happens, you see it happens simultaneously. Some processes are in purple, some processes are in red. And in particular, it is rank 0 and rank 1, the ones that are in purple, okay? Purple is on top of red. It means it's doing more work, but it's on the same vertical line, okay? It means they are working at the same speed. So if at the same speed, I have some guys doing less work and I have some guys doing more work, these ones will take longer. And actually, you can verify here that these ones take longer. So with the clustering, when you start to see this kind of elongated shapes or clusters with split behaviors, this can also be indicative of performance imbalances, okay, that you can verify also in the timeline if they happen simultaneously or not. Because when these kind of things happen simultaneously, the fast guys, which are the red team, will have to wait for the slow guys, which are the purple team. Okay, and in this case, there is an MPI synchronization in this black cap over here that absorbs the imbalance. Okay, but this is wasted time in MPI for the fast people. So then we see the green cluster, which also has good IPC around 2.7, very compact cluster, so no variability. And the slowest region, which is this one here, is a small, much less instructions than the other ones. Okay, we usually don't focus too much in the regions with low number of instructions because they are small and they represent a small percentage of time. So they are not so much representative, so relevant. Sorry, but,
no, but basically,
in any case,
one comment, Herman. If that cloud is labeled as cluster 1, then you have to focus on it. So basically, the order of a cluster, the less relevant for this run.
So the tool labels the clusters and orders them by relevance in time. So cluster 1 is always the one that covers the most percentage of time, followed by cluster 2, followed by cluster 3, and typically the first 4 sum up to 80% or 90% of the computation time, typically. So always look at the first clusters, okay? In any case, this one also have an IPC of 2, which is not bad. Okay, so in this example, in this scale, the IPCs are pretty good. So let's see how this degrades when we increase the scale. Okay, and for that, we can cluster the next experiment. Okay, I already have these traces clustered, so I will open it straight away. It's here. Here. There we go for 27. And then let me open the scatter plot. There we go. So first thing that you can see is that, well, the clusters are becoming a little bit wider. Okay, you can see it very clearly in the yellow, which is wider. You can see it very clearly in this one, which is wider. But you can also see that this red cluster, now it kind of has split into another one, which is the dark green. Okay, and when we look in the timeline, and again, the structure is very repetitive, so we can look at one single iteration. Okay, you can see that in this phase that we had this different behavior for just 2 processes, now we have groups of different behavior. Okay, and if we focus on this area and make this window a little bigger, okay, you can see that in groups of 4, the processes belong to red team or green team. Okay, and this is related to the mapping that Lau explained. So the way that this machine is assigning processes to the cores is a round robin between the NUMA node. So first process goes to the first NUMA node, second process to the second NUMA node, 3 to 3, 4 to 4, and up to this point, everything falls in socket 0. And then it continues, fifth process to fifth NUMA node, 6 to 6, 7 to 7, 8 to 8. This goes to the socket 1. And then it cycles. The next ones go to socket 0, socket 1, socket 0, socket 1. And if you sum up, you have 15 people in red in socket 0 and only 12 people in socket 1. Okay, so this is the imbalance that we introduce when we run with 27 processes. Okay, and this results in socket 0 a little bit more stressed than socket 1, and this makes that the behavior of this computing phase changes, right? And this is why the red cluster now splits in two. And
just one comment, it's not the behavior of the machine, it's because we have added some flags to do it. By default, it was kind of random.
Precisely true. By default, it's some sort of random assignment. Then we added flags to pin the processes to the sockets, okay, and to round robin them between the sockets. Okay, but typically, now that you mention it, in many systems, okay, when we do this, the machine does the round robin to the sockets, okay? So each process, it selects alternatively one of the two sockets, okay? But in this case, it does it at the level of the NUMA node. And because of that, it makes these groups of 4, okay? So in some machines, this 27 case results in having 14 processes in one socket and 13 in the other one. But in this case, it results in 15 versus 12, which is a little bit more unbalanced, okay? And in this case, this reflects in this change of behavior, and then the red team, which are the ones in socket 0, which is more stressed, this cluster is to the left, okay? It has lower IPC, okay? And the green team, which are the fastest ones because the socket is more free and they have more resources available, they achieve a little bit higher IPC, okay?
And maybe another thing important to comment here, the time imbalance we see is not only caused by the IPC, it's also caused by imbalance in instructions, okay? So you can see that there are red guys that are much more larger than other red guys, okay? So it's the combination of the two things. So despite it's true that the mapping is affecting, this region is also affected by the instructions, okay?
So, continuing with our objective, which is to understand why IPC is degrading, we could then cluster the next experiment with 64 ranks, and then we could load again this scatter plot and the timeline, and then look at these 6 windows together. Okay, but instead of doing that, which starts to become more difficult because there's more windows in the screen and more things to correlate, we can use another tool, okay, which is out of the scope of the course. We didn't install the tool in Carolina because it has a GUI and it makes it difficult to use remotely because it becomes unresponsive easily. And it is difficult to install the tool in your laptops because it has many Python dependencies, and the Python modules are very picky in the versioning. And we decided not to try to install this. But if you are interested, we can definitely help you. Just get in touch. And this other tool is the tracking that Judith also explained. And the tracking allows us to compare multiple clusterings at once. Okay, and so to use the tracking, we pass the clustered traces as input, okay? And you can see this as an interactive GNU plot that presents us with the clustering of each of the experiments. So this one corresponds to the 8 rank case, this one is 27, this one is 64, okay? And we can navigate between them, okay? The tool presents them in a space where ranges are fixed for all the experiments. Okay, so IPC goes from 0.5 to 3, which is the minimum and the maximum observed across all experiments. So when we switch between them, we can easily identify that things are moving to the left. Okay, moving to the left means, because the x-axis is IPC, means that we are degrading IPC. Okay, and if we move to the 64 experiment, we can still see that it is moving even more to the left. Okay, and for example, the purple that started at an IPC of 2 in the last experiment is at IPC of 0.5. What the tracking also allows to do is to represent these regions of code, these clusters, by their centroids. Okay, and then draw trajectory lines that show how these clusters are moving. And now it is very easy to see that mostly all clusters are moving to the left. Okay, so cluster 1 is moving to the left, cluster 2 is moving to the left, cluster 3 is moving a lot to the left, but there is one region that is not moving to the left, so this is good. No, this region is not affected by IPC degradation, so it is not sensitive to the sharing of resources. And then the cluster number 5, it's also moving a lot to the left. Okay, so it is very easy to see which ones are degrading in IPC. And you can also see that in the right pane over here, okay, which now it is showing instructions. So we said that the MPI version is weak scaling, okay. This is also showing the weak scaling, okay. All regions are doing the same amount of instructions in all the experiments. Actually, the red one is able to improve a little bit, okay, which is good. And from the point of view of IPC, you can see that the dark green is the one that does not see degradation of IPC. Then the two most important regions, which are cluster 1 and 2, they degrade a little bit. And then cluster 3 and 4, they degrade significantly. Okay, so now let's compare with a hybrid version. Okay, let me close this. Let me go back to Paraver. Let's start with the trace with one single OpenMP thread. Okay, and the same way we did before, we can check the MPI calls. We can check the duration of the computations. Okay, the focus of analysis is already selected. Okay, I already did the cut. Okay, but because this trace is sorry, no, these windows are not for the correct trace. Sorry. I didn't have the OpenMP trace selected. Sorry. The MPI calls. Select. Mode. Okay. Then the duration of the computations. We go. Now, in the same way, we could compute statistics for the MPI calls with the MPI profile. Okay. For example, this. Now, because the trace also has OpenMP, okay, the hints menu also suggests new views. So we can look, for example, the parallel loops. Okay, so we can see the OpenMP parallel loops. Okay, you can hover and see what are the names for the parallel loops. We can also see statistics for the parallel loops, as we did before. Okay, so by default, we are seeing the number of instances, but we can change that into percentage of time. We can sort this by the total values. So we can see, for example, that this one here, calc, FP, hourglass for LMs, is the one that takes the highest percentage of time. Okay. And now, if we compare with the pure MPI version, so we are using the same amount of resources here, right? So it's 8 ranks versus 8 ranks with just one single OpenMP thread, so same amount of resources. If we look at the structure, mode, both maximum. From the point of view of MPI, they look exactly the same. But if you look at the computations, you will see, now if we focus, for example, in one single iteration, as we typically did before, okay, this is one single iteration. Copy this time. We do the same here. Copy this time. Oops, sorry. There we go. So they look very similar, but if we copy the scales from one to the other, you will see that in MPI, the computations were larger because they are expressed with blue colors, okay? So this first computation here was large. In the OpenMP version, this has been split into 3 different parallel loops, okay? And so each of them is smaller. And you can also see that for this last region over here, the one that is imbalanced due to instructions and that it is affected for the mapping, here in OpenMP, it's been split also in a really very fine-grained parallel loop, okay, where there is probably a lot of overhead of forking and joining just to do very, very short, very little computations, okay? So probably it would be a good idea to maybe try to merge these very fine-grained parallel loops to reduce OpenMP overhead. Another thing that we can see in OpenMP, if we look at the instructions, histogram of use for instructions, and then it's the time. Okay. Now is that, well, these pick the large parallels that take more time, or are also the ones that are doing more instructions, okay, because they show more blue colors over here. There we go. Yeah. The large parallels are the ones that are doing higher number of instructions, okay? And in this last region where we have this very fine-grained parallel, the number of instructions is very small, okay? Actually, if we change the draw mode into random, okay, we will see the gaps better because these parallels are really short, okay, and there are many of them. Okay, and the last thing that I wanted to show you from the traces is to prove that this application, that this version of the application is doing a strong scaling, okay? So if we look at the histogram of the instructions, which is this window over here, and we compare with the next trace, the one that has 4 threads, okay, so 4 times more resources. It is this one over here. And we look at the instructions of this other one. The structure looks the same, but when we copy the scales, everything moves to the left. Okay, so with 4 threads, the amount of instructions has been significantly reduced. Okay, actually, it's been reduced by a quarter. Okay, so in this case, we are using strong scaling, and this is one way to look at it. But it is not the only one. We can also see this with the clustering and the tracking. Okay, so let's move to those and see which structure is found in the data in this experiment. So let me go here. Sorry. Actually, what I will do is to cluster the trace of one thread already here in Paraver. So let me pick one region with the focus of analysis that I want, for example, the computations, then right click, run clustering, then select the configuration file, this one, then run. And this produces the scatter plot with the description of the clusters and also the clustered trace. Okay, so for the clustered trace, Let me filter out the noise and really small clusters, okay? And let's look at these two things together as we did before. Again, the structure over time is very repetitive, so we can select one single iteration to focus the analysis. Okay, and we can correlate this with the OpenMP parallels, which are around here. There we go. So what do we have? The most important cluster is the green one. It's on the top. It's doing a lot of instructions. IPC around 3, which is pretty good. Then the yellow, IPC even higher, less instructions, but very good IPC. Then the red, also very good IPC, high number of instructions, very good. Okay, so also the dark green, okay, which is here, this region over here. The first 4 parallels, big parallels, they have decent granularity, high amount of work, very nice IPC, okay? And what we see is that there is a huge stain of different colors here at the bottom. If we put this in logarithmic scale, it's easier to see. And what we have detected is a huge cloud of different behaviors, okay, that have a lot of variability in instructions, a lot of variability in IPC, which goes from 1 to more than 4. Okay, and all this is falling in this region over here, okay, where we have this very fine-grained parallel. Okay. So the next step is to apply tracking and see what is the evolution of the IPC degradation. Okay, but then for the tracking, I'm going to leave out this huge cloud of very different behaviors which are very close, because what the tracking tool does in the end is paint the clusters with the same color for the same phase in the code. So the same phase in the code is easy to compare between the experiments, okay? So same region in the code when you are using 1 thread is assigned to the same region when you are using 4 threads, is assigned to the same region when you are using 8 threads, okay? So in the end, tracking is going to paint the same region of code, all these with the same color, and then when we represent this with a centroid, well, this centroid is not so much representative of so many distinct behaviors. So it can be done, but it's not that useful. So I'm going to leave that region away. And I'm going to focus on these clusters over here, which are actually the most important clusters, okay, and that they cover 80% or 90% of the time of this iteration, okay? And the fine-grained one, we leave it apart, and we already know, I already suggested that maybe we should try to optimize this fine-grained parallelism to reduce OpenMP overhead, okay, so it doesn't express in the clusters like this. So my last part is to use tracking on the hybrid. I have it here. Okay, and as we had before, okay, here we have experiment with 1 thread, and we see the phases of the code, the clusters on the right side of the histogram of the plot with high IPCs, okay, on the top with high number of instructions. When we move to the next experiment with 4 threads, the clusters have moved down. And what does this mean? They move down because the vertical axis is instructions. Okay, and I gave you the heads up, this is strong scaling test. And this is another way to verify it, okay? Because we are using more threads, the amount of work per thread is reduced, and so the clusters are moving down in the instruction axis. Okay, and if we keep moving to the next scale, they move down even farther. Okay, it is easier to see if we put the log scaling here, okay, and I repeat, now it's going down halfway and then going down halfway again. Okay, and you can also see that things have moved to the left and the dispersion has increased a lot, okay, in IPC, okay? And so as we did before, we can represent the clusters with their centroids, show the trajectories, and now we clearly see that things are moving down because of the strong scaling, and they are moving to the left because there is IPC degradation, which is different for different regions of code. For example, for the green region, it goes left a little bit. For the yellow region, it has a drastic, huge drop. Okay. Actually, you can also see that there are some regions that actually improve IPC a little bit. Maybe these two regions are able to improve IPC because of better use of the cache, because we are using small chunks of data. Okay, and you can also see that in the right pane, as we did before. Okay, from the point of view of instructions, all regions of code are decreasing proportionally. So this is good because of the strong scaling. From the point of view of IPC, there are two regions that are able to improve a little bit, probably because of the caches. But then there are some regions that are decreasing a little bit IPC, but we have identified one that is decreasing about a 40% of IPC, which is the yellow one. So, wrapping up a little bit everything. With the basic analysis at the beginning, it pointed us to the most limiting factors for the efficiency of the application, and it pointed to IPC. Then with the clustering, we have identified a structure in the application, we have identified the main computing phases, and we have described those in terms of how much work they do and how fast they do the work. Okay, and with the tracking, we have seen the evolution in the behavior of these computing phases, and we have seen how do they degrade in IPC. And in particular, we have identified this yellow region, which is the one that is degrading the most. So the final question is, and who is yellow? Where is it in my code? So we can jump back into the trace. Okay. This shows me where the yellow cluster is over time. So if I correlate this with the parallel loops, and I synchronize these two windows, and I zoom around, I can clearly see that the yellow cluster corresponds to the orange parallel, and it tells me it's the calc hourglass control for LMs. Okay, so I know now where to go into the code to try to improve this. And that's all from my side. Last thing to comment is that in Carolina, close this. In the project folder where the material was located, sorry, you have on one side this demo folder with all the files that I used in case you want to revisit something. And in the material folder, you also have examples for MPI, MPI+CUDA, and MPI+OpenMP. That if you go to one of these folders, you will see there are scripts to run the basic analysis and to run the clustering. These are tuned for examples of Lulesh, but you can easily take these scripts and adapt them to your own applications. Okay, in case you want this afternoon in hands-on to apply to your codes. And that's all from my side. And I think we have 15 minutes left. That Judith, do you want maybe to show the hybrid MPI CUDA case?
I can show something, but you didn't leave me much time, so I can have a 12 minutes demo. You have to stop sharing.
Sure.
Okay, so let's try to do some very quick demo on MPI plus CUDA. For that, we have to use a different application because as we mentioned the first day, there is a version of Lulesh with MPI plus CUDA that we obtained in the past with some traces, but in fact, it's not longer working. Okay, so these are traces from Carolina that were obtained yesterday. And this is a very quick analysis just to show you how to use the basic analysis and how to interpret that data. Okay, so we can do the same thing that it was done by Herman, and I use called model factors with my traces. And that should cover very few minutes, okay? It's pre-processing the data and it's going to generate the output of the metrics for this hybrid model, okay? So that allowed me to specify in the meantime few recommendations about the basic analysis. The current version that is being distributed basic analysis, I think it may have some limitation. Let's say if you are overlapping communications with MPI, then the metrics will blame to MPI more time than needed. It will say that it's worse than reality, okay? We are working to fix that part, and because basically we have to check how to split that blaming, okay? So if your code is MPI plus whatever, and there is overlapping, this is not the case neither for Lules nor for cover lead that I'm using now. But if your application is doing that, and if you are working in this training or outside this training, please contact us either to tools@vsc.es or judith@vsc.es, and we will help you to do it that manually. So it can be done manually, but it will be in the future also done by the tool, okay? And also currently for CUDA, MPI plus CUDA application, it only computes the metrics, the hybrid model. It does not compute the approach I show in the slides where we have also GPU metrics, okay? But I will do that in the demo, okay? So what it says, global efficiency, well, first, the elapsed time is significantly reduced, but the efficiency is going down from 228 to 88%. So it's a big drop, okay? And we can see that, I reported that to the developer of the basic analysis tool. That should have been fixed, but seems that is not working for this case. So we have to ignore some of the metrics, or basically instructions and frequency scalability, because they are wrong, okay? And the reasoning is because the CUDA devices do not have counters, and it seems that the formula that we apply to fix it is not properly working, okay? But the IPC is working and is contact, and basically the speed that should be close to 4 and it's just 3.5, okay? The first thing we see is that the global efficiency is very bad for both runs, okay? And it's close to 50%. And this close to 50% may hint that the problem is that the CPUs are not being used, okay? But we need to verify that. So most of it is because of the power efficiency, okay? And globally, the balance is 50%, close to 50%. Again, validates this idea that the CPUs are not being used. And the communication has a big drop from 98 close to 100 to 88 close to 90. Okay, so it's still on the good scale, but with a big drop. The computations, we can only focus on these two metrics. Okay, the computations have a small degradation. Okay, that is not related with IPC. Okay, so my guess is that may be related by frequency scaling, but maybe there is also some instructions that should be fixed in the next release in the next days, okay? Then if you go to the hybrid to split the blaming between the two programming models, we can see that the level of MPI, we select MPI, everything is very close to 100, so almost perfect scaling in MPI, okay? And all the issues are related to the CUDA parallel runtime, that it's also pinpointing that maybe this distribution between the two guys, because it's mainly caused by this imbalance, but we can see that the drop, so the scaling problem is on the communication, okay? So as a summary, reading all these numbers is, okay, your efficiency with a small core count is very bad, 50%. It may be because you are only using the GPUs, then I'm saying half of the resources are being wasted. And then the communication efficiency is the one that has more problems with the scale, that is having a significant drop, just multiplying by 4 the number of resources, okay? So let's go to the traces. And sorry, I forgot to say, this is directly the focus of analysis. I ignore initialization and finalization, and I get, as you will see now, a large number of iterations, okay? So I load both traces with Paraver. And the first thing I can do, as we have been seeing in the previous demos, I can just go to hints, useful efficiency. This is with 8, and I do the same thing. Sorry, I do the same thing for 2. I can go to files, previous configuration, and it's the last one, okay? So I have the 2 efficiencies that is just the same thing reported by the basic analysis. Then what I can do is I can go to hints, useful histogram of computing time, and I load that. And this is a trick. I do a quick trick in order to do this step. I do that, This is for 2, and I do the same thing for 8. I can go to 8, and I can go to File, Previous Configuration, my last configuration, okay? And from these tables, I can generate timelines focusing on the large computations that are on the GPUs, and I do the same thing in both of them. I don't care how many regions I take, because the only thing I want to do is copy and paste the objects, okay? So I focus on the GPUs that way, copy and paste the objects. And, sorry, paste the objects, and I do copy and paste the size. Okay, that was my fault. So now you see, power efficiency, if I only consider the GPUs, is perfect, is 100, okay? And all the issues, that is the same we saw before, between 98 to 88, is caused by the communications, okay? So this is telling me my problem is on communications. My initial idea, considering I should have 20, 30 minutes slot, was to show you how to compute in Paraver, how to program Paraver to compute a nice metric. But due to the time restrictions, I will directly load that configuration. If someone that keeps on the training this afternoon want me to show you how to compute it, I will do that, okay? So I go to, let me start with the 8, that is the one that has the problem. File, let me go to previous configuration, and I have compute a metric that is telling me what is this CPU doing while the GPU is computing, okay? And let me start showing this metric with instead time, and let me change the statistic to percentage of window time, okay? And this is telling me the idling time of the GPU, what is the CPU doing, okay? And as I see here, the idling time in the GPU is in average close to 11%, let's say 11%, okay? How this 11% is being distributed. Then we clarify, this is based on the states we get in the traces. So synchronization, memory transfer, configuring accelerator, this is caused by CUDA. Then wait, toll, immediate send, group communication, immediate receive, this is caused by MPI, okay? So I did that configuration yesterday very quickly. I can produce a nicer configuration that just says MPI or CUDA, and then it will be joining. But that way I can even know the details inside MPI or inside CUDA, okay? And this is ordered by the total, so I see the higher percentage of wasted time is due to synchronization of the CPU with the accelerator. Then, but it's only a 5.5% of the total execution. Memory transfer is a 2%, okay? And then let's say if I sum up things from the configuration of the accelerator is 5 and 2 is 7, and this is plus 1. It's around 8.5% of the time, okay? Of this 11%. Then MPI calls, I have 2% for the wait tolls, okay? And the other one is almost nothing, okay? All the other calls, okay? So basically the wait tolls are the only one that are quite relevant, okay? So one thing we can do is we can check, let me load the CUDA kernels, okay? And this is for the full execution. So what I can do very briefly is I can use copy and paste it. Sorry, I want to synchronize the two windows in the same group, okay? Another thing, this is something we have to fix in Paraver. Names of the devices by default are too large. This should be also in a newer version, but by the way, I can in the meanwhile put just 10%, so the access does not dominate the execution. So I can start zooming in here. And if you remember, I was 522 and it keeps the same thing. I can still go doing that. See, now I see the iteration. I see repetitive colors, so I can take a few of them. Okay, and I can just focus in one iteration will be I start, no matter where I start, the important thing is that you take one iteration. So between the starting of this dark blue till it got back to the dark blue, okay? And now it skips the same thing, okay? That is telling me most of the iterations are the same thing. There is no deviation along time. It's a very quick version of knowing that there is no variability along time on this idling time of the GPUs, okay? So the first thing I see here that for me is quite noticeable is that there are things that are larger and that there are things that are smaller, okay? And I can focus on larger things, okay? And I can see that here there is only a very small amount of time in synchronization, okay? And I can do undo zoom. And I can focus on another large region here, okay? Here is a little bit higher, but the total percentage is much more less than before. So I can go to my heat, I can do undo zoom and go to that region where I see variability, okay? As I presented in the slides. Where I see variability is typically where the problems are. So I go to this variability region, okay? And I see something that are very, very small kernels. So I can go to these very, very small fine-grained kernels, okay? Okay, now I see it. Here in this region, the overhead, the time where the idling of the GPUs is 42 plus 28, 18 plus 16, okay, so it's almost all the time. And you have the same feeling here because you see, and in fact, I take a little bit of the large one. In fact, you are having also very small points in the timeline, okay? But these numbers confirm me that basically this is very, very small. And then all the time is the overhead. So let's measure again between programming models. I just have 1 more minute. Okay, so it's 42 plus 16 plus 5, okay? So it's quite huge amount of time in the accelerator configuring and working with CUDA environment. Wait all is 20%, okay? So it's not so negligible. Before it was around 2%, okay? And all the others, I think it can be ignored, okay? Well, running is just 3%, I can ignore it, okay? So basically in this region, there is some causes due because the CPU is working with MPI, but most of the time is configuring the accelerator, okay? And as I have reached my time, I prefer to stop so you have the break, okay? But just one thing I want to warn is that these traits allow us to identify that we are working on a new version of the tracing of the CUDA, improving some parts of it, okay? And in fact, we have identified that maybe 10% of this overhead in synchronization is our fault, is the overhead of Extrae, because like when you do very, very frequent printfs, okay? So if you are tracing very small things, the overhead become more important, okay? So, but the good news is that we are working to fix that and to improve it as much as we can. So if this afternoon you are tracing an application that has CUDA and you have very fine-grained things, you will notice that Extrae is highlighting this as more overhead on that part. But as we have seen before, if the regions are larger, okay, you have the good news at the end. So if I go to one region where I have nice things, okay, then the overhead of Extrae is negligible, okay? So that's what I can say in the amount of time I have, okay? So maybe if you have a quick question, we can do it, okay? But if not, we can talk in more details this afternoon. Is there any question? Sorry if I was too fast. If someone else wanted, I can repeat that slowly this afternoon and I can show you how I compute this nice view.
Okay, thank you, Judith. And if there are no questions, so let's have a coffee break and we will continue at 10:45 again.
Okay, I hope you're seeing my presentation, which will start with the Scalasca trace tools.
Yes, we can see.
Okay. So I'm going to continue where we left off in the presentation and demo that was done yesterday, where we had used Scorpio and Scalasca together and also the Cube GUI for examining profiles. That got us to the point where we had done some initial measurements. We had got some additional information that allowed us to refine and improve the profile that was collected, and then verify that the new profile had the information that would allow us to understand that application's execution. Profile information is relatively high level, and the next level of detail, as we've seen in the Barcelona tools, is that we can look at the execution trace for more information. What the Scalasca trace tools do is they do an automated trace analysis. I mentioned this at the beginning, that the idea of the automated trace analysis is to deal with traces in a way that distills them down into a high-level summary of what they contain, allowing you to identify what are the key performance issues of that execution in terms of inefficiencies, wait states, or even identifying what's the critical path of execution, which is the part that you need to focus on when you're optimizing and improving performance. The examples that we've been working with today have just been from a single node, are very small, less than 100 processes or threads. So we're dealing with relatively small traces of execution from just less than a minute from 100 processes. Typically, that's not going to be anything that's critical. But what we saw yesterday afternoon was that some of the applications that people are working with, they can very quickly generate huge amounts of trace data. So one of the examples I saw had roughly 2 terabytes of data that would have been generated if we did it, just traced everything. And I don't know how much the Carolina sysadmins would have appreciated that. I also know that the trace of 2 terabytes would not have been in any way convenient to analyze. So even though we can do analysis of very large traces, the more that we can do to do it automatically, the more we can use the power of the parallel system in which the trace is collected to exploit the available memory and processes available there. That will give us a scalability that we can use to analyze very large traces when necessary. But it also means that we can make the smaller traces from 1 or 2 nodes much more efficient as well. So that's where the automated trace analysis comes in, and that's what will be the key focus of this first part presentation. I mentioned it's a scalable trace-based analyzer, focusing primarily on the MPI and OpenMP communication and synchronization. So it doesn't handle anything that's happening on the GPUs or additional events for hardware counters. It's just focusing on the key interactions between processes and threads, which are primarily MPI, OpenMP. We saw yesterday how you prepare your application with ScoreP, you run it, you get a summary report. That summary report gives you the basic information that you can then optimize to refine the measurement, get a refined summary report, adding additional information, removing parts which are excessive and not productive. And once you've done that, you're in a relatively good position, having scored that measurement, having identified it contains the focus that you're interested in. You're then ready to enable tracing, and enable the trace collection is always better to know how large the trace is going to be. Just assume, of course, that your application is deterministic. If it varies from run to run, anything can happen. But if you've already done the appropriate scoring of the summary report, it will give you a pretty good estimate as to how much disk space you require, how much memory is required for each process, and therefore whether the trace that's being collected is actually something that's manageable and practical. If you're collecting more data than fits into memory, you'll just be paging all the time. You'll have terrible analysis performance. If the trace is 2 terabytes, as we saw in one of the examples yesterday, then you're just going to fill the disk or fill your allocation quota and have the sysadmin screaming at you as to what you're doing. So getting the trace down to a manageable size containing the key information that you want about the MPI communication and synchronization, the OpenMP, potentially with additional information about hardware counters, potentially with information about the GPU kernels. But the analysis that you'll primarily get automatically from Scalasca will tell you about the MPI and OpenMP efficiencies. So that's part which I'm going to focus on right now. What are some of the issues that we can identify by comparing what's happening processes? We can identify when there's an interaction between two processes. A sender and a receiver is an obvious example. And the timeline diagram that's shown here at the top of the screen, we have two processes. We have one which has gone into a receive, and that's a blocking receive. So at that point, it is waiting. And of course, it can do nothing in the receive until the corresponding sender initiates the communication. So it's blocking for a period of time, and then the other process gets around to initiating its send. At some point, the data is transferred to the receiver, and the receiver can process it and continue. But this part at the beginning is pure waiting time. It could have been doing something else instead of blocking, waiting for that data. Maybe it presumably needs that data, and if it can't do anything else, then blocking is a reasonable thing for it to do. But in principle, there might be some other computation that could have been used more productively for that time here. We can't tell exactly when the message transfer happens because that's happening inside the MPI, and we don't have insight into what's happening inside the MPI. All that we can see is when the application called the MPI send and when it came out of the MPI send, when it went into the receive, when it came out of the receive. Everything inside that is a black box, but we can tell from the parameters that the send was using who it was sending to. We can tell the message size, how much was sent, how much was received. Hopefully they're the same, maybe they're not. So what's available at the MPI interface level is what our tools and what the Paraver tools that you just saw are able to determine and analyze. So you may say that this example, you could avoid it by doing something in a non-blocking receive, which is certainly true. And there's examples shown here where instead of doing a blocking send and receive, it's using a non-blocking I receive. The receive returns immediately, and then it can do something else before at some point it needs the results of that message transfer, and it'll go into something like a wait for it. At the point it goes into the wait, it unfortunately still doesn't have the data initiated because the sender is still doing something else. So it's now no longer the I receive that's waiting, it's the MPI wait that is having to wait until the data that it requires has actually been sent. So we've moved the problem around, but we haven't actually resolved it in all cases. And you can also go to the other examples here where you have a non-blocking send or a non-blocking send and I receive. Basically, you're moving the waiting time around, but where things don't match up, where the sender is late, the receiver will have to wait for the send to be initiated. What's done for point-to-point operations is also done for collective operations as well, where you can imagine that if all the processes is doing a broadcast, they have to wait until the initiator of the broadcast actually gets around to sending the data. If it's a reduction, the root of the reduction has to wait until all of the other processes get around to sending it the data that it wants to aggregate and then be able to continue. So depending on which processes are involved, and it depends on the communicator, depending on the operation, depending whether you're the root of it or all of the processes are involved, you may have different waiting times on each rank. And if it's something like an all reduce, then all of the processes have to wait until the last one gets into providing its data, and then they can all continue. So that's one thing that the automated trace analysis can do. Another example is it can work out what is the critical path of execution. And it's the critical path that determines which processes are waiting and not able to continue until some other process has communicated, transferred some data to them. If you have a timeline and you have all the nice arrows connecting things up, then you can work through things yourself and build up this picture. It gets very complicated very quickly, but the automated trace analysis provides a way of identifying the critical path and the routines and the costs of them on the critical path in a more convenient fashion for you. So the details of the algorithm are not so important here, but we identified what are the waiting times on each of the processes in the receive or the wait part of the message transfer. And then the critical path is determined by working back from the last computation on whichever node it is, the one in the middle here, to the one that was sending to it. So the one that it had to wait for that message to be received. And then you work back through what that sender was doing. And then it was involved waiting for a communication from the lower rank here. So working back through this chain of communications and operations on the different processes, we can identify the critical path and how much of that time was for different operations. And now that we've identified that, the next question would be, well, what is causing all of this time on the critical path? Well, before we think about that, we would want to know what would happen if I was to change the time of execution of some of these functions. So if, for example, I was to make this bar execution here much faster, how much would I save in overall execution time? The quick answer is you'd save nothing at all, because you can make a bar much shorter here. You can take it down to 0. That means that foo bar starts earlier, but you still have to wait for the last process at the end. So you just have more waiting time. So if you're optimizing, reducing the cost of something that's not on the critical path, you're just increasing your waiting time there. You're not actually benefiting overall. So you have to identify it's the bar execution on rank 1 up here that is the first rank, top rank here, that is the costly one. If you can reduce that, then that send can be done earlier, this receive will be shorter, and then this foo bar execution can be completed much sooner as well. So that's the importance of the critical path and the importance of identifying the costs of the different routines that are on the critical path. Figuring out the root cause of the delays allows us to determine that in this example here, we have 3 processes executing foo. The foo execution on the top one is much longer than the others, which results in them having to wait until it is done and completed before the corresponding data transfers come from the others. So this is an extension of the critical path analysis, which allows us to break down the waiting time into wait states which are directly involved on the process that was responsible for the send. And it may well be that there's a chain of dependencies that the case at the bottom, the rank at the bottom, is actually waiting not directly for the top process, but there's an intermediary here. So it's an indirect wait based on some other rank. And so that these chains are important to understand as well. Okay, so what we would identify and mark as delay costs are the parts highlighted in this darker orange here, where this extra computation on the top rank is a delay that is impacting the others. There's an extra time resulting from there's a need for the send here, but that manifests as an additional delay before the other processes continue. So there's a direct delay and an indirect delay as a result of the chain of dependencies here. So that's some of the things that we can get from the trace analysis. I'll go back to the example that we started yesterday. The slides you can go through at your leisure. They go through a slightly different example, but it's actually the same example, but a different configuration. But if we do things live as a demo, I think it's a bit more engaging. I can figure out how to get my screen back. Okay. So this is the directory I was working in yesterday, and we did all of the instrumentation of our application, BTMZ, yesterday, produced an instrumented version of it here. And then yesterday, we got an initial measurement, which gave us the basic information that about how that MPI and OpenMP execution on a single node manifest. Just as a quick starting point, I'm going to So we did the filtering to optimize the measurement configuration. We can specify a named directory if that's what we want. So let's well, put in here. So I'm going to call this one. So I'm going to add the hardware counters just to show that we can add something to that measurement. That way. Okay. So now I've specified that I want a set of hardware counters to be added to my profile. I have a cycle counter, instructions, floating point instructions, floating point operations. This is all hardware dependent, but those are relatively standard counters that are available on multiple systems. And I'll just verify that we can run that. Hopefully it'll run relatively quickly. I don't know what the state F is. Let me try using the reservation as we have it available. This one should do. Okay. So this looks a bit better. I'll cancel the other one just because it'll get in the way, or it will end up being blocked by the one that's actually successfully running, or well, I'll just leave it and we'll see what happens. How are we getting on? And I guess F has failed, so let's see why it failed. Maybe I should have checked that earlier. Scan command not found. So need to load the Scalasca module. And I was using the Compy toolchain, so I'll load that first. And module load Scalasca 2 point whatever for Compy. So now let's try it. Okay, this time I'm getting a directory, one that I explicitly named. It should run more or less as quickly as it was running previously, which I remember was about 18 seconds. And so what do we have here? Here we have 19 seconds. So adding hardware counters, adding anything can be expected to add some level of additional measurement overhead. Hardware counters are certainly not entirely cheap. Depending on the counter, some are more expensive than others. But I have a measurement directory here that was created, and that measurement directory with sum plus HWC contains a profile. And now I can use square to look at that, see what it contains. Some HWC. So it does the post-processing of it. It's showing me my new measurement of BTMZ on the single node here with its 8 processes and 6 threads per process. As before, the iteration is the main benchmark part of the kernel. That's a part which was explicitly annotated. If you look in the slides, or if there's time, I'll show you the slides where that API for controlling measurement and annotating the measurement is described. There's also a part of the execution up here where also all of the measurement, whether it's profiling or tracing, was explicitly disabled. So recording was paused for a period during the initialization, then it was resumed again, which then continues. And then I have my marked iteration, which allows me to distinguish the execution time for the key part of the benchmark itself. As we saw yesterday, I think I showed you the the POP efficiency metrics for this execution. It's very efficient in this execution configuration. Some of the metrics, such as the IPC, the instructions per cycle, or the instructions, those are coming from those additional hardware counters, which I just added. So those were missing in the measurement yesterday, but if you add them, then you get them included in the assessment here as well. So nothing very interesting there. IPC of 3 is very good. If I go back to the left tree here, the metric tree, that's showing me the time as I had before, with this breakdown into various subcomponents for MPI, OpenMP. And at the bottom of this list are the 4 hardware counters that I requested. Instructions, which is the number of instructions executed, the number of floating point instructions, which is a large proportion of them. So more than 90% of the instructions are actually floating point instructions. What are floating point operations? Well, those can be a single instruction might be executing multiple floating point operations, like a fuse, multiply, add, and so those numbers might actually change. So we can get hardware counters, we can get cache accesses and other things. I'll let you experiment with those. It's hardware dependent. You can look at the names of the counters that are available on Carolina. Let me just see if is PAPI available. Yes, PAPI is here. So PAPI avail would tell me which of those predefined metrics are available. So if they're not available, unfortunately, there's no definition for them, but there are a number which are available. More typically on Intel platforms than on AMD, but here's one for branches taken. Here's branch instructions. Something about cache, perhaps. So these are various counters about level 1 instruction caches, level 2 data caches, whatever. So depending on the nature of your computational problem, you might want to experiment and explore multiple counters to figure out what's going on there. All of that profiling. How do I now get a trace? So I'm going to use the same executable and re-edit my Scran job script. I'm going to comment out this instruction naming because I prefer the automated one. I don't need the hardware counters in the trace, so I'm going to eliminate those for now. There's a couple of numbers in here. Scope P total memory equals 80 megabytes. Where did that number come from? I'm going to use it, but where did it come from? And I'm going to enable tracing as well, so I can do that in here, or I can use a -T flag to the scan command. Both of them will do the same thing. So I'm enabling tracing, but where did I get this Scope P total memory requirement from? And why do I need that? Well, let me just submit it, and then I'll take a look. You may remember that we did a scoring of with Score P. I don't need the details. So this was our previous execution yesterday, where we'd already done the filtering of it. I need to give it the profile. So what the scoring did was it came up with an estimate of how much trace was going to be collected by each process, and therefore the amount of memory required on each process or at least on the largest process, the one with the largest requirements, and then the total size of the trace in total. So it's estimating, and there's compression and all sorts of other things applied to keep the traces as small as possible, but compression is not something you can rely on. It's saying that to be safe, you would set the total memory requirements to 88 megabytes. I've cut things a little bit and just use 80, so we'll see if that works out. And the total disk space required could be up to 600 megabytes. This was after filtering, of course, because if we had run the initial version, which had other sorts of issues because it didn't have, it had more I did more events, I did more measurement overhead for it. There, the initial version would have been not this 600 megabytes, but it would have been 160 gigabytes, and I needed 20 gigabytes per process, which is clearly unreasonable. So if you need more than a gigabyte, I think you're doing something pretty extreme. And if you're collecting data from thousands of processes, you'll end up with very large traces very quickly. So do appropriate filtering. If that doesn't cut everything down as much as you need, then think about doing a shorter execution. You may not need to run all 200 iterations, or you may want to just run a few. So I just fail again. So whoever installed the tools on Carolina set up the directories wrong. So these are directories that don't exist. I need to set the trace file system to something more reasonable. So let's try that. So you should be using Scratch, so that should have been set automatically. And let's see if that works now. Running. And I see my directory has been created. It will contain quite a few things more than it did before, because trace files are already, they're not written, of course, at the beginning, but they're opened at the beginning so that they can be written to during the course of execution. They're in a separate subdirectory called traces, but typically they're relatively small when the measurement starts. It may well be that we're more or less finished. Let me just check. So just to check here, when we did the scan, this time it recognizes that trace collection was desired, and so it renamed the experiment directory, or defined a different name for the experiment directory before it started measurement collection. It's also saying it's going to do the trace analysis as well, but it can only do that once the trace has been collected. We have our benchmark execution for 200 iterations, again, 19 seconds. Collection finished after 24 seconds, and then it went immediately into the analysis. The analysis is done using the same execution configuration inside the same batch job. So it's running srun again with our 8 processes and 6 threads per process. But instead of running the application, it's running our trace analyzer, which is Scout. Scout from the Scalasca module, and it's running the hybrid version, the version that's able to handle MPI and OpenMP together. Takes the handle for the trace data so that it knows what to work with, and then it runs through replaying the execution to analyze it. How long does it take to do the analysis? Well, that depends on how much data has been collected, amongst other factors. Depends how much communication is in there. As a rule of thumb, it could be roughly comparable to the execution of the application itself. So the application took 24 seconds to execute. That included writing the traces. So it's a bit more than just running the application on its own. It's actually including the writing of a trace at the end, as well as the creating of it files at the beginning. But the trace analysis in this case was a few seconds faster. It doesn't have to replay all of the computation, of course. Depending on the type of communication it's doing, it might actually be slower in certain circumstances. But as a rule of thumb, I would say that if the application runs for 24 seconds or 30 seconds, then double the length of time that you allocate the batch job for, so that the trace analysis has time to start and run at the end. So if it runs for 10 minutes and set a job length of 20 minutes, it will typically be a lot shorter than that. If it only gets part of the way through and is cancelled, then you can restart the analysis without needing to redo the trace collection. The other thing it's telling me at the bottom here is that I now have 400 megabytes of trace data in this trace directory. At 400 megabytes, how does that compare to what the score was predicting? Here was my score, not that one, this one. So the score predicted that it needed 600 megabytes. With compression and whatever, it was actually only a bit more than 400. So it's an approximation, but it's giving you a rule of thumb, a bit of guidance. And so it's the difference between megabytes and gigabytes or terabytes that you're looking for, not the precise numbers that are so critical here. So now I have a directory with the trace, and that directory contains the trace data. We need to see what's in that directory now. This one. So I have the profile because I didn't disable profiling. So if you don't disable it, you still get the profile. It now has various files from Scout, which were produced. It has an analysis report from Scout, which is a bit bigger than the profile, because the Scout analysis has additional information in it that was collected from or generated by the trace analysis. There's a couple of files here for Scout error and Scout log. You should always take a look at what's in the Scout error. It won't be there if there's nothing to if it's empty. But if it's there, it's always a good idea to verify that what's in there is acceptable. And of course, in this case, what's in there are the errors from OpenMPI that we always seem to get and seem to be harmless. So we can ignore those. The other file is the output from Scout itself. So just what we also saw in the job output, it has a record of that as well. We have our traces directory with all of the trace data, and we have a handle file, an anchor file here, which allowed Scout and allows other tools to look at the trace. So I'm not going to spend a lot of time dealing with Vampire. Vampire is available. Vampire is a trace visualizer. If I give Vampire the name of this directory, it will show us what it contains. So it's loading the trace data and will produce a visual representation of the data that it contains. This, of course, gets longer and slower depending on how large the trace is, but there's also a parallel version which is able to handle very large traces. This is running remotely, so some of the interactivity issues might be related to the latency as opposed to the nature of Vampire itself. We're seeing a timeline like we were looking at with Paraver. We have time going from left to right. This is showing an execution of 24 seconds here. The first 2.5 seconds are MPI init thread, which is part of the initialization, which we have to accept. It's not under our control. And then we have various computation going on. During the init thread, we see that the worker threads, the worker cores are not being used, but after we get into the parallel computation, we see those as well. And we see the 5 additional OpenMP threads for every primary thread from the OpenMP application. I'm only able to see the first few processes here because it takes a bit of space, but I can adjust this display, adjust the process height to fit the chart, fit the available information. So now I'm seeing all 8 processes with their 6 threads. And if I add additional charts, such as the process timeline, one that I like, then I have a view of what individual processes or threads are doing. So I'm looking at the master thread of rank 0 here. It's showing me the init thread at the beginning, and then it goes into this iteration, which is doing a number of ADI steps. And inside the ADI step, things which I can't read here. But if I drag the mouse to define a region, I can zoom in and get some insight into what's happening with perhaps an individual time steps. I just choose one of the iterations at somewhat random. I can then set the zoom just to zoom into that. So now I'm looking at just one iteration, and maybe I can see what's going on, maybe I can't. If I zoom in further inside that single iteration, all of these black diamonds or marks are actually individual or aggregates of communication. When it can't resolve individual communication events, it's just showing the aggregate. So if I zoom in close enough, I'll hopefully be able to start resolving some of them. Try this one. You can also zoom in the other direction. That might help things. Yeah, so now I can see for for process 5, MPI rank 5, and its threads, they were executing some Y-solve computation. They then went into an implicit barrier here, and they all had to wait until the last one completed its work. And then the barrier completed, and then it went into what is probably the Z-solve. Yes. And then new parallel region created, and then continue after that. So I can scroll through this, I can zoom, I can unzoom, I can examine things at arbitrary levels of detail, depending what I'm interested in. But it's a bit of a needle in a haystack issue. Sometimes it's hard to figure out where the problems are when you're showing everything all at once. The other charts are, I think, self-explanatory. This is a profile. The profile updates based on what I've zoomed into. So here I'm zoomed into just a subset of processes and a subset of time interval. If I zoom back out to the full execution, then it's not really changing much because I have 3 expensive do loops, X, Y, and Z solves. There's various things happening with some right-hand side computation. At the beginning, I have a thread, which I probably don't care about, but if I was to set my zoom interval to the iteration part here, then I get rid of the initialization, and I see, for example, the relative time in the implicit barriers, whatever. So this is the information that you would expect to see in the cube profile, showing it in a slightly different graphical form, but the numbers would be exactly the same, based on the same measurement, based on the same data. There's all sorts of other stuff in here, which I'm not going to go into. If you've used Vampire before, or if you're interested in using Vampire, then you can try it out. It has things like communication matrices, which allow you to see at a glance more of the interaction between processes and threads. In this case, the threads are not actually very interesting because all of the communication is done by the masters. So if I was to group by MPI rank instead, then I would just see the MPI processes. They're all sending 200 messages. If I changed it to another metric, I can see the amount of data that is sent, and we see that they're sending different amounts of data. Even though they're sending the same number of messages, the amount of data that is being transferred is varying. And then, of course, the corresponding cost, the time for what do we have? The data rate, for example, or the average data rate will again be varying depending on how much data is sent between who. So all sorts of lovely information that you can explore, just like you were exploring it with Paraver. You can use Vampire if you're using with Scalasca instead. Okay, so we're now done with Vampire, but what did the Scalasca trace analyzer come up with? So there was if I run square again on this new directory, the trace analysis directory, it has a profile to process, it has a scout file to process, and then it will show as the most comprehensive one, which is the trace analysis containing the additional metrics that Scout was able to generate. The structure and what we see in the middle and on the right-hand side will be exactly the same as we had before. What looks the same at first glance in the time hierarchy won't be exactly the same, and that's one of the reasons that there are these magenta highlights around things. At a certain level, we'll get down to the additional metrics that were collected and determined by the Scalasca trace analyzer. So now we're seeing them highlighted here. Instead of seeing the total time in the synchronization collective, the barrier, if I select it and it will show me it's a barrier, how much of that time was actually waiting time, going into the barrier or after the barrier, where the processes came out of it at different times. So the good news is that they all finished the barrier at the same time, but they all spent almost all of the time waiting going in. So no surprise there. There's nothing to be done in the barrier other than wait for the last one to arrive. And so when we look at the waiting time in the barrier, we can see how that varies across the different master threads in this case. Similarly, for the collective operations, we have a simple reduce here, so we can see how much time going into the reduce was waiting time. In this case, again, negligible. For the point-to-point operations, we have something that's perhaps a little bit more interesting. Here we're seeing the point-to-point operations in the exchange QBC boundary conditions. The I-send and I-receive are relatively quick. Most of the time is actually in the wait all in this case. And if I expand the hierarchy here, it's distinguishing between the time which is late sender time, where a receiver has to block, where the wait has to block waiting for the corresponding send to be initiated, versus the time that was associated with the processing of the message itself. So in this case, it's a little bit more than half of the time was actually wasted waiting time. Potentially wasted, it could have been used for something else. You'll also notice that one of the things that I distinguished by adding this iteration region here is that there's a warm-up phase of this benchmark where it executes the QBC and the ADI solver. It just does one or a few iterations before it goes into the main computational, timed computational iteration loop. But by marking or distinguishing the iterations that I'm interested in from the initialization, which in principle I'm not, I'm also able to distinguish those. And so I could have included that as part of when the measurement was disabled. That would have got rid of it. But I can also quickly ignore it and just go down and look at the iteration itself, which is the part that corresponds to the benchmark. Let me get rid of that. Close up this a little bit more. So we have some additional metrics here, similarly for OpenMP. There won't be additional metrics for CUDA or anything else yet. Maybe that'll happen in the future. Idle threads was something that I mentioned yesterday that is nothing to do with the trace analysis. But when I have the when I have it here, I just wanted to make sure that it was explained here. So when we're outside of the parallel regions, we're just executing serially. Get it again. Where is it? Oh, there it is. Nope. If I go to the top, I can find it easier. I hope. Idle threads time. So if I'm thinking as a timeline, I have a number of processes executing outside of the parallel region. I have the primary thread executing, and then I go into the parallel region. It starts a number of threads, which execute for a while. At some point, they finish. There's an implicit barrier or something, perhaps. And then we go back to serial execution before we go back to the next case. So this time, which is shown in red here in the serial part, is idle threads time. I also will have idle threads if I don't have all of the threads in the parallel region active. So if I have a parallel region that is only for 3 threads and I have asked for 4 or more, then some of them will be idle outside of when the others are inside the parallel region. and that would be distinguished as another metric here, limited parallelism. So that's the case where a thread is idle, but it's idle because there's insufficient parallelism in the execution at that point. In this case, it doesn't apply, but it's worth explaining at the same time. If I go down this list of metrics, there's a lot of them. I don't want to go through all of them in detail. The critical path was one that we explained, so I'll look at that. There's an online explanation of it, which is hopefully insightful. Actually, probably don't need it. At the top here, I had total time for the different paths of execution. So I have all sorts of numbers here. This is the total time in the ADI, 800 seconds. But how much of that time is actually time on the critical path? If I select the critical path metric, it tells me that of the 19, 20, or whatever seconds, there was 18 seconds of it was in the ADI. And then this is how it breaks down across the different solves which were caused here. There's no significant imbalance between the processes here, so it's actually pretty equal, but depending on your application, it may be doing very different things on different processes, and then this distinction of the critical path will be much more valuable. How much imbalance is on the critical path? That's a measure of how much you might gain by redistributing and balancing your computation. And then you want to know where do I need to apply that? In this case, you could gain 3 seconds of the 21.5 seconds. So that 3 seconds is where would I get the most benefit from that? Well, some of it's in this compute RHS. Most of it in this case is actually coming from the MPI init, which is out of our control. So we really have to ignore that and deal with what's happening in the Exchange QBC. There's some time there, or in the compute RHS. So those are some of the metrics, but I want to make sure that we have a chance to look at some more interesting applications, such as something from CUDA. So I'm going to finish with what we were looking at there and see how things change when I take another example. I'm going to go to Overleaf, which was one that I mentioned on the first day. Again, I would build it and build an executable. So if I do make, I think I need to say compiler equals PGI, or it's probably a good idea to say compiler equals PGI. So GCC, I don't want to be using GCC. I want to be using the NVIDIA, because GCC doesn't have the OpenACC support. So let's get rid of our Comp module purge, module load NVIDIA, module load Scalasca. And I want the video one. That'll do. That should do it. So let's do make again and see what happens. Okay. So it's building the application in this case without any instrumentation, but building an executable, which I could run. Maybe I even will run. There's a number of source files here, but in the bin directory, it has produced a Cloverleaf executable. I'm going to copy the job script for our Carolina, which will allow it to run. What's inside here? So just srun Cloverleaf. It's running on a single node with 8 GPUs, and I'm going to run 8 tasks, so each process has a GPU. There's reservations for the afternoon, but I'm just going to be lazy and see if it will run quickly enough on its own. And that seems to be the case. So I'll let that continue. Verify that it started. Okay, it's already going. It stays at 8 processes. It's finished. It took very short period of time. It did 87 steps. It tells me which rank which device each rank was using. They're all using separate devices. That's fine. I could run a larger test case, which would be more interesting, but in the interests of a quick demo, I'll omit that. I want to do a make clean here to get rid of the pre-built executable objects. Inside the make file, it has some hints. It tells me how I might want to use ScoreP with this. So it's an OpenMP application, so I want to enable OpenACC. ScoreP doesn't do that automatically yet. At least it doesn't recognize it in this case. I could ignore CUDA, or I can have CUDA. In this case, I'm quite keen to have CUDA as well, because I will see the kernels. And like with BTMZ, I have manually instrumented the most interesting region here. So I have marked a particular region of interest. So let me use that. Prep equals ScoreP, user, OpenACC, CUDA, just give it the works. And now at the top, I should see I'm instrumenting everything with ScoreP. This is all output from the NVIDIA compiler, so you can turn that off, but maybe it's interesting to see what it's doing. Come on. Okay, so we're done. We have a new directory in ScoreP, so it's separate from the original. So I now have an instrumented version that has my ScoreP instrumentation in it. Give me another job script, one that, as I said, I can run it in the default configuration without any additional job script, but I don't have time to do all of the various permutations, so I'm just going to take the available job script and let's see what it contains. Again, it's the same execution configuration. I need to enable ScoreP OpenACC. Again, it doesn't do it by default. Curiously, it does enable the CUDA by default. It just doesn't collect the OpenACC. I don't really care about all of the internals of CUDA. That's just noise as far as I'm concerned. But I'm kind of curious as to what's happening in terms of what kernels are being executed when the GPU is idle. So I'm going to keep those and avoid everything else. So let's see what happens if I submit this. Running, which is good. I have my ScoreP measurement directory. It's telling me the number of processes. Maybe at some point we'll augment it to say how many GPUs, if it can work that out. But at least I know I'm running with 8 processes here. Should run relatively quickly. I already have the profile there. So what's in the profile? Okay, on the right-hand side, I have single node, I have my 8 MPI ranks, and I have 8 CUDA devices. So far, sounds plausible. For each of the CUDA devices, I have an execution context and a CUDA stream. They all have a single CUDA stream in this case, so it's relatively boring, so I'll just collapse that, but just keeps things more concise. If you have multiple streams, multiple contexts, you would see them as part of the hierarchy here. How do the devices relate to the MPI ranks? Well, it can vary, but if I select an MPI rank, this link information here is telling me which CUDA device it has events associated with it. And in this case, it's a one-to-one correspondence, so it's pretty easy to work out, but it might be something much more complicated. My application is split into two parts. I have one part which is main and one part which is kernels. And the kernels are the GPU kernels running on the devices. They have the name _GPU. That's coming from the compiler, so that's just what the NVIDIA compiler does. I see lots of initialization kernels, which are not so important. And then I have some more interesting ones for ideal gas or whatever. That seems like one of the more interesting ones. And I see then the execution time for that kernel across the devices. If I look at the visits metric, I see how often that kernel was executed, and it was executed 185 times, again, across on each of the devices. So whereas the initializations were executed once, the ideal gas kernel was 185 executions, and these other ones for packing and unpacking messages have differing amounts. Here, the differing amounts are perhaps explainable by the fact that it depends on where a process is in the network of processes. So here, I have 4 of them, the even numbers, which are packing the right. The ones which are packing the top are 0 to 5, and then 0 to 6 and 7. And there's other packings for top and bottom that'll be somewhere else. If I can find them. Bottom, so that's 2 to 7, but not 0 and 1. So depending on where they are in the grid, they have different kernels that are being executed. And of course, that has an impact on how long they take to execute. Time. So here it's saying 84 seconds. There was 5 seconds executing on the GPU, the kernels, and 5 seconds on the CPUs executing the host computation. You can go down through the host computation time, and I think the most interesting part is in this hydro, which is where I marked a time step loop. So that is the part that is particularly interesting that I might want to spend more time looking at. And I see it was only 1.3 seconds. So I have half of the time in this case on the CPUs, half of the time on the GPUs. If I expand the time arc a year, it's telling me that I have a lot of idle GPUs. That's because I had the idle metric collected, so it tells me that a lot of the time on the GPU execution is actually idle time. So that's to be expected because the initialization and most of these kernels are, when I select a kernel here, so I see which devices are executing that kernel. Yeah, I should have included the call path information, which I think would have allowed me to see the CPU that was associated with it. But I mean, clearly these are all associated with the initialization, which we're not interested in. The ones which are packing and unpacking the messages or updating the kernels are the more interesting ones. The execution time can be broken down into different parts, part which is computation, MPI we've seen before, or OpenACC. And OpenACC has different breakdowns here for launching kernels, for synchronization, for memory management. And in principle, you get something very similar for CUDA, which we didn't collect, or we disabled the collection of it, so we don't have that information here. It's a bit redundant to collect CUDA information as well as OpenACC. If the CUDA is coming from OpenACC, it's better to have all of the time associated to OpenACC itself. If you have additional CUDA libraries, then you have a mixture and it gets a lot more complicated. Whereas the synchronization time for OpenACC, most of it's in this time step. I see most of the time is in this advection, kind of split equally here, but I take the MOM, and then I see the data regions, data enter and exit, as well as the compute region. And in the compute region, I'll have the various kernels that are being launched, as well as the weight for the results of those kernels, another weight for some other kernels. So just like for OpenMP, I can see the structure of the parallel execution. OpenACC gives me a similar structure that allows me to distinguish the various kernel launches, the various weights, the various data transfers, which are associated with the different OpenACC constructs here. This is the way in which the metric hierarchy is structured by default. If I look at the general panel, I can get back to time step here. So I'm selecting time step. In the general panel, here I have, I don't have so the new version of Cube will have the calculation of the efficiencies, but this was an older version that doesn't have that. So I'm not going to show it here. So let me load the newer version of Scalasca, or the newer version of QGUI is what I need. This and see what happens. Okay, that looks relatively promising. So this is a restructuring of the metric hierarchy. So this is configurable through a specification file. So here it's showing 82 seconds of execution time, which is the host part of the execution, versus 42 seconds of device time, which is what the CUDA devices are doing. And that's where, of course, we have our kernels being executed and our idle time. So if I expand the device time here, I see which part of it is executing CUDA kernels and which part of it is not executing kernels, which in principle is idle. So it should be no surprise that the 42 seconds match up. This is assuming that there's a one-to-one association between processes and GPU devices. If you have many more processes and you have GPU devices, or if you have a single process that is running multiple devices, then that association won't apply. But in most cases, you have a single process, or for every GPU device, you have a single process that is managing it and responsible for driving it. Where is our time step again? So this version should show me the GPU efficiency metrics. And let me see. Again, for the focus of analysis, I've specified here it's determining which kernels are executed within that region, and then it's calculating the efficiencies for that combination of the kernels which are executed plus the host computation for that interval. The presentation here needs a little bit of work, but I don't think I can adjust that right now. In principle, it has worked out the regular MPI parallel efficiency. It's worked out the maybe it hasn't worked out the GPU efficiencies. Maybe I need to do something else. This is all work in progress, I'm afraid. So if it hasn't worked or isn't working, then it's something we need to improve. Let's calculate. And now I have at least something that's giving me GPU efficiencies, telling me the GPU loaded balance, telling me the communication is perfect. Why did it not work for just a time step on its own? Don't know. It should be able. It can only work out the association if I have the appropriate markers in the profile, and I unfortunately didn't collect them, so that's something that I should add. I don't know if I don't really have time to do it now, but the marker required I should be able to determine by using Scorpy info config vars. And look for optimise. It's a CUDA attribute. And the attribute I need is the kernel call site. So if I add kernel call site to my my measurement, then I hopefully have something that's much better than what I had by default. So this is work in progress. You're welcome to try it out. We'll take you through the steps in the afternoon. What do I want to finish with? I think that was the basics about. I mean, I can do a trace and a trace analysis. Maybe I want to do that while I'm here. As I said, the Scalasca trace analyzer won't actually analyze any of the CUDA information. So it will actually abort if it finds any. So I'm going to turn it all off so that I can do a trace collection. So nothing from CUDA, or in principle, I could have information on the host side, but I don't have information from I don't want kernels and GPU information. So let me see if this will work. I don't think I'm really going to wait for it, but in principle, it will. I did enable tracing. That was a. So there's a lot of different things that you can try out on your own in the afternoon sessions. But maybe there's time for 5 questions if you have anything to clarify in the last few minutes before we go into the lunch break. I don't see the chat, so if someone has something that they want to ask, then either tell me or someone else has to read it.
There is one question.
Yeah.
Will Cocos labels be in the traces?
Okay.
Can you repeat that? I didn't catch it.
Will Cocos labels be in the traces?
Will Cocos be in the traces?
The labels. I mean, I suppose it's the API. I have no news about Cocos. I don't know.
Yeah, I've never used Cocos either. So it is, my colleagues tell me it's supported. It's in our release information that it's supported. I've never used it, so I have no idea what you get from Cocos. But it almost certainly, well, I've never used it, so I doubt it's enabled by default. It's in the installation, so you can certainly try it out. You may need to explicitly say -- Cocos. So when you run the Scopy instrumenter, there'll be a Cocos option that you'll might need to give it, because I don't know if it will do it by default. And then it'll be interesting to see what you get. So again, I have a new trace. load up that new trace in Vampire, which was needing the directory. I need to load Vampire because I purged it. Yeah. Would have been more interesting if it was the version with the CUDA kernels, but now that those are disabled, I just see what's happening in the host threads. Yeah. Lots of things that we can try out with your codes in the afternoon, or try it with the examples in the afternoon if you're interested, but I think we're more or less out of time for the morning session here. So this is your last opportunity to give us some feedback on, some verbal feedback as to what we would need to focus on in the afternoon. I know that a number of you were able to get measurements yesterday. As I said, some of them were a bit more challenging to work with than others. Some of them we still have to do some work on to score and filter them to make them a bit more efficient. Some people got traces already, and we're looking at those, both from CPUs and GPUs. So I think that the people working in the afternoon were quite productive yesterday. So we look forward to continuing that work in the afternoon session. Hopefully you can, at the beginning of the afternoon session at 1, give us a short briefing, a short update on what you were doing, what issues you might have encountered, or what you were able to achieve, and in particular, what you would want to focus on for the rest of the afternoon so that we can decide how to split up and help you. So think about that. If you have something to show us, that's perfect. It's easier to look at something together than it is to exchange email or chats or whatever. So we look forward to hearing from you in the afternoon session. I think that...
Just one comment from my side for the attendees that will not attend in the afternoon. If you install VSC tools on your side and you do some tests and you have any issue, please feel free to contact us, either tools@vsc.es or judith@vsc.es if you want to contact myself, okay? So we will be happy to, after this workshop, if you give it a try and you have some questions, you have some issues, also you can contact POP if you want us to do some analysis. That's it from my side. Thank you.
Okay, thank you to both of you, Brian, for the presentation, and also participants for the attendance. If they are not continue in hands-on parts, then we are glad to have the course for you and hope you enjoyed it, and see you after lunch at 1 p.m.